Alex, I was reviewing a postmortem from a mid-sized fintech firm yesterday. They suffered a catastrophic billing event. A developer key was compromised, and the attacker spun up the largest available EC2 instances in the Sao Paulo region. The company operates exclusively in Northern Virginia. They had standard IAM policies in place. Why didn't those policies stop the bleeding?
Because IAM policies are strictly about identity, Maya. They define what a user is allowed to do, but they exist inside a container. If that container doesn't have hard walls, the permissions bleed out. That startup failed because they ignored the governance layer. They lacked the absolute ceiling. That is exactly what we are dissecting tonight on High Yield Audio Labs.
This falls squarely into Domain 1 of the SAP-C02 exam, designed for organizational complexity. It is creating a multi-account environment that is secure by default, not secure by hope.
Correct. The first mental shift for the exam candidate is to stop thinking of AWS as a single account. A single account is a single blast radius. If an attacker gets root or administrator access in a single account architecture, the game is over. In a multi-account architecture, we contain the explosion. We use AWS organizations to group accounts into organizational units, or OUs.
Let's visualize the structure for the listeners. You have the root at the top. Under the root, you have OUs. Inside OUs, you have accounts. The exam often asks about the hierarchy of policy application.
Imagine a tree. The root is the trunk. The OUs are branches. The accounts are leaves. Now, here is the critical concept. Service control policies, or SCPs, flow down the tree like water. If you apply a restrictive SCP at the root, it trickles down to every single OU and every single account beneath it. If you apply it at a specific OU, it only affects that branch and its leaves.
And this brings us to the most common trick question on the exam regarding SCPs. Does an SCP grant permission?
Never. This is the mantra you must memorize. An SCP never, ever grants permission. It is a filter. It acts as a guardrail. Think of it this way. IAM policies are the gas pedal. SCPs are the brakes. You can press the gas pedal, the IAM policy, as hard as you want, giving a user full administrator access. But if the SCP, the brake, is clamped down on a specific action, the car does not move.
So, if I have an IAM policy that says allow S3 full access, but the SCP on my OU says deny S3, what happens?
The deny wins. The request is blocked. It is an explicit deny at the organizational level. The SCP sets the maximum available permissions for the account. Even the root user of the member account cannot bypass an SCP.
That is a vital distinction. The root user of a member account is constrained by the SCP. But what about the management account? The account that owns the organization?
That is the exception. SCPs do not apply to the management account. The management account is the God mode of the structure. If you apply a deny policy to the root of the organization, it will affect every member account, but it will effectively be ignored by the management account itself. This is why we treat the management account as a radioactive vault. You should arguably never deploy resources there. It is for billing and governance only.
Let's talk about the strategy of deny list versus allow list. By default, when you enable SCPs, AWS attaches a policy called full AWS access.
Right. The default state is an allow list strategy, but it starts wide open. The full AWS access policy simply says, allow action, resource, It allows everything. To restrict access, you attach a second policy that denies specific things. For example, deny all actions in regions other than us, East 1. This is the deny list approach. It is easier to manage because you leave the default allow all in place and just layer on your restrictions.
And the allow list approach?
That is for high security environments, often referencing NIST 800-53 or PCI DSS requirements. You detach the default full AWS access policy. Now, nobody can do anything. The account is dead. Then, you explicitly attach an SCP that allows only EC2 and S3. This is a whitelist. It is incredibly secure, but the operational overhead is massive. Every time a developer needs a new service, like DynamoDB, you have to update the SCP at the organizational level. For the exam, assume the deny list approach. Blocking specific dangerous actions is the standard recommendation unless the scenario explicitly demands a zero-trust whitelist model.
Let's go back to that cold open scenario. The startup with the unauthorized GPU cluster. How would an SCP have saved them?
Simple. They should have had a region restriction SCP applied to the root of their organization. The policy logic is deny, action, star, condition, string not equals, requested region, us, east, 1.
Translate that. That is the power of the governance layer. It overrides local stupidity. Now, Alex, let's pivot to automation. Managing these OUs and SCPs manually in the console is fine for 3 accounts. It is a nightmare for 300. The SAP-C02 exam expects us to know about AWS Control Tower.
Control Tower is the easy button for AWS organizations. It acts as an orchestrator. When you click Set up Landing Zone, Control Tower builds the entire multi-account structure for you. It creates a log archive account for centralizing CloudTrail logs. It creates an audit account for security cross-account access. And it sets up the account factory.
The account factory is powered by AWS Service Catalog, right?
Correct. It allows users to provision new accounts that are pre-configured. When a team needs a new environment, they don't file a ticket with IT to manually click through the console. They go to the account factory, enter a few parameters, and Control Tower spins up a new account, attaches the correct SCPs, joins it to the correct OU, and sets up the networking.
Control Tower uses the term guardrails. How does a guardrail relate to an SCP?
In Control Tower speak, a preventive guardrail is an SCP. It stops bad things from happening. But there is a second type, detective guardrails. These are backed by AWS config rules.
Explain the difference in a failure scenario.
Sure. A preventive guardrail, SCP, says you cannot disable CloudTrail. If you try, you get an error. A detective guardrail, config rule, says, I see you allowed public read access on this S3 bucket. It doesn't stop you from doing it, but it immediately logs the violation, alerts the security team, and can even trigger a Lambda function to auto-remediate, to go back and close the bucket.
So preventive is you can't, and detective is you shouldn't have.
Precisely. And for the exam, you need to know when to use which. You use preventive guardrails, SCPs, for absolute non-negotiables, data residency, region locking, preventing root user usage. You use detective guardrails for granular resource configurations where you might need an exception process, or where the logic is too complex for the JSON of an SCP.
Let's discuss the tagging strategy in organizations. Can you enforce tagging with SCPs?
You can, and you should. You can write an SCP that denies the run instance's API call if specific tags, like cost center or environment, are missing from the request. This forces developers to tag their resources at the moment of creation. If they forget the tag, the server doesn't launch. This solves the unallocated costs problem that plagues every CFO.
I want to touch on a specific edge case involving delegated administrators. Historically, all organization management had to happen from the management account. That is a security risk because we want to log into the management account as rarely as possible.
Yes, AWS has rolled out delegated administration for many security services: GuardDuty, Security Hub, Macie, and IAM Access Analyzer. You designate a specific member account, usually the security or audit account, as the administrator. This allows your security team to manage the entire organization's security posture without ever logging into the master billing payer account.
Does that apply to SCPs themselves? Can I delegate the ability to write SCPs?
That is a trickier area. Generally, policy management is centralized. However, you can use IAM permissions to grant a specific user or role in the management account the ability to attach or detach policies. But true delegation of organization management is limited compared to services like GuardDuty. Stick to the principle. Management account is for paying bills and high-level structure. Member accounts are for work.
Let's talk about the quarantine scenario. You identify a compromised account within your organization. What is the architecture move?
You move it to a quarantine OU. You should have an organizational unit pre-built with a deny all SCP attached to it. The moment an incident is confirmed, you drag that account into the quarantine OU.
And because of inheritance.
Instantly, every permission in that account is revoked. The deny all flows down. The EC2S might keep running, but no API calls can be made. The data cannot be exfiltrated. The attacker is frozen in carbonite. Then, your forensics team can assume a specific role that is whitelisted in that SCP to go in and investigate.
That is a classic exam scenario. Fastest way to suspend all activity in a compromised member account. The answer is almost always related to moving it to an OU with a restrictive SCP.
One nuance to remember: moving an account takes time to propagate, but it is generally very fast. However, if you really need to kill everything, you might also look at suspending the account, but that is a billing action. For security containment, the quarantine OU is the professional answer.
What about resource sharing? We have RAM, Resource Access Manager. How does that fit into organizations?
RAM is the friendly neighbor of organizations. It allows you to share subnets, transit gateways, and license configurations across accounts. Before RAM, we had to use complex VPC peering or VPNs. Now, with RAM enabled in your organization, you can share a subnet from a central network account to an app account. The app account can deploy EC2 instances into that shared subnet. They see the subnet as if it were their own, but the network team maintains control over the routing tables and ACLs.
This is the shared VPC pattern.
Exactly. It decouples the application layer from the network layer. Developers control the instances. Network engineers control the pipes. It is cleaner, safer, and heavily tested on the SAP-C02.
Let's do a quick rapid fire on limits. How deep can the nesting of OUs go?
5 levels deep. Root dash, OU dash, OU dash, OU dash, OU dash OU. If you are going deeper than 5, your architecture is too complex. Flatten it.
And how many SCPs can you attach to a single OU?
You can attach multiple policies, but there is a size limit on the policy document itself. It used to be very small, but it has increased. However, the best practice is modularity. Have one SCP for region restrictions, one for service restrictions, and one for tagging enforcement. Don't try to write one giant monolithic JSON file.
Before we wrap up, I want to clarify the service-linked role concept with organizations.
When you create an organization, AWS creates a service-linked role, SLR, in every member account. This role allows the management account to perform tasks inside the member account. Do not delete this role. If you do, the organization breaks.
And finally, leaving an organization. Can a member account just leave?
Not if it was created by the organization. If you created the account via Control Tower or the API, it lacks a payment method. It cannot stand alone. To leave, it must undergo a process to add a valid credit card and sign the user agreement independently. You cannot just detach it and have it float in the void.
Excellent. Let's summarize the top 3 takeaways for the listener's mental cheat sheet.
1. SCPs are filters, not keys. They restrict permissions, they never grant them. If the IAM policy allows it, but the SCP denies it, the answer is deny.
2. Structure your OUs by security posture, not just by department. Production, non-production, sandbox, and forensics. This allows you to map SCPs to the risk level of the environment.
And 3. Use Control Tower to automate the baseline. Don't build the landing zone by hand unless you have a very specific, exotic requirement. Let AWS do the heavy lifting on the logging and audit structure so you can focus on the application architecture.
This has been a deep dive into multi-account governance for the AWS SAP-C02. You have been listening to High Yield Audio Labs.
In our next session, we will be tearing apart transit gateways and advanced networking. Until then, keep your boundaries hard and your permissions least privileged.
Good night.
I remember a specific disaster recovery audit for a global financial institution about 3 years ago. They had invested millions in 2 dedicated 10 gigabit direct connect circuits at 2 different provider locations. They were convinced they had a bulletproof failover strategy. But when we simulated a primary link failure, the entire production environment went dark for nearly 45 minutes.
That sounds like a classic case of the routing table not behaving the way the architects envisioned. I see this often in audits. On paper, the redundancy exists, but the logic to trigger that redundancy is either missing or misconfigured. Welcome to High Yield Audio Labs. Tonight, we are deconstructing the AWS Solutions Architect Professional SAP-C02 domain of hybrid connectivity. Alex, what was the technical root cause of that specific 45-minute blackout?
It was a failure to understand the BGP priority ladder in a hybrid environment. They were using a mix of static routes for their backup site-to-site VPN and dynamic BGP for the direct connect. When the direct connect went down, the BGP session didn't terminate immediately because they hadn't enabled bidirectional forwarding detection, or BFD. Even worse, once the session finally timed out, the static routes they had manually entered in the VPC route tables didn't account for the longest prefix match rule. A shorter, more specific prefix was still being advertised from a different part of the network, creating a massive black hole for their traffic.
This is exactly why the SAP-C02 exam focuses so heavily on the nuances of direct connect, transit gateway, and BGP metrics. For someone sitting the exam tomorrow, they need to understand that AWS follows a very strict hierarchy when deciding how to route traffic back to your on-premises data center. If you have multiple paths, AWS looks at the longest prefix match first. If those are equal, it looks at the routing source. For hybrid setups, the order is usually direct connect first, then the site-to-site VPN. But within BGP itself, there is a lot of room for error.
Let us start with the foundation of direct connect. When you are designing for a professional-level scenario, you are rarely talking about a single connection. You are looking at hosted versus dedicated connections. A dedicated connection is your own physical fiber port at the AWS Direct Connect location, offering 1, 10, or 100 gigabits per second. A hosted connection is what you get through a partner, and these can range from 50 megabits up to 10 gigabits. The exam will often test your ability to choose between these based on the requirement for sub-second failover or specific MASEC encryption needs.
And remember that MASEC, which provides layer 2 encryption at the physical link level, is only available on dedicated connections of 10 gigabits or 100 gigabits at certain locations. If the scenario demands high-speed encryption between your data center and AWS without the overhead of an IPsec VPN, MASEC on a dedicated direct connect is the surgical answer. But Alex, let us talk about the connective tissue between the physical link and the VPC. The virtual interfaces, or VFs.
This is where most candidates get tripped up. You have three types: the private VIF, the public VIF, and the transit VIF. A private VIF connects you to a single virtual private gateway or a direct connect gateway to reach your VPCs. A public VIF allows you to reach public AWS endpoints, like S3 buckets or DynamoDB, using the direct connect instead of the public internet. But the gold standard for the modern enterprise is the transit VIF.
Right, because the transit VF is the only one that can connect to a transit gateway. If the exam question mentions a hub-and-spoke architecture with hundreds of VPCs and multiple direct connect locations, you are almost certainly looking for a transit gateway paired with a direct connect gateway and a transit VF. You cannot connect a private VF to a transit gateway. That is a hard rule.
Let us visualize the architecture for a moment. You have your on-premises router. You have your direct connect circuit. You create a transit VIF on that circuit. That transit VIF terminates on a direct connect gateway. That direct connect gateway is then associated with your transit gateway. This allows a single direct connect connection to reach any VPC connected to that transit gateway across any AWS region, excluding China. This is a massive simplification of the older, more fragmented models.
But that simplicity introduces a single point of failure if you do not design for resiliency. AWS defines 3 levels of resiliency for Direct Connect: maximum resiliency, high resiliency, and the basic configuration. For the SAP-C02, you should always assume the client wants maximum resiliency unless cost is the only factor. Maximum resiliency means 2 separate direct connect locations with 2 separate circuits in each location, terminating on 4 different routers on the customer side.
And the routing must be dynamic. This brings us to BGP, the Border Gateway Protocol. AWS uses BGP to exchange routing information with your data center. To influence how traffic enters AWS from your network, you use the local preference attribute on your own routers. But to influence how traffic leaves AWS and enters your data center, you have to use AS path prepending or multi-exit discriminators, also known as MED.
This is a high-yield point. If you have 2 direct connect links and you want one to be the primary, you prepend your autonomous system number multiple times to the AS path of the backup link when advertising it to AWS. AWS will see a longer path for the backup link and prefer the shorter path of the primary link. If the AS path links are the same, AWS then looks at the MED value. A lower MED is preferred over a higher MED.
There is a catch, though. If you are using a direct connect gateway, the way it evaluates routes is very specific. When traffic is going from AWS to your data center, the Direct Connect gateway will prefer the path with the shortest AS path, regardless of which Direct Connect location it is coming from. If the ASPATHS are equal, it then looks at a specific internal AWS metric that favors the connection that has been active the longest. This is often an overlooked detail that can lead to asymmetric routing.
Asymmetric routing is a nightmare for stateful firewalls. If your traffic leaves via Direct Connect but tries to return via Direct Connect B, a stateful firewall at your perimeter will drop the packet because it never saw the initiation of that connection. This is why we emphasize symmetrical pathing using consistent BGP community tags or careful AS path prepending.
Let us pivot to the failover scenario involving a site-to-site VPN. Many enterprise architectures use Direct Connect as the primary path and an IPsec VPN over the public internet as the cost-effective backup. To make this work, you must advertise the same prefixes over both the Direct Connect and the VPN. Because AWS inherently prefers Direct Connect over VPN for the same prefix, The failover should be automatic.
But automatic is a dangerous word in a professional exam. To make it truly resilient, you need to ensure the VPC route table is configured correctly. If you are using a virtual private gateway, you enable route propagation. This allows the VPG to automatically inject the BGP routes from both the Direct Connect and the VPN into your VPC's route table. If the Direct Connect fails, the BGP session drops, the route is removed, and the VPN route, which is already there with a lower priority, takes over.
However, if you are using a transit gateway, the logic shifts slightly. You have transit gateway route tables. You have associations and propagations. An association means the VPC is attached to a specific route table. Propagation means the transit gateway learns the routes from an attachment and places them in a route table. For a hybrid setup, your Direct Connect gateway attachment and your VPN attachment should both propagate their routes into the transit gateway's main route table.
This is where we see the VPN over Direct Connect requirement. Some security-conscious organizations, like the ones I audit, aren't satisfied with the physical security of a Direct Connect alone. They want the data to be encrypted in transit using IPsec, but they still want the consistent performance of a dedicated circuit. In this case, you create a public VF on your Direct Connect. You then establish a site-to-site VPN, but instead of pointing the VPN at a public internet IP address, you point it at the public IP address of your Direct Connect's public VF.
It is a clever design, but it adds layers of complexity. You are running an IPsec tunnel inside a Direct Connect circuit. You need to account for the MTU, the maximum transmission unit. A standard Ethernet frame is 1500 bytes. IPsec adds overhead, which can lead to fragmentation if you don't adjust your MSS, the maximum segment size. On high-yield audio labs, we often see this cause performance degradation that looks like a slow circuit, but is actually just a fragmentation issue at the tunnel interface.
Let us talk about the trap questions regarding Transit Gateway and Direct Connect. A common one involves the Transit Virtual Interface limit. You can only have one Transit VF per Direct Connect connection. If you have a massive organization with 50 different transit gateways and different accounts, you cannot connect them all directly to one Direct Connect. You must use a Direct Connect gateway. One Direct Connect gateway can be associated with up to 3 transit gateways. This is a hard limit you need to memorize.
And those transit gateways can be in different accounts, but the Direct Connect gateway itself must be owned by one of those accounts. This is where AWS Resource Access Manager, or RAM, comes into play. You share the transit gateway with the account that owns the Direct Connect gateway, and then you perform the association. It sounds like a lot of administrative overhead, but it is the only way to scale a global backbone.
What about the scenario where a company wants to migrate from a legacy virtual private gateway setup to a transit gateway setup without downtime? That is a very common SAP-C02 scenario.
It is delicate. You cannot simply flip a switch. The recommended approach is to create the transit gateway and the new transit VIF alongside the existing private VIF. You then use BGP-AS path prepending to make the new transit gateway path less attractive initially. You verify connectivity. Then you gradually shift traffic by removing the prepending from the transit gateway path and adding it to the old private VIF path. Once the traffic has migrated, you decommission the private VIF.
We should also touch on the concept of Cloud WN versus Transit Gateway. While Transit Gateway is excellent for regional hubs, AWS Cloud WN is designed for global automated routing. If the exam question describes a globally dispersed enterprise that needs to define its network using a central policy document rather than managing individual route tables in every region, Cloud WN is the intended answer. It still uses the same underlying Direct Connect infrastructure, but the orchestration layer is much more abstract.
Let us get into some myth versus fact for the listeners. Myth: Direct Connect is inherently encrypted. Fact: it is not. It is a private circuit, but the data is sent in the clear unless you use MASEC on a dedicated connection or an IPsec VPN over a private or public VF.
Myth: you need a public VF to reach S3. Fact: while a public VF is one way, the more common enterprise approach today is to use an interface VPC endpoint for S3. This allows your on-premises servers to reach S3 via the private VF and the transit gateway, staying entirely on the private AWS backbone without needing a public VF or complex BGP configurations for public IP prefixes.
Another one. Myth: a direct connect failover to VPN is always instantaneous. Fact: without bidirectional forwarding detection, or BFD, the BGP hold-down timer can keep a ghost route in your table for up to 90 seconds after a physical link failure. In a high-frequency trading or real-time application environment, 90 seconds is an eternity. You must explicitly enable BFD on both your on-premises router and the AWS Direct Connect configuration to get sub-second or low-second failover.
Speaking of BFD, there is a specific configuration requirement. AWS sets the BFD liveness detection interval to 300 milliseconds and the multiplier to 3. This means if 3 consecutive heartbeats are missed, the session is torn down. Your on-premises equipment must be able to handle that frequency. Some older hardware can't, and you'll end up with flapping links.
I want to talk about a specific war story regarding BGP community tags. I was working with a client who had a primary site in New York and a secondary site in London. They wanted their New York VPCs to prefer the New York Direct Connect and their London VPCs to prefer the London Direct Connect. But if one failed, they wanted the other to take over.
That is the classic regional preference problem. How did they solve it?
They used BGP community tags. AWS provides predefined community tags that allow you to control the scope of your route advertisements. For example, you can use a tag to tell AWS to only advertise your on-premises prefix within the local region or across the entire continent or globally. By tagging their New York routes as local region only for their primary traffic and global with a prepended AS path for their backup traffic, they were able to create a highly granular, automated failover system that didn't require manual intervention during a crisis.
That is the level of sophistication AWS expects from a professional architect. It is not just about making the connection, it is about controlling the flow of data with surgical precision. For the exam, if you see a question about optimizing cost and performance for a multi-region deployment, look for the answer that combines Direct Connect Gateway for the global reach and BGP community tags for the regional traffic engineering.
We have covered a lot of ground, from the physical dedicated and hosted connections to the logical private, public, and transit VIFs. We have dissected the role of the Direct Connect Gateway and the Transit Gateway as the central nervous system of a hybrid cloud. And we have hammered home the importance of BGP metrics like AS path and MED for controlling the path of your data.
The mental model I want the listeners to take away is a 3-layer stack. Layer 1 is the physical, direct connect locations and circuits. Layer 2 is the logical, direct connect gateways and transit gateways. Layer 3 is the protocol, BGP, and its various attributes. If you can identify which layer a problem exists in, the solution becomes obvious. A failover that is too slow is a Layer 3 BGP timer problem. A VPC that cannot reach a data center is a Layer 2 routing table or VF type problem. A lack of encryption is a Layer 1 MASEC or Layer 3 VPN problem.
That is a perfect summary. When you are in that exam room, or when you are sitting in a data center at 2 in the morning, remember that AWS is just a series of deterministic rules. It doesn't matter how complex the architecture looks. It always follows the longest prefix match, then the specific route source priority, then the BGP attributes.
One final thought for our High Yield Audio Labs listeners. Do not ignore the Direct Connect site link feature. If you have two different direct connect locations and you want to use the AWS backbone to connect your two data centers directly, bypassing the VPCs entirely, SiteLink is the feature. It turns the AWS network into your own private global WN. It is a frequent distractor or correct answer in scenarios involving data center to data center connectivity.
Everything we have discussed tonight is designed to move you from a state of uncertainty to a state of clinical expertise. Hybrid connectivity is the backbone of the enterprise. Master it, and you master the exam.
This has been a deep dive into AWS hybrid connectivity architecture. On behalf of High Yield Audio Labs, we hope this session serves as a powerful weapon in your study arsenal. Stay precise, stay analytical, and we will see you in the next session.
Keep the signals clear and the noise low. Good night. Most architects think they understand the virtual private cloud until they have to scale it across 500 accounts with overlapping IP ranges and a strict mandate for zero public internet exposure. The complexity is not in the creation, Maya, it is in the connectivity. We are seeing a massive shift away from the traditional wide-open peering models toward a more surgical, service-oriented architecture. Welcome back to High Yield Audio Labs. Tonight, we are dissecting the advanced virtual private cloud and PrivateLink patterns specifically for the SAP-C02 Professional Architect exam.
It is a critical shift, Alex. When I am auditing these enterprise environments, the first thing I look for is sprawl. Peering was the gold standard for years, but it is a blunt instrument. It requires unique classless inter-domain routing blocks across every connected segment, which is a luxury many legacy-heavy organizations simply do not have. On the exam, they will often present you with a scenario where two companies merge, or a third-party vendor needs access, and their IP spaces are identical. Peering is dead on arrival there.
Exactly, and that is where we have to start. Let us look at the fundamental limits of virtual private cloud peering. You have the 125 active peering connections limit per virtual private cloud, though you can request an increase, but the real killer is the non-transitive nature. If A is peered to B and B is peered to C, A cannot talk to C through B. You end up with this massive, unmanageable mesh. From a security standpoint, you are also exposing the entire CIDR block unless you are incredibly disciplined with your security groups and network access control lists.
Which most teams are not. That leads us directly into shared VPC. This is a subtle but powerful distinction for the exam. In a shared virtual private cloud environment, we are using AWS Resource Access Manager to share specific subnets from a central host account out to participant accounts. Alex, from your perspective in security architecture, why is this the preferred pattern for centralized governance?
It is about the separation of duties. The central networking team owns the host account. They manage the virtual private cloud itself, the subnets, the route tables, the internet gateways, and the transit gateway attachments. The developers in the participant accounts own their resources, their elastic compute cloud instances, their relational database service clusters, and their own security groups. But they are restricted to the networking sandbox defined by the host. This prevents IP fragmentation. Instead of every account having a small /24, you have a massive shared pool. But there is a trap for the exam. Participant accounts can see each other's resources if they are in the same shared subnets, but they cannot modify or even see the security groups of other participants. They can only reference them by the security group ID if the architect has permitted it.
And we must remember that certain resources cannot be shared. You cannot share an Amazon Aurora cluster or a dedicated host in this way. The sharing happens at the subnet level. Now let us pivot to the scalpel of AWS networking, PrivateLink. If peering is a bridge, PrivateLink is a dedicated tunnel directly into a specific service.
PrivateLink is built on the hyperplane. This is the same high-performance internal distributed state engine that powers the network load balancer and NAT gateway. When you create a private link, or an interface endpoint as the exam calls it. You are placing an elastic network interface directly into your subnet. This interface is given a private IP from your own range. To the consumer, that service, whether it is an AWS service like Key Management Service or a custom application in another account, looks like a local resource.
This is the solution to the overlapping CIDR problem we mentioned earlier. Because PrivateLink operates at Layer 4, mapping a consumer's private IP to the provider's network load balancer, the actual IP addresses of the provider do not matter to the consumer. For the SAP-C02, you must know the requirements for the provider side. You need a network load balancer. You cannot use an application load balancer directly as the provider for a PrivateLink service. You put the network load balancer in front of your instances or containers, create a VPC endpoint service, and then the consumer creates an interface endpoint to connect to it.
And let us talk about the handshake. It is not automatic. The provider must whitelist the consumer's account principal. Once the consumer requests the connection, the provider has to accept it. This creates a clear boundary of consent. I once worked with a SaaS provider who was trying to use peering to connect to their clients. It was a nightmare of routing tables and security reviews. We flipped them to PrivateLink, and suddenly, they could scale to thousands of customers without ever worrying about their customers' internal network layouts. It also inherently limits the attack surface. PrivateLink is unidirectional. The consumer can initiate a connection to the provider, but the provider cannot initiate a connection back into the consumer's virtual private cloud.
That is a massive security win. But we have to be careful about DNS. This is a common exam friction point. When you enable private DNS for an interface endpoint, AWS creates a private hosted zone in Route 53 that overrides the standard service URL. So, if you are calling logs.test.amazon.aws.com, it resolves to the private IP of your endpoint instead of the public internet. If you are doing this across multiple accounts, you need to ensure your Route 53 resolver rules are correctly configured, or you might find yourself still routing traffic out the NT gateway without realizing it.
Which brings up cost. This is high-yield audio labs, and we have to talk about the bottom line because the professional exam loves to test your ability to optimize spend. Peering is free for the connection itself, and you only pay the standard data transfer rates, usually 1 cent per gigabyte for interavailability zone traffic. PrivateLink is expensive. You pay an hourly fee for the endpoint itself, plus a data processing charge per gigabyte. If you are moving petabytes of data between your own VPCs in the same region, and you have unique IP spaces, peering or transit gateway might be significantly cheaper. PrivateLink is for security, for overlapping IPs, and for third-party service consumption.
Let us double back to the gateway endpoints. These are the exceptions to the interface endpoint rule. Currently, only S3 and DynamoDB support gateway endpoints. These do not use ENIs. Instead, they use a prefix list in your route table. Alex, why would an architect choose an interface endpoint for S3 over the traditional gateway endpoint?
Usually, it is about on-premises access. Gateway endpoints are not reachable via Direct Connect or site-to-site VPN. If you have a server in your local data center that needs to upload to S3 without going over the public internet, you have 2 choices: a proxy server in your virtual private cloud or an interface endpoint for S3. The interface endpoint is the modern, serverless way to solve that. It gives you a private IP that your on-premise router can reach over the VPN or Direct Connect. But remember, the interface endpoint for S3 still carries those data processing charges, whereas the gateway endpoint is free. For the exam, if the traffic is staying within the VPC, use the gateway endpoint every time. If it is coming from on-prem or from another region, interface endpoint is your answer.
Let us look at a what would you do scenario. Imagine a massive enterprise with a centralized shared services VPC. They have a suite of security tools, firewalls, deep packet inspection, and logging agents that every other account in the organization must use. The requirement is to ensure that no traffic from the spoke accounts can ever reach the internet directly, and all traffic must pass through the security suite. However, the spoke accounts are managed by different business units and have overlapping IP ranges.
This is the classic PrivateLink design pattern. You would host your security tools behind a network load balancer in the shared services virtual private cloud. You create a VPC endpoint service. In each spoke account, you create an interface endpoint. Now, even if the spoke accounts have identical /16 CIDRs, they can all communicate with the central security hub because the traffic is being handled by the PrivateLink ENI in their own local subnet. To take it a step further for the exam, if you need to inspect that traffic, you would use Gateway Load Balancer, which also leverages PrivateLink technology, specifically Gateway Load Balancer endpoints, to transparently intercept traffic and route it to your firewall fleet.
And we cannot ignore the audit trail. Endpoint policies are a vital piece of this puzzle. An interface endpoint or a gateway endpoint can have a JSON policy attached to it. This is separate from your IAM identities. It acts as a perimeter guard. You can write a policy that says this endpoint only allows access to a specific S3 bucket, or this endpoint only allows actions from a specific IAM role. Even if a user has administrator access, if the endpoint policy denies the action, the traffic is blocked at the network layer.
That is a critical point for the least privileged questions on the SAP-C02. You might see a question where a company wants to prevent employees from uploading data to their personal S3 buckets from company servers. You don't just change the IAM roles. You apply an S3 endpoint policy that restricts access to only the corporate bucket ARNs. It is a foolproof way to prevent data exfiltration.
Let us talk about the architectural limitations of PrivateLink. It supports TCP traffic almost exclusively. If you have a service that relies on UDP, like some voice over IP or streaming protocols, standard PrivateLink won't work. However, the network load balancer now supports UDP, and you can use PrivateLink for UDP as well, but it is a relatively recent addition that you should keep in mind if a legacy question suggests otherwise. Also, PrivateLink does not support fragmented packets. If your application sends large packets that get fragmented at the IP layer, PrivateLink will drop them.
Another common exam trap involves the maximum transmission unit. Inside a VPC, you get the jumbo frame support of 9,100 bytes. But once you start crossing into different connectivity models, that can change. PrivateLink handles the MTU gracefully, but it is always something to keep in mind when troubleshooting performance issues in these surgical environments.
Alex, what about the service quotas for PrivateLink? When we are designing for a massive enterprise, we have to think about the limits of the network load balancer and the number of connections.
The limits are high, but the real bottleneck is usually the IP addresses in your subnet. Each interface endpoint consumes one IP per availability zone it is deployed in. If you are doing this across hundreds of VPCs, you need to ensure your management subnets are sized correctly. But honestly, the biggest fail I see in real-world scenarios is people forgetting about cross-zone load balancing on the network load balancer. If your provider instances are only in Zone A, but your consumers are in Zone A and B, you need to make sure your NLB is distributing that traffic correctly, or you will see lopsided performance.
Speaking of cross-zone, we should mention that PrivateLink services can be accessed across regions now via inter-region VPC peering. You can pair VPC ANS East 1 to VPC BNS West 2, and then access a PrivateLink endpoint in VPC B from VPC A. This is a common way to centralize a service for a global footprint. For the exam, they might ask you to compare this to just having an endpoint in every region. The trade-off is latency and inter-region data transfer costs versus the complexity of managing multiple endpoints.
And don't forget the transit gateway. Transit gateway and PrivateLink are often presented as either-or in exam questions. but they are complementary. You might use a transit gateway to connect all your internal VPCs for general administrative traffic, but use PrivateLink to provide a specific high-security payment processing service to those same VPCs. The PrivateLink provides that extra layer of isolation and the ability to apply a specific endpoint policy that the transit gateway cannot.
That is the deep focus insight. Transit Gateway is for network connectivity. PrivateLink is for service connectivity. If the question asks about connecting networks, look at Transit Gateway. If it asks about exposing a specific application or service securely, especially to third parties or overlapping IPs, look at PrivateLink.
Let us wrap up with a look at the exam strategy for this domain. When you see a question about VPC connectivity, first check the IP ranges. If they overlap, strike peering from your list of answers immediately. Second, look at the security requirement. If they mention data exfiltration or private access to AWS services, your mind should jump to endpoint policies and PrivateLink. Third, check the cost constraints. If it is a high-volume data transfer between your own accounts with unique IPs, Transit Gateway or peering will likely be the most cost-effective answer.
And always remember the S3 gateway versus interface distinction. It is a classic for a reason. Gateway is free, VPC local, and uses route tables. Interface is paid, supports on-premise access, and uses DNS. That single piece of knowledge usually guarantees you at least 2 correct answers on the SAP-C02.
Networking is the foundation of the entire exam. If you can't get the traffic from point A to point B securely and efficiently, the rest of the architecture doesn't matter. We have covered the shared VPC for governance, peering for simple connectivity, and PrivateLink for surgical, secure service delivery.
This has been a dense session, but that is the requirement for the professional level. You have to move past how it works and into when to use it and what it costs.
Precisely. Study the prefix lists, memorize the endpoint policy syntax, and understand the flow of a PrivateLink handshake. These are the details that separate a candidate from a certified professional. Thank you for joining us on High Yield Audio Labs. We'll be back in the next module to dive into advanced identity and access management patterns.
Good luck with your deep work tonight. Stay clinical, stay focused.
So the auditor flagged it, but the real issue wasn't the finding itself. It was that the compensating control had been silently deprecated 2 patch cycles ago, which is a perfect segue into what we're breaking down tonight on High Yield Audio Labs. Because in the world of the Amazon Web Services Solutions Architect professional exam, silence is rarely golden. We're looking at global domain name system and traffic management. Specifically, how we architect for sub-millisecond decision-making and bulletproof hybrid connectivity.
It's a critical domain, Alex. When you're sitting for the SAP-C02, the examiners aren't just looking for someone who knows how to create a record set. They're testing for the architect who can manage the gravity of global traffic. We need to start with the advanced routing policies because that's where the most sophisticated architectural traps are laid. Most candidates understand latency and geolocation, but geoproximity is where I see people stumble.
Geoproximity is often misunderstood because it feels like geolocation, but it functions more like a fluid boundary. In geolocation routing, you're making binary decisions based on the user's physical location. If you're in France, you go to the Dublin region. Period. But geoproximity allows us to influence that mapping using a bias. If I have a massive compute cluster in Northern Virginia and a smaller, more expensive one in Oregon, I can apply a positive bias to US East 1. This effectively expands the geographic reach of that region, pulling users from the Midwest who might physically be closer to Oregon into the Virginia infrastructure.
And the exam loves to test the how behind that. You can't just flip a switch in the standard console for geoproximity. You have to use the Route 53 traffic flow visual editor. It creates a traffic policy that is then associated with a policy record. Architects need to remember that this isn't just about latency, it's about resource optimization. If one region is at 80% capacity and another is at 20%, you shift the bias to rebalance the global load without waiting for the network latency metrics to change.
That's a surgical approach to traffic. But let's contrast that with multi-value answer routing. I've seen senior engineers try to use multi-value as a replacement for an application load balancer. That's a dangerous mistake. Multi-value is essentially simple routing with a health check pulse. It lets you return up to 8 healthy records for a single name. It provides a level of client-side load balancing and high availability, but it lacks the layer 7 intelligence of an ALB. If you're hit with a question about distributing traffic across multiple IP addresses where you need to ensure the client only receives healthy endpoints, multi-value is your primary weapon.
It's the poor man's load balancer at the DNS level, but with the added benefit of health checks. Speaking of health checks, let's look at the nuance of calculated health checks. For a global architecture, you might have a primary site backed by a complex array of microservices. You don't want to fail over just because one non-critical service is flapping. You can create a parent health check that monitors multiple child checks using or, and logic, or even 5 out of 10 logic. It adds a layer of dampening to prevent unnecessary global DNS propagation events.
Propagation is the enemy of uptime. I remember a migration for a global fintech firm where they had a 30-minute time to live on their primary records. They suffered an outage in their primary data center, and even though they updated the records in Route 53 instantly, the world was still hitting a dead IP for half an hour. That's a war story that should be burned into every architect's mind. For the exam, if you're designing a disaster recovery strategy, you must address the time to live. Lower it to 60 or 300 seconds well before the cutover or as part of a high availability design.
That brings us to the hybrid problem. Most enterprise environments aren't cloud only. They have legacy data centers, on-premises Active Directory, and maybe even another cloud provider. This is where Route 53 Resolver becomes the hero of the story. Before the Resolver service, we were building custom EC2-based DNS forwarders or unbound clusters. It was a management nightmare. Now, we have inbound and outbound endpoints.
And the distinction is vital. An inbound endpoint is what allows your on-premises servers to resolve names in your VPC. They point their local DNS forwarders to the IP address of the inbound endpoint. Conversely, an outbound endpoint allows your EC2 instances or Lambda functions to resolve internal.corporate.local. You create a resolver rule that says, if the query ends in .local, send it through the outbound endpoint to the on-premises DNS server.
There's a specific pattern the exam looks for regarding the shared services VPC. Instead of putting endpoints in every single VPC, which is expensive and complex, you centralize them. You put your inbound and outbound endpoints in a hub VPC, and then share the resolver rules across the entire organization using Resource Access Manager. This is the gold standard architecture. It keeps costs down and centralizes the audit trail for all DNS queries.
Let's talk about the security of the DNS itself. DNSSEC. It's been a long time coming for Route 53, but it's finally here, and it's a major part of the SAP-C02 blueprint. It's not about encrypting the DNS query. That's DNS over HTTPS. DNSSEC is about integrity and authenticity. It prevents cache poisoning and man-in-the-middle attacks by cryptographically signing the records.
The implementation is what trips people up. You have the key signing key, or KSK, and the zone signing key, the ZSK. Route 53 simplifies this by integrating with AWS Key Management Service. But remember the chain of trust. You can enable DNSSEC on your hosted zone, but if you don't provide the delegation signer record, the DS record, to your domain registrar, the chain is broken. If the registrar is also Route 53, it's a seamless process. But if your registrar is external, you have a manual step that is a prime candidate for a "which step did the architect forget?" question.
Exactly. And you have to consider the performance impact. DNSSEC increases the size of the DNS responses. While Route 53 handles the heavy lifting, your network infrastructure must support the larger packet sizes. Maya, let's walk through a scenario. Suppose you have a client with a multi-region presence. They're using a primary-secondary failover strategy. They want to ensure that if the primary region goes down, the traffic shifts to the secondary, but they also want to ensure that only the most geographically appropriate secondary is used. How do you layer these policies?
That's where you use nested routing policies. You don't just have one record. You have a hierarchy. At the top level, you might have a failover policy. The primary branch of that failover could then point to a geolocation record. So, under normal operations, you're using geolocation to give everyone the best experience. If that entire primary infrastructure fails the health check, the top-level failover policy kicks in and redirects everyone to a secondary record, which might be a simple weighted record across two other fallback regions.
It's like building a decision tree for traffic, but you have to be careful about the health check logic at the top of that tree. If the top-level record doesn't have a health check, it will never fail over, regardless of what's happening to the child records. The SAP-C02 loves to test your ability to debug a stuck failover. 9 times out of 10, it's a missing health check at the apex of the nested structure or a TTL that's too long for the failover to be effective.
Let's pivot to the difference between Route 53 and AWS Global Accelerator. This is a common point of confusion. Route 53 is a DNS-based solution. It directs you to an IP address, and then the client's browser takes the standard internet path to get there. Global Accelerator, however, provides you with static anycast IP addresses and then onboards that traffic onto the AWS private global network as close to the user as possible.
The distinction is where the steering happens. DNS steering happens at the very beginning of the connection. Once the client has the IP, Route 53 is out of the loop. If the connection drops mid-session, DNS can't help you until the next lookup. Global Accelerator handles the failover much faster, often within 30 seconds, because it's managing the network path itself, not just the name resolution. If a question mentions instant failover or avoiding the public internet for better performance, you should be leaning toward Global Accelerator, even though Route 53 is part of the overall naming strategy.
And remember that Global Accelerator doesn't play well with some legacy systems that expect a dynamic IP. It gives you 2 static IPs that never change. That's a huge win for allow listing in on-premises firewalls. If you have a client who says, "We can't allow list the entire AWS IP range," Global Accelerator is the architect's answer.
Let's go back to the resolver for a second. There is a specific edge case with conditional forwarding and recursive lookups. If you have a private hosted zone in Route 53, say internal.example.com, and your on-premises DNS also thinks it's authoritative for example.com, you're going to have a conflict. The resolver rule must be more specific. The most specific rule always wins. So, if you have a rule for example.com and another for internal.example.com, the internal one takes precedence. This is basic DNS logic, but under the pressure of the exam, it's easy to overlook.
It's also worth noting the limits. You can have up to 10,000 rules per region. But more importantly, each VPC can only be associated with a certain number of rules. If you're an architect for a massive conglomerate with thousands of PCs, you need to be thinking about how to consolidate those rules. Again, Resource Access Manager is the key. You share the rules, you don't recreate them.
And let's not forget the Amazon-provided DNS at the 169.254.169.253 address, or the VPC CIDR +2. That internal resolver is what handles all your VPC to VPC and VPC to Internet lookups. If you disable that, your VPC becomes a dark island. You can't even resolve the S3 endpoint names unless you're using interface endpoints with private DNS enabled. That's another common exam scenario. Instance A can't reach S3 even though the IAM policy is correct. Check the DNS resolution first. If it's a private subnet without a NAT gateway and no S3 interface endpoint, the DNS lookup for s3.us-east-1 AmazonAWS.com will fail because it can't reach the public DNS servers.
That's a classic. And if they're using interface endpoints, make sure Enable DNS Support and Enable DNS Hostnames are both set to true in the VPC settings. If those are false, the private DNS feature for the endpoint won't work, and you'll be left trying to manually point your application to the long, random DNS name provided by the endpoint itself.
Let's talk about DNS auditing. In a highly regulated environment, you can't just let queries go into a black hole. Route 53 resolver query logging is a must-know. You can log every single DNS query that originates in your VPC, who asked for what name, when, and what the response was. You can send those logs to S3, CloudWatch logs, or Kinesis data firehose. For the SAP-C02, if you see a requirement for detecting exfiltration via DNS tunneling or meeting compliance requirements for network activity auditing, query logging is your first line of defense.
It's powerful, but it's also a lot of data. You'd want to use Amazon Athena to query those logs in S3 for any forensic investigation. Imagine a scenario where an instance is suspected of communicating with a command and control server. You go to your resolver logs, query for the timestamp, and you can see the exact DNS request that gave the game away.
We've covered a lot of ground. From the fluid boundaries of geo-proximity bias to the cryptographic integrity of DNSSEC and the complex plumbing of hybrid resolver endpoints. The key for the exam is to always look for the most managed and scalable solution. AWS wants to see that you aren't building custom scripts or managing EC2 instances where a managed service exists.
Exactly. Don't build a DNS server if the resolver can do it. Don't manually update records if a failover policy and health check can automate it. The architect's job is to build a system that heals itself and requires the least amount of human-in-the-loop intervention. That's the mindset that passes the SAP-C02.
It's about building a robust foundation. If your DNS is shaky, nothing else in your stack matters. You can have the most resilient auto-scaling group in the world, but if the users can't find your IP address, your uptime is zero. We've seen this time and again in real-world outages where the hidden infrastructure, the DNS, was the single point of failure.
Which is why we spend so much time on it here. It's the high-yield part of the preparation. You master these nuances, and the rest of the architecture starts to fall into place. You understand how traffic flows, and you understand how the system survives.
Well said. As we wrap up this session, take a moment to visualize the traffic flow in your current projects. Are you using the right routing policy? Is your hybrid DNS centralized or a sprawling mess of forwarders? These are the questions an elite architect asks every day. We'll be back next time to dive into the next layer of the stack. Until then, keep your TTLs low and your health checks rigorous. Thank you for joining us on High Yield Audio Labs.
Good night, and good luck on the journey to professional certification. It's a steep climb, but the view from the top is worth it. See you in the next session.
So the auditor flagged it, but the real issue wasn't the finding itself. It was that the compensating control had been silently deprecated 2 patch cycles ago.
Which is a perfect segue into what we're breaking down tonight on High Yield Audio Labs. We are looking at the architectural backbone of modern enterprise security within the Amazon Web Services ecosystem. Specifically, the evolution from traditional identity and access management to IAM Identity Center and the intricate world of federation.
It is a critical shift, Maya. For the Solutions Architect professional exam, you have to move past the basics of just creating a user in a console. We are talking about the industrialization of identity. When you have 5 accounts, IAM users are a nuisance. When you have 500 accounts and 10,000 engineers, IAM users are a security catastrophic event waiting to happen.
Exactly. And that is why the exam focuses so heavily on centralized identity. Let us start with the core transition. Most candidates understand that IAM Identity Center, which we use to call AWS Single Sign-On, is the recommended way to manage access. But Alex, from an architectural standpoint, what is actually happening when we enable this at the organization level?
At its heart, Identity Center is an abstraction layer. It sits on top of your AWS organization and automates the creation of IAM roles and trust policies across your member accounts. When you define a permission set in the management account or the delegated administrator account, you are essentially creating a template. When you assign that permission set to a user or group for a specific account, Identity Center reaches into that target account, creates an IAM role, usually with a path starting with AWS reserved SSO, and configures the trust relationship to allow the Identity Center service principal to assume it.
That is an important distinction for the exam. The user does not exist in the target account. The role does. And I often see questions that try to trick you on where the source of truth lies. If we're using an external identity provider, say Okta or Azure Active Directory, how does the authentication handshake actually flow before the user even sees the AWS portal?
That is the SAML 2.0 or OpenID Connect dance. Let us walk through the security assertion markup language flow, because that is the enterprise standard you will see most on the SAP-C02. The user hits the AWS Access portal URL. AWS acts as the service provider. It redirects the user's browser to the external identity provider with a SAML authentication request. The user authenticates there, maybe using multi-factor authentication or a hardware key. The identity provider then sends a SAML response back through the user's browser to the AWS assertion consumer service endpoint.
And that response contains the assertions, correct? The claims about who the user is and what groups they belong to.
Precisely. And this is where the metadata exchange becomes vital. You must exchange the XML metadata files between the identity provider and AWS to establish that chain of trust. Without that certificate exchange, the assertion is just noise. AWS validates the signature on the SAML response, and if it matches, it grants the user a sign-in token for the portal.
Let us dig into a common exam scenario. A global company wants to use their existing on-premises Active Directory for AWS access, but they do not want to manage separate credentials. They have a direct connect in place. What are the architectural trade-offs between using an AD connector versus the self-managed SML federation?
That is a classic. If you use AD connector, you are essentially proxying authentication requests back to your on-premises domain controllers. It is a seamless experience for legacy setups, but it requires line of sight to your domain controllers. If that connection drops, nobody signs in. On the other hand, if you use a modern identity provider like Okta or Ping Identity that is already syncing with your Active Directory, you can federate directly with IAM Identity Center using SAML. This is often more resilient because the identity provider is usually a highly available cloud service. For the exam, if the requirement is minimize management overhead and they already have a cloud-based identity provider, that is almost always the right answer.
And we cannot talk about scale without talking about provisioning. I have seen many architects fail to implement SCM, the System for Cross-Domain Identity Management. Why is SCM the secret sauce for large-scale AWS environments?
Because without SCM, you are stuck in manual sync hell. Imagine an employee leaves the company. You disable them in Active Directory. If you do not have SCM, that user might still have an active session or a recognized identity within the AWS Identity Center store until the next manual cleanup. SCIM automates the lifecycle. When you add a user to a group in your external identity provider, SCIM pushes that change to AWS in near real time. It creates the user object in the Identity Center identity store. This is fundamental for the security pillar of the well-architected framework. You want a single point of revocation.
Let us pivot to something more advanced that the SAP-C02 loves to test, attribute-based access control, or ABC. We are moving away from role-based access control, where we have 1,000 different roles for 1,000 different teams. Alex, how does ABC simplify the lives of a senior security architect?
ABAC is about moving the logic from the policy to the principle. In a traditional role-based setup, if I have a new project called Project X, I have to create a new IAM role and a new policy that grants access to Project X resources. With ABAC, I create one generic developer role. I then use the AWS principal tag condition key in my IAM policies. The policy says, allow this user to start or stop an EC2 instance if the instance's project tag matches the user's project tag.
So the permissions are dynamic. If the user moves from Project X to Project Y, I just update their attribute in the identity provider, SCM pushes that tag to AWS, and suddenly they can access Project Y resources without me ever touching an IAM policy.
Exactly. It reduces permission sprawl. But there is a catch for the exam. You have to ensure that the attributes are being passed correctly during the federation process. In SAML, these are passed as attributes. In IAM Identity Center, you have to enable the attributes for access control, feature, and map your identity provider's fields to the tags AWS recognizes. If you see a question about scaling permissions across hundreds of projects with minimal administrative effort, ABAC is your primary candidate.
I want to touch on a war story here. I once audited a firm that was using Federation, but they had a massive security gap because they weren't handling the relay state correctly in their deep links. Users were being dropped into the console homepage instead of the specific dashboard they needed, leading them to poke around in areas they shouldn't have been.
Relay state is often overlooked. It is essentially a parameter in the SAML flow that tells the service provider, AWS, where to send the user after a successful login. From an exam perspective, if you are asked how to provide a seamless, one-click access to a specific AWS console page from an internal corporate portal, the answer usually involves a properly constructed federation URL that includes a relay state parameter.
Let us talk about the blast radius. In a multi-account environment, how do service control policies, or SCPs, interact with IAM Identity Center? If I have a permission set that grants full administrator access, but an SCP at the member account level denies S3 access, what wins?
The deny always wins. This is a fundamental rule of IAM evaluation logic. Even if Identity Center creates a role with full administrative privileges, that role is still subject to the boundaries of the account it resides in. The SCP is the guardrail. It sits above the IAM policy. For the exam, remember that Identity Center manages the allow, but organizations and SCPs manage the can never. If a user has the right permissions in Identity Center, but still gets an access denied error, the first thing I check is the SCP and then the IAM permission boundary.
That is a great point. Permission boundaries are another tool in the arsenal. I have seen questions where you need to delegate the ability to create roles to a developer, but you want to ensure they cannot escalate their own privileges.
Right. You give them the power to create a role, but you require that any role they create must have a specific permission boundary attached. That boundary limits the maximum permissions the new role can ever have. It is a way to maintain least privilege while still enabling builder velocity.
We are halfway through our session on high-yield audio labs, and I want to dive into the technicalities of the trust policy. When we look at a role created by IAM Identity Center, the trust policy looks different than a standard cross-account role. What should we look for?
You will see the principal is not an AWS account ID, but a service principal, usually sso.amazonaws.com. There is also a condition block that validates the organization ID. This is a critical security feature. It ensures that only your specific AWS organization can trigger that role assumption. If you are ever reviewing a trust policy and it is missing that organization ID condition, you have a potential security hole where a principal from a different organization could theoretically attempt to assume that role if other conditions were weak.
Let us talk about session duration. In a high-security environment, we often want to limit how long a federated session lasts. Where is that configured?
You have two places to look. The first is at the identity provider level. How long is the SAML assertion valid? The second, and more relevant for AWS, is the maximum session duration setting on the permission set itself. This can range from 1 hour to 12 hours. For an exam scenario involving highly sensitive data, like a break glass account, you would want to set this to the lowest possible value to minimize the window of opportunity if a session token is hijacked.
And what about the Identity Center directory? Some customers do not want to use an external provider. They want to use the built-in directory. When is that appropriate?
The built-in directory is great for small startups or isolated proof of concepts. It is a managed store within AWS. But for the SAP-C02, the professional answer is almost always to integrate with an existing enterprise identity source. Whether that is an on-premises Active Directory via a two-way trust and AWS managed Microsoft AD, or a cloud provider via SAML and SCM. The exam wants to see that you understand how to integrate AWS into a broader enterprise ecosystem.
Let us look at a trickier protocol, OpenID Connect, or OIDC. We see this more with modern cloud-native applications and GitHub Actions, or GitLab CI/CD pipelines. How does ODC Federation differ from SML when we are talking about machine-to-machine identity?
OIDC is much leaner. It uses JSON Web Tokens, or JWTs, instead of the heavy XML of SCML. When you are federating a GitHub Actions runner with AWS, you don't create an IAM user. You create an IAM OIDC identity provider in your AWS account. You then create a role with a trust policy that allows the GitHub OIDC provider to assume it, but only if this sub or subject claim matches your specific repository and branch. This is the gold standard for secure CI/CD. No more long-lived access keys stored in your repository secrets.
That is a major point for the exam. Eliminate long-lived access keys is a recurring theme. If a question asks how to allow an application running on an on-premises server to access an S3 bucket securely, what are our options?
If the server is on-premises, we should look at AWS IAM roles anywhere. This is a relatively new but very exam-relevant feature. It allows you to use your own public key infrastructure, or PKI, to issue certificates to your on-premises servers. The server uses its certificate to authenticate with the IAM roles anywhere private CA, and in exchange, it gets temporary AWS credentials. It is basically federation for hardware.
I love that. Federation for hardware. It follows the same principle of exchanging a known identity, a certificate, for temporary, short-lived tokens.
Exactly. Now, Maya, let us talk about the delegated administrator for IAM Identity Center. Why should we care about this from an architectural design perspective? Traditionally, you had to manage everything from the organization's management account, but we know the management account should be as empty as possible to reduce risk. By delegating Identity Center to a specific security, or identity account, you follow the principle of separation of duties. The security team can manage permission sets and assignments in their own account without having full administrative access to the entire organization's billing and root level functions.
And for the exam, if they ask how to structure a multi-account environment for a security-conscious organization, mentioning a dedicated identity account with delegated administration is a high-scoring answer.
Absolutely. Let us touch on custom SAML applications. Identity Center isn't just for AWS access. You can use it as a jump point for other SaaS applications like Salesforce, Slack, or your own custom-built internal apps. This allows you to centralize all your single sign-on needs in one place. If a question asks about centralizing access to both AWS and third-party SaaS applications, Identity Center is the answer, acting as the identity provider in this case.
We are nearing the end of our deep dive. I want to challenge you with a complex scenario. A company has two separate AWS organizations due to a recent merger. They want a single sign-on experience for engineers in both organizations using one central Azure Active Directory. How do you architect that?
That is a tough one, but it comes down to the identity provider's capabilities. A single Azure AD tenant can be connected to multiple IAM Identity Center instances in different AWS organizations. You would set up two separate enterprise applications in Azure AD, one for each AWS organization. Each would have its own metadata exchange and SCM provisioning endpoint. The engineers would see two different icons in their Azure portal, one for AWS Orga and one for AWS Org B. It is not a single identity center instance, but it is a single identity source which satisfies the requirement.
And what about cross-account access for third parties? If a security firm needs to audit our account, do we give them an identity center login?
Usually no. For third-party auditors, we prefer the external ID pattern. We have them provide their AWS account ID, and we create a cross-account IAM role in our account. The trust policy allows their account to assume the role, but, and this is the exam-critical part, it must require an external ID string. This prevents the confused deputy problem, where one auditor could potentially use their role to access a different client's account if the role ARNs were guessed.
Great catch. The external ID is a must-know for any professional-level architect.
We have covered a lot of ground today, from the SAML handshake and SCM provisioning to ABAC and roles anywhere. The key takeaway for the SAP-C02 is that identity is the new perimeter. If you control the identity and you audit the who, what, and where using CloudTrail and IAM Access Analyzer, you have one half the battle.
Before we wrap up, let us give our High Yield Audio Labs listeners 3 golden rules for the exam regarding this topic.
Rule 1. Always prefer IAM Identity Center over IAM users for any scenario involving more than one account. Rule 2. If the word scale or thousands of users is mentioned, look for ABAC and SCM. Rule 3. Short-lived credentials always beat long-lived keys, whether that is through OIDC for CI/CD, roles anywhere for on-premises, or standard federation for humans.
That is perfect. I would add a fourth, know your protocol. SML for the enterprise, OIDC for modern apps and web identities.
Well said. This is the kind of technical depth that separates a passing score from a failing one. You have to understand the why behind the XML and the how of the trust relationship.
Thank you, Alex. This has been a surgical breakdown. To our listeners at High Yield Audio Labs, we hope this session has moved you one step closer to that professional certification. Remember, this is not just about passing a test. It is about building secure, resilient architectures that can withstand the real world.
Precisely. The exam is just the validation. The knowledge is the weapon. Until next time, stay clinical, stay curious, and keep the signal-to-noise ratio high.
Good night, everyone. And good luck on your deep work journey. I was reviewing a multi-account architecture yesterday where the team had manually replicated VPC endpoints across 65 different accounts. The latency was acceptable, but the cost for those interface endpoints was staggering. It made me wonder why we still see such massive architectural redundancy in the age of centralized resource sharing.
It usually comes down to a lack of confidence in cross-account governance. Designers are afraid of the blast radius, so they build silos. But as we discussed in this high-yield audio lab session, the AWS Solutions Architect Professional Exam expects you to move past those silos. We are looking at the transition from decentralized sprawl to a hardened shared services model. Specifically, how we leverage the Resource Access Manager, or RAM, and the AWS Service Catalog to create a governed, repeatable environment. When you are sitting for the SAP-C02, you have to realize that AWS is no longer just a collection of accounts. It is a single, programmable entity that needs to be sliced and diced with precision.
That is an important distinction. The exam often presents scenarios where an organization needs to provide a common set of tools, think directory services, private DNS zones, or specialized golden images, without giving every developer account the keys to the kingdom. If we start with the Resource Access Manager, what is the fundamental shift in thinking for an architect who is used to traditional VPC peering or simple cross-account IAM roles?
The shift is from delegation to native sharing. Before Resource Access Manager, if you wanted to share a transit gateway or a specific subnet, you were often looking at complex workarounds. Now, RAM allows you to share resources while maintaining clear ownership. For the SAP-C02, you must understand the distinction between the resource owner and the resource consumer. If I share a subnet from a central network account to a developer account via RAM, the developer can launch EC2 instances into that subnet, but they cannot see or modify the underlying VPC settings. They cannot change the CIDR block. They cannot touch the route tables. They are just tenants in a managed space. This is critical for centralized IP address management. You avoid the overlapping CIDR nightmare because you are managing the entire address space from a single source of truth.
And from an auditing perspective, that is a dream. In my experience, the biggest headache in a large-scale AWS environment is tracking where resources are and who is paying for them. When we talk about RAM and the AWS organization integration, how does that change the handshake process? I know that in a standalone account setup, there is a manual acceptance required for every share.
Exactly. For the exam, always look for whether the organization has enabled sharing with AWS organizations. If that flag is enabled in the RAM console or via the CLI, the handshake is automated. When you share a resource with an entire organization unit, or OU, or even the whole organization, the resources appear in the consumer accounts immediately. No manual acceptance. This is the only way to scale. If you see an exam answer suggesting manual acceptance for 500 accounts, it is almost certainly the wrong distraction. You want the frictionless path. But let's go deeper into what we can actually share. It is not just subnets. We are talking about transit gateways, Route 53 resolver rules, and even license manager configurations.
Let's pick up on Route 53 resolver rules. That is a frequent topic on the professional exam. If we have a shared services PC that handles all on-premises DNS forwarding, how does RAM facilitate that without requiring every spoke account to have its own outbound endpoint?
That is a classic architectural pattern. You create your outbound endpoints in the shared services VPC. You define your forwarding rules, say, for your internal .corp domain, and then you use RAM to share those rules with the entire organization. The spoke accounts then associate those shared rules with their own VPCs. This way, Any DNS query from a developer account for an on-premises resource hits the shared rule, travels across the network to the central outbound endpoint, and resolves correctly. You have centralized your DNS costs and your security logging. You only pay for one pair of endpoints instead of dozens.
And what about the security implications of sharing? As an auditor, I'm always looking for how we prevent a compromised developer account from using a shared resource to pivot into a more sensitive area.
The beauty of RAM is that it respects the original resource's security groups and network access control lists. If you share a subnet, the instances in the consumer account still have to follow the rules defined in the owner account. However, you must be careful with the principals you share with. You can share with specific AWS accounts, OUs, or the entire organization. For the SAP-C02, the most secure answer usually involves sharing with a specific OU to limit the blast radius. If you have a sandbox OU and a production OU, you would never share your production database clusters via RAM with the sandbox. You maintain that logical separation even while using centralized sharing.
Let's pivot to the second half of our objective, the AWS Service Catalog. While RAM handles the sharing of the underlying infrastructure, the Service Catalog is about the sharing of the application patterns themselves. I often describe it as an internal curated marketplace. Alex, why would an enterprise choose Service Catalog over just giving developers access to CloudFormation directly?
It comes down to the launch constraint. This is perhaps the most important technical concept for the exam regarding Service Catalog. In a standard setup, if a developer wants to deploy a complex stack, maybe an auto-scaling group with an RDS instance and specific IAM roles, that developer needs the IAM permissions to create all those resources. That is a lot of power to give to a junior dev. It increases the risk of misconfiguration or intentional misuse. With Service Catalog, the developer only needs permission to use the Service Catalog. You, as the architect, define a launch role. This is an IAM role that the Service Catalog service assumes to deploy the CloudFormation template. The developer doesn't need EC2, run instances, or RDS, create DB instance. They just need the permission to call the Service Catalog provision product.
That solves the principle of least privilege perfectly. The developer can deploy a gold standard web server, but they can't manually spin up a massive P4D instance for crypto mining because they don't have the permissions to do so outside of the catalog. But how do we manage this at scale? We aren't going to manually create the same catalog in every account.
We use the hub-and-spoke model. You define your products and portfolios in a central tooling or shared services account. You then share those portfolios with your other accounts or OUs. When you share a portfolio, the recipient account gets what we call an imported portfolio. They can see the products, but they cannot modify the underlying CloudFormation templates. They can only use them. This ensures that every team is using the exact same version of the architecture, including all the mandatory security headers, logging configurations, and tagging requirements.
Tagging is a great point. I know that the Service Catalog has a specific feature for this, the tag option library. How does that help with financial governance?
Tag options are a game changer for cost allocation. Instead of hoping a developer types department marketing correctly, you provide a predefined list of tags in the Service Catalog. When they provision a product, they have to select from a drop-down. These tags are then automatically applied to every resource created by that CloudFormation template. It makes your AWS Cost Explorer data actually useful. On the exam, if you see a requirement for strictly enforced tagging across multiple accounts, Service Catalog with tag options is your go-to answer.
Let's look at a scenario that might pop up on the SAP-C02. Suppose a global company needs to ensure that any S3 bucket created in any of its 200 accounts is encrypted and has public access blocked. They want a self-service way for devs to get these buckets. Would you use a service catalog or an SCP, a service control policy?
You would use both, but they serve different roles. The service control policy is your guardrail. It is the no. It prevents anyone from creating a public bucket or an unencrypted one. But the SCP doesn't tell the developer how to do it right. The service catalog is the yes. It provides the pre-approved template that is already encrypted and already private. You use the service catalog to enable the business, and you use the SCPs and AWS config to ensure they don't color outside the lines. If the exam asks for a way to provision according to standards, it's service catalog. If it asks to prevent or detect non-compliance, it's SCPs or config.
That is a very clear distinction. I also want to touch on the updates. In a fast-moving environment, our gold standard might change every week. If I update a CloudFormation template in my central service catalog hub, how does that propagate to the Spoke accounts?
When you update the product version in the hub account, the change is reflected in the shared portfolios in the Spoke accounts. However, the existing provision products, the resources already running, won't change automatically. The users in those Spoke accounts will see that a new version is available. They can then choose to update their provision product. This gives them control over their own maintenance windows. For a more automated approach, you could use a combination of AWS CloudFormation stack sets and Service Catalog, which allows you to push updates more aggressively across accounts.
This brings up a point about the shared services VPC itself. We often see the exam ask where to place things like AWS Managed Microsoft AD or a central logging bucket. If we have a central Active Directory in a shared services VPC, we're back to the networking problem. How do we make that AD reachable across the whole organization?
This is where the synergy of these tools comes in. You use RAM to share the directory service itself if you are using the seamless domain join feature, or more commonly, you share the subnets from the shared services VPC. If you have a transit gateway, you share that TGW via RAM with the whole organization. Now, every VPC can attach to that transit gateway. You manage the routing in the central TGW route table to allow traffic to the AD controllers in the shared services VPC. Then, in the service catalog, you provide an EC2 product that includes the user data scripts to automatically join the domain upon launch. You are essentially building a factory where the infrastructure is shared via RAM and the assembly line is managed by Service Catalog.
It's a very sophisticated way to handle it. I've seen some architects struggle with the limitations of Service Catalog sharing. For example, can you share a portfolio with an account that is not in your organization?
You can, but it is a manual process. You have to provide the account ID and the recipient has to accept it. Within an organization, it is much smoother. Another technical detail for the exam: the recipient of a shared portfolio cannot see the products until you, in the Spoke account, associate an IAM user, group, or role with that portfolio. The share just moves the metadata. You still have to define who in the local account has the right to actually click Launch.
That is a common point of failure in real-world setups. People share the portfolio and then wonder why the developers can't see anything. You have to remember that IAM is still the final gatekeeper. Alex, let's talk about a real-world scenario, a war story of sorts. I once worked with a client who tried to use Service Catalog for everything, including their entire production database layer, but they didn't use launch constraints. They just gave the developers the permissions. What went wrong?
They essentially bypassed the whole point of the service. Without a launch constraint, the user is the one creating the resource. In their case, a developer accidentally modified the CloudFormation template locally before running it, because they had the permissions to run CloudFormation directly, and they ended up deploying a database with a public IP. If they had used a launch constraint, the developer would never have been able to touch the template. They would have just been able to pass in a few allowed parameters, like database size or name. It's that layer of abstraction that provides the security. High-yield audio labs is about finding these exact points of failure and engineering them out of your design.
Another thing I see frequently on the exam is the account factory concept. How does Service Catalog fit into the AWS Control Tower environment?
Control Tower actually uses Service Catalog under the hood for its account factory. When you request a new account through Control Tower, it triggers a Service Catalog product. This product uses stack sets to deploy the baseline resources, the VPCs, the IAM roles, the logging, into the new account. This is the ultimate example of standardized architecture. You are not just deploying a server, you are deploying an entire governed environment. For the SAP-C02, if you are asked to design a system for onboarding hundreds of accounts with a standard baseline, Control Tower is the answer, but knowing that Service Catalog is the engine will help you understand how to customize that process.
We've covered a lot of ground on the how and the why. Let's look at some rapid-fire technical constraints that might trip someone up. First, RAM and resource tagging. If I tag a resource in the owner account, do those tags show up in the consumer account?
Generally, no. Tags are local to the account. If you need consistent tagging for cost allocation, you have to tag the resource in the consumer account as well. This is another reason why Service Catalog is so powerful. It can handle that tagging at the moment of creation in the consumer account.
Second, can you share a resource across regions with RAM?
No. RAM is a regional service. If you want to share a transit gateway in US East 1, you have to do it through the RAM console in US East 1. If you have resources in US West 2 that need to be shared, that is a separate set of resource shares. This is a common exam trick. Always check the region.
Third, what happens to the resources in a spoke account if the Service Catalog portfolio share is revoked?
The provision products, the actual running resources, stay running. You aren't going to have a production outage just because a share was revoked. However, the users in that account will no longer be able to update those products or launch new ones from that portfolio. It's a graceful degradation of service, which is a key design principle.
Let's talk about the what would you do scenario. Imagine you are the lead architect for a massive retail company. It's Black Friday. You need to quickly deploy specialized caching layers across 50 different accounts to handle the surge. These layers need to connect back to a central inventory database. How do you use RAM and Service Catalog to survive the day?
First, I would have already shared the central VPC's transit gateway with those 50 accounts via RAM. This ensures they have the low latency path to the inventory database. Then, I would have a cache tier product defined in my central Service Catalog. This product would include the CloudFormation for an Elasticache cluster, pre-configured with the correct VPC settings and security groups to allow traffic only from the web tier and to the inventory database. I would update the portfolio in the hub account with the latest performance-tuned version of this cache product. Then, I'd use a script or a stack set to tell all 50 accounts to launch this product. Within minutes, I have a standardized, secure, and high-performance caching layer across my entire global footprint. No manual configuration, no human error, and I can tear it all down on Saturday morning just as easily.
And because you use Service Catalog, you can track exactly how much that surge capacity cost because of the tag options you enforced.
Exactly. The business loves the agility, and the finance team loves the visibility. That is the hallmark of a senior solutions architect. You aren't just solving a technical problem, you are solving an organizational one.
As we wrap up this module, I think the key takeaway for the SAP-C02 is the integration of these services. Don't look at RAM or Service Catalog in isolation. Look at them as the connective tissue of an AWS organization. RAM handles the where, the shared infrastructure, and Service Catalog handles the what, the shared applications and patterns.
Well said. When you are studying, focus on the specific resources RAM supports. the mechanics of the launch constraint and service catalog, and how both services leverage AWS organizations to automate the handshake and the sharing process. If you can master those three areas, you will be well equipped to handle any governance or multi-account question the exam throws at you.
And remember that the goal is always to reduce friction for the developers while increasing control for the architects. It's a delicate balance, but with these tools, it's entirely achievable.
This has been another technical deep dive from High Yield Audio Labs. Keep your focus clinical, keep your architectures clean, and we will see you in the next module where we tackle Advanced Identity Federation.
Good luck on the journey to professional certification. It's a steep climb, but the view from the top is worth it. I reviewed 3 different study guides this week, and all 3 of them got the shared responsibility boundary wrong for container workloads when discussing Fargate versus EC2 based clusters.
That doesn't surprise me at all, Maya. Most people treat compute selection as a simple price-to-performance calculation, but on the SAP-C02, it is a surgical operation. If you do not understand the underlying hardware abstractions and the precise mechanics of scaling, you are going to leave points on the table. And that is exactly the kind of precision gap we are closing tonight on High Yield Audio Labs. We are looking at the Advanced Compute Selection module, specifically how to architect for massive scale and extreme cost efficiency without sacrificing the resilience that an enterprise architect is expected to deliver.
It is interesting you mention resilience because I was looking at a postmortem from a major retail event last month. They had a massive scale-out event. Their auto-scaling group fired exactly as designed, but the new instances took nearly 7 minutes to pass health checks because of a legacy bootstrap script. By the time the capacity was ready, the latency had already breached their service level agreement and customers were dropping off.
That is a classic architectural failure that the exam loves to probe. When we talk about advanced compute, we have to move beyond just basic dynamic scaling. In that specific scenario, a professional-level architect should have implemented warm pools for Amazon EC2 auto-scaling. A warm pool keeps a set of initialized EC2 instances ready to join the fleet. Instead of starting from a cold state, the instances are already started, the software is preloaded, and they are sitting in a stopped state or a running but hibernated state.
And from a cost perspective, if those instances in the warm pool are stopped, the organization is only paying for the EBS volumes, not the compute cycles. But they can transition to the set-as-service state in a fraction of the time it takes to boot a fresh instance from an Amazon machine image.
Exactly. But let's take it a step further into predictive scaling. Most architects rely on target tracking policies, which are reactive. You wait for the CPU to hit 60%, then you scale. But if your traffic follows a cyclical pattern, say, a morning spike at 9 a.m. every weekday, predictive scaling uses machine learning to look at your historical CloudWatch data. It actually schedules the capacity increase before the spike happens. On the exam, if you see a scenario with predictable, recurring traffic patterns, predictive scaling is almost always the key component of the optimal answer.
I want to challenge you on the Spot instance strategy, Alex. I see many candidates afraid to use Spot for anything other than batch processing. But for a highly available, web-scale architecture, how are we supposed to integrate Spot without risking a total outage when the capacity is reclaimed?
The secret lies in the allocation strategy. Most people think of Spot as take what you can get, but in an auto-scaling group, you want to use the capacity-optimized strategy. Instead of just looking for the lowest price, AWS looks at which instance pools in that availability zone have the deepest spare capacity. This significantly reduces the probability of an interruption. For a professional architect, the move is to use a mixed instances policy. You define a base of on-demand instances to ensure a minimum viable product state, and then you fill the rest of the capacity with a diversified set of Spot instances across multiple instance types, like M5.large, M5D.large, and M4.large.
Right, because if you only pick one instance type and that specific pool is reclaimed, your entire scaled-out fleet disappears. Diversification is the only way to make Spot production grade. I also noticed that the exam is leaning heavily into the Nitro system lately. Why is that hardware-level detail so critical for the professional certification?
Because Nitro changed the math on overhead. In older generations, a portion of the CPU and memory was reserved for the hypervisor to manage networking and storage. With Nitro, that is offloaded to dedicated hardware cards. This allows for nearly 100% of the resources to be allocated to the virtual machine. But more importantly for the exam, Nitro is what enables things like enclaves for highly sensitive data processing and the massive EBS throughput we see in the higher-end instances. If a scenario asks for maximum IOPS with minimum jitter, you are looking for a Nitro-based instance type.
Let's pivot to the specialized silicon. Graviton is no longer just a niche option for hobbyists. We are seeing massive pushes to move enterprise workloads to ARM-based instances.
Graviton 3 is a game-changer for the SAP-C02. We are talking about 25% better compute performance and up to twice the floating point performance compared to Graviton 2. When you see a question focused on cost optimization for a high-performance web tier, Graviton should be your first thought. The price-to-performance ratio is simply better than the x86 counterparts like the M5 or C5 families. The catch, of course, is that the application must be compiled for ARM, but for managed services like RDS, Lambda, or Fargate, that transition is nearly invisible to the architect.
What about the heavy hitters? I am talking about the X2 or the R6G instances. In my audits, I often see these being used incorrectly for workloads that don't actually need that much memory.
Those are for the big iron problems. High-memory instances are almost exclusively for in-memory databases like SAP HANA or massive real-time analytics. The X-family instances can provide terabytes of RAM. If you see a question about migrating a legacy monolithic ERP system that requires 12 terabytes of RAM, you aren't looking at scaling out. You are looking at scaling up to those high-memory metal instances.
And we can't forget about the machine learning side of compute selection. I had a mock scenario recently where the candidate kept trying to use standard G4 DN GPU instances for inference, and the costs were astronomical.
That is a classic trap. For training a model, yes, you want those powerful NVIDIA GPUs in the P4 or G4 families. But for inference, actually running the model once it is trained, AWS Inferentia chips in the INF1 and INF2 instances are designed specifically for that. They provide the lowest cost per inference in the cloud. It's about using the right tool for the right stage of the life cycle. If the exam says inference at scale, you think Inferentia. If it says training complex deep learning models, you think P4D.
It's that level of nuance that separates a passing score from a failing one. You are listening to High Yield Audio Labs, and we are dissecting the advanced compute selection requirements for the AWS Solutions Architect Professional Exam. Alex, let's talk about the actual mechanics of a scale-in event. This is where I see a lot of data corruption issues in real-world environments.
Scale-in is often an afterthought, but it's dangerous. When an auto-scaling group decides to terminate an instance, it just kills it unless you have lifecycle hooks. A lifecycle hook puts the instance into a terminating wait state. This gives you time to run a script. Maybe you need to ship final logs to S3, or gracefully drain active connections, or move a local state file to a persistent store. Only after the script completes does the instance actually terminate.
I often see questions about ensuring that long-running batch jobs are not interrupted by scale-in. Is the answer always to use instance protection?
It's one of the primary tools. You can enable instance protection on specific instances that are currently processing a job. The auto-scaling group will respect that and choose a different instance to terminate during a scaling event. Another strategy is to adjust the termination policy. By default, it tries to balance across availability zones and then picks the oldest launch template or configuration. But you can customize this too. For example, always terminate the newest instance first if that fits your workload better.
Let's talk about the attribute-based instance selection feature. This feels like a shift in how we manage auto-scaling groups. Instead of saying, I want exactly an M5.large, we are telling AWS I want any instance with 2 vCPUs and 8 gigs of RAM.
It is a more cloud-native way to think. By defining the requirements rather than the specific name, your auto-scaling group becomes much more resilient to capacity constraints in a specific region. If there is a shortage of M5.larges, AWS can automatically fulfill the request with an M5D.large or a C5.large that meets those same attributes. For the exam, this is the gold standard for flexible, future-proofed compute fleets.
We should touch on the networking side of these instances. Enhanced networking and the elastic fabric adapter. I've seen students get confused about when to use which.
Think of enhanced networking via the Elastic Network Adapter, or ENA, as the baseline for all modern enterprise workloads. It provides higher I/O performance and lower CPU utilization. But the Elastic Fabric Adapter, the EFA, is specifically for high-performance computing. It allows for OS bypass, which lets the application communicate directly with the network interface hardware. This is for workloads like computational fluid dynamics or weather modeling, where you have massive nodes that need to talk to each other with sub-microsecond latency. If the question doesn't mention HPC or MPI or tightly coupled nodes, the EFA is likely overkill.
That makes sense. What about the instance refresh feature? If I have a fleet of 500 instances and I need to update the AMI to patch a security vulnerability, I can't just terminate them all at once.
Instance refresh automates that rolling update pattern. You update the launch template with the new EMI, and then you trigger the refresh. You define a minimum healthy percentage, say 90%. AWS will terminate 10% of the fleet, launch new ones with the new AMI, wait for them to pass health checks, and then move on to the next 10%. It handles the orchestration that we used to have to write custom Lambda functions for.
One more thing before we wrap up this session. The capacity block for ML. This is a newer feature, but it feels like it could show up as a newest best practice question.
Capacity blocks are interesting. They allow you to reserve high-end GPU instances for a specific time window in the future. If you know you are running a massive training job next Tuesday at midnight, you can guarantee that capacity will be there. It's a departure from the on-demand philosophy, but for the current scarcity of high-end ML compute, it's a necessary tool for the architect's belt.
We've covered a lot of ground, from the ML-driven predictive scaling and warm pools to the cost efficiency of Graviton and Inferentia and the resilience of mixed-instance spot fleets.
The takeaway for the SAP-C02 is that there is no default compute. Every choice must be justified by the requirements of cost, performance, and resilience. If you can justify the why behind the selection, the exam becomes much simpler.
I feel much more confident about the compute selection domain now. It's all about the precision of the requirements.
Precision is exactly what we aim for. This concludes our deep focus on advanced compute selection. Remember to review the Nitro system specifics and the spot allocation strategies, as those are frequent high-value topics. Thank you for joining us for another session of High Yield Audio Labs.
One of the most common pitfalls I see during architecture audits is a fundamental misunderstanding of what high availability actually means when you are dealing with distributed storage systems at scale. People tend to treat Amazon's simple storage service as a simple, infinite bucket, but when you are architecting for the SAP-C02, that level of abstraction will get you failed.
It is a dangerous assumption, Maya. Just last year, I consulted for a financial services firm that lost 4 hours of transaction processing because they assumed standard IA would behave exactly like standard under a burst of retrieval requests. They had not accounted for the retrieval fees or the minimum storage duration. Welcome to High Yield Audio Labs. Tonight, we are stripping away the abstractions and looking at the cold, hard mechanics of high availability storage design for the AWS Certified Solutions Architect professional.
Let us start with S3, because it is the foundation of almost every data lake and backup strategy. Most candidates can recite the 11 nines of durability, but the exam expects you to distinguish between durability and availability across the storage classes. Alex, when a scenario asks for the most cost-effective path for data that is rarely accessed but must be available within milliseconds, where is the trap?
The trap is usually in the one-zone IA versus standard IA decision. Standard infrequent access stores data across a minimum of 3 availability zones. One-zone infrequent access, as the name implies, lives in a single zone. If that availability zone is destroyed, your data is gone. The durability is still technically 11 nines for the objects within that zone, but the resilience to a site-wide disaster is 0. For the exam, if the requirement mentions non-reproducible data or critical backups, you must avoid one zone regardless of the cost savings. However, if they mention secondary copies or regeneratable thumbnails, one-zone IA becomes the surgical choice.
And then we have the complexity of S3 intelligent tiering. I see many architects using this as a set-and-forget solution, but there are nuances to the pricing model that can actually increase your bill if you are not careful with object sizes.
Precisely. Intelligent tiering is brilliant for data with unpredictable access patterns. But you have to remember the monitoring and automation charge. It is a per object fee. If you have billions of tiny 1 kilobyte files, that automation fee will dwarf any savings you get from the tiering. Also, remember that for the SAP-C02, you need to know that intelligent tiering now includes 5 access tiers. You have frequent, infrequent, and archive instant access, which are all millisecond latency. But the 2 deep archive tiers, archive access and deep archive access, require an opt-in and have retrieval times ranging from minutes to hours. If the exam question says the data must be immediately accessible, you cannot rely on those 2 deep archive tiers.
Let us pivot to replication. Cross-region replication, or CRR, is often the go-to for disaster recovery. But I have seen questions where candidates get tripped up on what actually triggers the replication. It is not just a simple toggle.
Versioning is the prerequisite. You cannot have CRR or SRR, same region replication, without versioning enabled on both the source and destination buckets. And you have to understand the IAM requirements. The source bucket owner must have permission to replicate objects to the destination. If the destination bucket is in a different account, that complicates the policy logic. Another high-yield point for the professional exam is replication time control, or RDC. If the business requirement specifies a strict service-level agreement for replication, say 15 minutes, standard CRR does not guarantee that. You must enable S3 RDC, which provides a 99% replication guarantee within 15 minutes, backed by a service-level agreement.
What about the existing objects? This is a classic gotcha on the professional exam. If I enable CRR on a bucket that already has 5 petabytes of data, what happens to those 5 petabytes?
Nothing happens. CRR only replicates new objects created after the policy is applied. To move those existing 5 petabytes, you would need to use S3 batch operations. If you see a question about a massive legacy migration where replication must be established for historical data, batch operations is your answer, not just a simple CRR toggle.
That is a critical distinction. Now, moving from object storage to file systems, let us talk about Elastic File System, or EFS. In high-availability scenarios, EFS is often chosen for its ability to span multiple availability zones, unlike EBS volumes. But the performance modes, general purpose versus max I/O, and the throughput modes are where people lose points.
EFS performance is all about the metadata. General purpose is the default, and it is what you want for most workloads like web serving or content management because it has the lowest per operation latency. Max I/O is for when you are scaling out to hundreds or thousands of instances, like a massive big data processing cluster. It allows for higher aggregate throughput, but at the cost of slightly higher latency per operation. On the exam, if the focus is low latency, choose general purpose. If it is massive parallel processing, choose max I/O.
And the throughput modes have changed recently. We used to talk mostly about bursting and provisioned, but now elastic throughput is a major player.
Elastic throughput is a game changer for unpredictable workloads. You pay for what you use, and it scales automatically. However, for the SAP-C02, if you have a workload with a known, high baseline, like a database backup that runs every night and needs 300 megabytes per second, provision throughput is usually more cost-effective. You are basically buying the pipe size. Bursting is only viable if your peaks are infrequent and short-lived, as you rely on a credit system based on the size of the file system.
Let us go deeper into the FSX family, specifically FSX for NetApp ONTAP. This has become a huge topic because of how many enterprises are migrating from on-premises data centers. It is much more than just a managed file share.
FSX for NetApp ONTAP is effectively the Swiss Army knife of AWS storage. It supports multi-protocol access, meaning you can hit the same data via NFS, SMB, or SCSI. For the exam, if you see a requirement for multi-protocol support or block storage over a network file system, ONTAP is the answer. But the real high-yield feature is the data efficiency. It supports compression, deduplication, and compaction. If a scenario mentions reducing the footprint of redundant data, ONTAP can often be cheaper than EFS because of these features, even if the raw per gigabyte price looks higher.
I also want to touch on the high availability architecture of FSX. When we talk about multi-AZ deployments for FSX for Windows or ONTAP, how does the failover actually happen? Because it is not instantaneous like S3.
It relies on a standby file server in a second availability zone and a set of floating IP addresses. When the primary fails, the standby takes over and the floating IP is remapped. For the client, it looks like a brief pause in I/O. You need to know that for FSX for Windows, this is handled through Microsoft Distributed File System namespaces to maintain a single path. If the exam asks about maintaining a consistent UNC path during a zone failure, you are looking for FSX for Windows with multi-AZ and DFS namespaces.
We cannot talk about FSX without mentioning Lustre. It is a favorite for high-performance computing, but I often see confusion between Scratch and persistent deployment types.
Lustre is built for speed. If you are doing genomic sequencing or autonomous vehicle training, you use Lustre. Scratch file systems are for temporary storage. They are not highly available. If a server fails, the data is lost. They are meant for short-term bursts, where the data is replicated elsewhere. Persistent file systems, on the other hand, are designed for longer-term workloads. They have highly available file servers and data is replicated within the availability zone. Notice I said within the zone. If the entire zone goes down, Lustre is still vulnerable unless you are backing it up to S3, which is a native integration.
That S3 integration is key. The ability to lazy load data from S3 into FSX for Lustre is a common architecture for cost-optimized high-performance computing. You keep the bulk of your data in cheap S3 and only pull it into the expensive Lustre file system when the compute cluster needs it.
Exactly. And when the processing is done, you write the results back to S3 and delete the Lustre file system. This ephemeral high-performance storage pattern is a classic SAP-C02 solution for cost optimization. It is about only paying for the high-performance tier when the CPU is actually spinning.
Let us look at a specific scenario. Imagine a global media company that needs to share a massive library of video assets across 3 regions, US East 1, EUS 1, and AP Northeast 1. They need low-latency access in each region, and the data must be protected against a regional outage. What is our strategy?
This is where we look at S3 cross-region replication to get the data into all 3 regions. To handle the low-latency access, we could use S3 multi-region access points. This gives us a single global endpoint that uses global accelerator behind the scenes to route the request to the closest bucket. If US East 1 goes offline, the multi-region access point automatically routes traffic to the next closest healthy region. It is the pinnacle of S3 high availability. For the file system side of that house, if they needed shared access for video editing, we might look at FSX for NetApp ONTAP with Global File Cache or NetApp Flex Cache. This allows you to have a primary cache in one region and edges in the others, only pulling the blocks that are actually being edited.
That block-level caching is much more efficient than replicating entire multi-terabyte video files if only a few minutes of footage are being touched. It is all about the data in flight versus data at rest trade-offs.
And you have to consider the locking mechanism. If 2 editors in different regions try to modify the same file, how does the system handle it? EFS does not support file locking across regions. ONTAP with Global File Cache does. That is a very specific, very high-yield distinction for complex enterprise questions.
Let us talk about the storage gateway. I feel like people underestimate how often this appears in the professional exam, especially the volume gateway versus file gateway distinction for hybrid clouds.
The storage gateway is your bridge. If the requirement is minimize on-premises storage footprint while maintaining low latency access to frequently used files, you want the S3 file gateway. It caches the hot data locally and pushes everything else to S3. If the requirement is disaster recovery of on-premises block storage, you want the volume gateway. It takes snapshots of your ISCSI volumes and stores them as EBS snapshots in AWS. If the local hardware fails, you can spin up those snapshots as EBS volumes in EC Cloud 2. It is a classic bridge to the cloud strategy.
And we should mention the S3 file gateway's relationship with high availability. Since it is a virtual appliance running on premises, it is a single point of failure unless you deploy it on a high availability cluster like VMware HA. On the AWS side, the data is safe in S3, but the access to that data from on-premises can be interrupted if the local gateway VM goes down.
That is a great point, Maya. Always look for where the access bottleneck is, not just the data bottleneck. On the SAP-C02, they love to give you a highly durable storage backend, and then a single, non-redundant connection or appliance in front of it. Your job is to spot that single point of failure.
Before we wrap up, let us dive into the transfer family. For high availability SFTP, FTPS, or AS2, how does AWS handle the scaling?
The AWS transfer family is fully managed and scales automatically. It is redundant across multiple availability zones by default. The key for the exam is how it connects to the storage. It can point to S3 or EFS. If you need a globally accessible SFTP server that backed by a distributed file system, you point transfer family at an EFS mount point. This allows multiple users to upload and download files simultaneously with the file locking and consistency of a true file system. rather than the eventual consistency challenges you might face with S3 in very specific, high-concurrency write scenarios.
Actually, we should clarify that. S3 now has strong read-after-write consistency for all applications. That was a big change a couple of years ago.
You are right to correct me. The eventual consistency ghost still haunts many older study guides, but for the SAP-C02, you can assume strong read-after-write consistency. However, S3 still does not support object-level locking in the way a file system supports byte range locking. If two people are editing the same byte range of a large file, the last one to put the object wins. EFS or FSX would handle that at the file system level, which is why they are preferred for active collaborative workloads.
So, if we were to summarize the high availability storage decision matrix for our listeners at High Yield Audio Labs, it would look something like this. 1. For absolute maximum durability and global scale with millisecond access, S3 with multi-region access points. 2. For shared Linux file storage that needs to scale to thousands of instances across a region, EFS with general-purpose mode. 3. For Windows-native workloads or complex on-premises migrations requiring deduplication and multi-protocol access, FSX for NetApp ONTAP. And 4. For extreme performance, sub-millisecond latency, and massive throughput, FSX for Lustre with a persistent deployment.
And always verify the RTO and RPO. If the recovery time objective is near zero, you need active-active replication like S3CRR with RDC. If the recovery point objective allows for some data loss, regular snapshots or S3 standard replication might be enough to save the client money.
This has been a deep session, Alex. The technical density here is what makes the difference between a pass and a retake.
It is about internalizing the why behind the service limits. Once you understand why EFS has a metadata overhead or why S3 intelligent tiering has a monitoring fee, you stop memorizing and start architecting. That is the goal.
Thank you for listening to another session of High Yield Audio Labs. We have covered the foundations of S3, the complexities of EFS, and the enterprise capabilities of the FSX family.
Study hard, stay clinical, and we will see you in the next module. Take these lessons, apply them to your practice labs, and the SAP-C02 will be just another day at the office. Good luck. So the auditor flagged it, but the real issue wasn't the finding itself. It was that the compensating control had been silently deprecated 2 patch cycles ago.
Which is a perfect segue into what we're breaking down tonight on High Yield Audio Labs. We are diving deep into the architecture of global database systems, specifically for those of you preparing for the Amazon Web Services Solutions Architect Professional Exam. This is Module 9 of our series, and we're moving beyond simple backups and multi-availability zone setups into the realm of true multi-region, high-availability data layers.
It's a space where most candidates lose points because they confuse the mechanics of replication with the requirements of the business. When we talk about global databases, we're no longer just solving for a single rack or data center failure. We're solving for geopolitical boundaries, catastrophic regional outages, and the physics of light speed. If your users are in Singapore and your data is in Northern Virginia, you're already fighting a losing battle with latency.
Exactly. And that's why the exam focuses so heavily on things like Aurora Global Database, DynamoDB Global Tables, and Elasticache Global Data Store. They aren't just features, they are architectural choices that dictate your recovery point objective and your recovery time objective. Alex, let's start with Aurora. I've seen so many architects get tripped up by how the replication actually works here. They think it's like standard RDS read replicas, but it's fundamentally different at the storage layer, isn't it?
It is. In a standard Amazon relational database service setup, your read replicas rely on the database engine's binlog or logical replication. That's heavy. It adds overhead to the primary instance. But with Aurora Global Database, We are talking about storage-based replication. The primary cluster's storage layer replicates data directly to the secondary region's storage layers. The database engines aren't even involved in the transport. This is why we can see an RPO, a recovery point objective, of less than 1 second and an RTO, a recovery time objective, of less than 1 minute.
1 minute is an incredible benchmark for a cross-region failover. But I want to dig into the failover process itself. In the exam, they often present a scenario where a region goes dark. Candidates often assume that Aurora will just automatically promote the secondary region to primary. That's a trap, right?
It's a massive trap. As of the current architectural standards, a global failover in Aurora is a manual process, or at least one that must be triggered via an API call. You have to promote the secondary cluster to be its own standalone regional cluster. This involves breaking the replication link. Now, once you do that, it becomes the new writer. But here's the surgical detail. Your application needs to know where that new writer is. If you haven't architected for endpoint management, perhaps using something like Route 53 CNEMES or a global proxy layer, your database might be up, but your app is still talking to a ghost in the old region.
And speaking of talking to the database, we have to mention write forwarding. This was a game changer for global architectures. Before, if you were in a secondary region, you could only read. If you wanted to write, your application had to handle the logic of sending that write back to the primary region. Now, Aurora can handle that transparently.
It can, but the architect needs to understand the cost. Local writes in a secondary region using write forwarding are still physically traveling across the globe to the primary. You aren't bypassing the laws of physics. You're just simplifying the application code. For the exam, if the requirement is low latency writes for global users, Aurora with write forwarding might not be the answer. You might need to look at something multi-active.
Which brings us to DynamoDB global tables. This is where we move from a single writer architecture to a multi-active, multi-region architecture. Every region is a writer. Alex, I remember a case study where a firm thought they could use global tables to avoid all conflicts, but they didn't account for the last writer wins resolution.
That's the clinical reality of distributed systems. DynamoDB uses a last writer wins conflict resolution based on a wall clock timestamp. If two users update the same item at the same time in London and Tokyo, the one with the slightly later timestamp is the winner. The other update is simply overwritten. In the SAP-C02 exam, they will test your ability to recognize when this is acceptable and when it isn't. If you're building a banking ledger, last writer wins is a nightmare. If you're building a social media like Counter or a user profile service, it's usually fine.
And what about the underlying mechanism? For the longest time, global tables required you to enable DynamoDB streams. Now, with the 2019 version, it's much more integrated. But the architect still needs to monitor the replication latency. If my Tokyo region is lagging by 2 seconds and my user in London reads the data they just updated while traveling, they might see stale data. This is that classic eventual consistency trade-off we talk about on high-yield audio labs.
It's all about the CAP theorem: consistency, availability, and partition tolerance. DynamoDB chooses availability and partition tolerance. You get that 5 nines availability SLA, but you pay for it with eventual consistency across regions. One thing people forget about DynamoDB global tables is the IAM and security layer. You need to ensure that your KMS, key management service, keys are managed correctly across those regions. If you're using customer-managed keys, they must be multi-region keys, or you need to handle the encryption mapping manually.
Let's shift gears to the caching layer. Elasticache Global Data Store. It's often the forgotten middle child of global architectures, but for real-time applications, it's the only way to keep the experience snappy.
It's essential for things like session state or real-time leaderboards. The global data store for Redis allows you to have a primary cluster in one region and up to 2 read-only secondary clusters in other regions. Again, we're talking about very low latency replication, usually under 1 second. The beauty here is that if your primary region fails, you can promote a secondary cluster to be the new primary. It provides a very smooth transition for the data that lives in memory.
But here is the exam question. Why use Elasticache Global Data Store instead of just having local caches in each region that talk to a global DynamoDB table?
It comes down to the frequency of access and the cost of the read. If you're hitting the same data millions of times a second, even DynamoDB's single-digit millisecond latency is too slow compared to the microsecond latency of Redis. Also cost. Reading from a local Elasticache is significantly cheaper at scale than constantly querying DynamoDB, even with DAX, the DynamoDB accelerator.
Let's walk through a scenario. A common one on the exam involves a global e-commerce platform. They have a massive surge in traffic during a flash sale. They need to ensure that inventory levels are accurate, but they also need the site to be incredibly fast for users in Europe, North America, and Asia. How do we balance Aurora, DynamoDB, and Elasticache here?
This is where you have to be surgical. Your source of truth for the actual order and payment. That should probably be Aurora. You need the ACID compliance, the atomicity, and consistency. You'd use Aurora Global Database with a primary in the region where the bulk of your operations happen. Now, for the product catalog and user sessions, that's DynamoDB Global Tables and Elasticache. The product catalog doesn't change every second, so eventual consistency is fine. The user session needs to be local to the user to keep the site feeling fast, so Elasticache Global Data Store is perfect.
And what happens when the primary Aurora region fails during that flash sale?
First, the monitoring system, perhaps Route 53 health checks or CloudWatch alarms, triggers an automation. We promote the secondary Aurora cluster. This is the moment of truth. We have to update our application configuration. If we're using AWS Secrets Manager, we can have the application poll for the new database endpoint. The RTO is the time it takes to promote the DB and update the app. The RPO is that sub-second lag that was in flight when the region went down. Some transactions might be lost, which is why your application must be designed to handle retries and idempotency.
Idempotency is such a key word for the professional exam. If the app retries a payment because the database failed over, you better make sure you don't charge the customer twice. That's a common distractor in the multiple choice questions. They'll offer a solution that involves global databases, but ignores the application-level logic needed to handle the failover gracefully.
Exactly. You can't solve a distributed systems problem with just a checkbox in the console. You have to write code that understands the state of the infrastructure. Another thing the exam loves to test is the networking side of this. How does the data actually get from region A to region B? For Aurora and DynamoDB, it stays on the AWS global backbone. It doesn't traverse the public internet. This is a huge security and performance win.
But you still have to deal with VPC peering or transit gateway if your application servers in region B need to talk to the database in region A before a failover happens. For example, if you're using write forwarding, that traffic is traversing the network. You need to make sure your security groups and NACLs, network access control lists, are configured to allow that cross-region traffic.
And don't forget the data transfer costs. Replicating a multi-terabyte database across 3 regions isn't just a technical challenge, it's a budgetary one. You're paying for the storage in all 3 regions, the IOPS in all 3 regions, and the cross-region data transfer. On the exam, if they mention cost-effective as a requirement, you might want to rethink that 3rd region.
That's a great point. The SAP-C02 isn't just about what's possible, it's about what's optimal. Let's talk about the specific gotchas for each service. For Aurora, it's the fact that the secondary cluster must have the same instance class as the primary to handle the load after failover. I've seen people try to save money by having a tiny T3 instance in the secondary region, but when the failover happens, that instance immediately chokes under the production load.
It's a classic mistake. You're essentially building a high-performance engine and then putting a lawnmower transmission in the backup. It won't work. For DynamoDB, the gotcha is often around the capacity mode. If you're using provision capacity, you have to manage it in every region. If you're using on-demand, it scales, but you have to be careful with those sudden bursts. And for Elasticache, it's the fact that it doesn't support all Redis features in a global configuration. You have to check the compatibility matrix.
We've covered a lot of ground. From the storage-level replication of Aurora to the multi-active nature of DynamoDB and the microsecond latency of Elasticache. If you're listening to this to prepare for your exam, remember that the most important thing is to identify the RPO and RTO requirements in the question.
If the question says zero data loss, you are in a tough spot with multi-region. Even Aurora Global has a sub-second RPO. To get true zero data loss cross-region, you need synchronous replication, which AWS doesn't offer out of the box because the latency would destroy your performance. You'd have to build something very custom and very slow. So, in the context of the exam, near zero is the keyword for Aurora.
And if the question says multi-active or local writes in multiple regions, your mind should go straight to DynamoDB global tables. Aurora's write forwarding is a hub and spoke model, not a true multi-active model.
Correct. It's also worth mentioning the monitoring. You need to be familiar with the replication lag metric in CloudWatch for all these services. If that lag starts to spike, your global strategy is failing. You need to know how to set alarms on that metric to alert the engineering team before the lag becomes a business problem.
This is the kind of technical density that makes or breaks a candidate. We're not just talking about clicking buttons. We're talking about understanding the physics of the cloud. I think we've given them a solid foundation for Module 9.
I hope so. These global database architectures are the backbone of the modern enterprise. If you can master these, you're not just passing an exam. You're learning how to build systems that can survive a regional apocalypse.
On that note, we'll start wrapping up this session. Remember to review the official white papers on high availability and disaster recovery with Aurora and the DynamoDB Global Tables Developer Guide. They are dense, but they contain those little nuggets of information that the exam loves to turn into trick questions.
And keep practicing. Build a global table. Trigger a failover in an Aurora global database. See how your application reacts. There is no substitute for the war stories you create yourself in the console.
We'll be back with Module 10, where we'll tackle the complexities of identity federation and single sign-on in a multi-account environment. That's another area where the details are surgical and the stakes are high.
Until then, keep your latency low and your availability high. You're listening to High Yield Audio Labs, and we'll see you in the next deep dive.
Thanks for joining us. Good luck with your studies, and remember, on the exam day, you are the architect. Stay calm, be methodical, and trust your training.
It's like I always tell the juniors, the cloud is just someone else's computer, but when it's global, it's everyone else's computer. You have to treat it with respect.
That's a bit cynical, Alex, but technically accurate. Let's get some coffee.
Only if it's from a region with less than 10 milliseconds of latency.
I'll see what I can do. Good night, everyone.
Good night. The fundamental mistake most architects make when moving to serverless is treating it like a distributed monolith where every function just calls the next one via the software development kit. It looks clean on a diagram, but in production, you have created a synchronous chain where one failure cascades through the entire stack, and you are paying for every millisecond of idle waiting. This is exactly the mindset we are here to dismantle in this session of High Yield Audio Labs. We are looking at the professional level of the Amazon Web Services Solutions Architect exam, specifically focusing on how to design truly decoupled, event-driven architectures that can survive at enterprise scale.
It is interesting you mention the idle waiting, Alex, because that is usually the first indicator of an architectural smell in a serverless environment. When I am auditing these environments, I look for lambdas that are essentially acting as orchestrators. They trigger another lambda and then just sit there waiting for a response. Not only is that a waste of compute cost, but you are also double paying for that time. In the context of the SAP-C02 exam, the solution almost always points toward AWS step functions. But the real trick is knowing exactly which type of workflow to use. Can we start there? The distinction between standard and express workflows is a favorite for exam questions because the trade-offs are so specific.
Exactly. If you see a requirement for a long-running process, something that might take hours, days, or even up to a year, you must go with standard workflows. They offer exactly once execution and provide a full execution history that you can inspect in the console for up to 90 days. This is critical for auditing and compliance. However, if the requirement is high volume, short duration processing, like IoT data ingestion or high-frequency trade processing, express workflows are the tool. They are designed for durations of less than 5 minutes and can handle more than 100,000 executions per second. The catch is they offer at least once execution, which means your downstream logic must be idempotent.
Idempotency is a term that comes up constantly in these professional-level scenarios. For the listeners, that means the operation can be repeated multiple times without changing the result beyond the initial application. On the exam, if you are asked to design an order processing system that uses express workflows, you better ensure your database update logic checks for existing order IDs before processing a payment. Alex, what about the service integrations within step functions? I often see candidates trying to write Lambda functions just to put a message on a simple queue service or update a DynamoDB table.
That is a classic anti-pattern. AWS has been aggressively expanding the direct service integrations for step functions. You can now interact with over 200 services directly from the state machine using the AWS SDK integration. This removes the need for what I call glue lambdas. Every lambda you remove is one less piece of code to maintain, one less security surface to patch, and one less cold start to worry about. For the exam, if a question asks for the most cost-effective and operationally efficient way to move data from an S3 bucket to a DynamoDB table after an event, look for a step function that uses the optimized integration rather than a Lambda function.
And let us talk about error handling within those state machines. This is where step functions really shine compared to custom code. You have the catch and retry fields. In a professional architecture, you do not just retry immediately. You use exponential backoff and jitter. Alex, why is jitter so important when we are dealing with thousands of concurrent executions?
If you have 1,000 lambdas all failing because of a downstream rate limit and they all retry at exactly 1 second, then 2 seconds, then 4 seconds, you have just created your own distributed denial of service attack against your own database. Jitter adds a random element to the wait time, spreading the load and giving the downstream service a chance to recover. In step functions, you simply set the max delay and the backoff rate. It is a configuration change, not a code change. Maya, I know you focus heavily on the auditing side. How do you feel about the transition from orchestration with step functions to choreography with Amazon Event Bridge?
Choreography is where the true power of decoupling lies. In an orchestrated system, the step function is the brain that knows every step. In a choreographed system, each service just emits an event to an event bridge bus and does not care who is listening. From an auditor's perspective, this is a dream for scalability and extensibility. If a new business unit needs to know when a new customer is created, I do not have to modify the original customer service code. I just add a new rule to the event bridge bus that targets the new service. For the SAP-C02, you need to understand the schema registry. It allows you to discover and track the structure of events across your organization. It can even generate code bindings for your developers, so they are always working with the correct event structure.
Event Bridge has really evolved with the introduction of pipes and API destinations. Pipes are particularly important for the exam because they handle the integration between an event source and a target. Think about a simple queue service or a DynamoDB stream. Traditionally, you would need a Lambda to poll that stream, filter the events, and then send them somewhere. Event Bridge Pipes does the polling, the filtering, and the enrichment for you. You can even use a Lambda function within the pipe just for enrichment, transforming the data before it hits the target. This brings us back to our core theme at High Yield Audio Labs, minimizing custom code by leveraging managed features.
Let us dive into a common exam scenario. A company has a global application and needs to route events between different regions. How does Event Bridge handle that?
You can route events from one event bus to another in a different region. However, you have to be careful with the circularity of events. But the more modern approach for global resilience is Event Bridge Global Endpoints. This allows you to provide a single endpoint for your event producers. If a region goes down, Event Bridge can automatically fail over to a secondary region. It uses Route 53 health checks under the hood. For the professional exam, if the requirement is high availability and low recovery time objective for an event-driven system, Global Endpoints is the answer you are looking for.
We should pivot to Lambda specifically, as it is usually the execution engine for these events. I see a lot of confusion around scaling and the different types of concurrency. Specifically, provisioned concurrency and how it interacts with the cold start problem. Alex, can you break down when an architect should justify the cost of provisioned concurrency?
Provisioned concurrency is your weapon against latency spikes. In a standard Lambda execution, the first time a function is called, AWS has to download the code, start the execution environment, and initialize the runtime. This is the cold start. For some Java or .NET applications, this can take several seconds. If you have a real-time API where the service level agreement is sub-second latency, cold starts are unacceptable. Provision concurrency keeps a specified number of execution environments warm and ready. The trade-off is that you pay for them as long as they are provisioned, regardless of whether they are being used. On the exam, look for keywords like predictable latency or strictly defined latency requirements.
There is also the concept of Lambda extensions. This is something that many senior architects overlook. Extensions allow you to run tools alongside your Lambda function code. This is perfect for things like sending logs to a third-party provider, fetching secrets from a vault, or performing security instrumentation. Alex, I have seen some clever uses of extensions for prefetching configuration data. How does that impact the execution lifecycle?
Extensions run in the same execution environment, but in a separate process. There are internal extensions that modify the runtime startup and external extensions that start before the runtime and continue to run after the function has finished. This is vital for observability. If you need to ensure that every single execution log is sent to a monitoring tool before the environment shuts down, an external extension is the way to carry that out. For the exam, remember that extensions share the same memory and CPU resources as your function. If your extension is heavy, it will steal performance from your main logic.
That leads into the resource allocation for Lambda. It is not just about memory. When you increase the memory for a Lambda function, you are linearly increasing the available CPU power and network bandwidth. If you have a CPU-intensive task, like image processing or encryption, sometimes increasing the memory from 128 megabytes to 2 gigabytes actually makes the function run faster and cheaper because the execution time drops so significantly. This is called power tuning.
Let us look at a real-world scenario that might appear on the exam. Imagine a financial institution processing transactions. They use an event bridge bus to receive transaction events. These events must be checked against a fraud detection service, then stored in a database, and finally, a notification must be sent to the user. If any step fails, they need a clear audit trail. Maya, how would you architect this for maximum reliability and auditability?
I would start with Event Bridge to receive the initial transaction. I would use a rule to trigger a step function standard workflow. Why a step function? Because we have multiple steps that depend on each other, and we need to maintain state. The first state is the fraud check. If the fraud check returns a high-risk score, the step function branches to a manual review state. This is where we use the task token pattern. The step function sends a message to an SQSQ for a human to review and then pauses. It waits for a callback with the task token before it continues. Once approved, the next state updates the DynamoDB table using a direct service integration. Finally, we use another direct integration to send a message via the simple notification service. If any of these steps fail, we have a catch block that sends the failed transaction details to a dead letter queue and updates a separate audit log.
That task token pattern is a crucial one for the exam. It is the bridge between automated workflows and manual or long-running external processes. If the exam asks how to integrate a third-party payment processor that might take 5 minutes to respond, you do not want your Lambda function waiting and polling. You want your step function to send the request and wait for the token to be returned via an API call.
Alex, let us talk about the Lambda execution environment reuse. This is a common source of bugs and security vulnerabilities. When a Lambda function finishes, the environment stays warm for a few minutes. If you have global variables or files in the /tmp directory, they will persist for the next execution. From a security standpoint, this is a risk if sensitive data is left behind. But from a performance standpoint, it is an opportunity.
Right. You should always initialize your database clients, your secrets, and your configuration outside of the handler function. This way, they are initialized once during the cold start and reused for all subsequent warm starts. However, you must be careful with database connection pooling. If you have 1,000 Lambdas, each keeping a connection open to a relational database, you will exhaust the connection limit in seconds. This is where Amazon RDS Proxy comes into play. It pools those connections and manages them for you, which is a key requirement for any serverless architecture involving a relational database.
Let us touch on the concept of the Saga pattern in a serverless context. On the professional exam, you might be asked how to manage distributed transactions across multiple microservices without a traditional database lock.
The Saga pattern is the standard solution here. Since we cannot use a single database transaction across multiple services, we use a step function to manage a series of local transactions. Each step has a corresponding compensation step. If the third step in the sequence fails, the step function is responsible for running the compensation steps for the first 2 successful operations to roll back the system to a consistent state. For example, if we successfully reserved a hotel and a flight, but the car rental fails, the step function must trigger the cancellations for the hotel and the flight. This is the only way to maintain eventual consistency in a truly decoupled system.
It is all about managing failure gracefully. On the exam, if you see a question about ensuring consistency in a distributed system, the Saga pattern using step functions should be top of mind. Alex, before we wrap up this session of high-yield audio labs, let's talk about the security of these event-driven systems. Specifically, how do we handle permissions when one service is triggering another through Event Bridge?
It is a two-way street. You have the identity-based policy on the IAM role that the producer uses to put events onto the bus. Then you have the resource-based policy on the Event Bridge bus itself, which defines who is allowed to send events to it. Finally, the Event Bridge service itself needs a role to trigger the target, whether that is a Lambda function or a step function. This is a common point of failure. If your rule is not triggering, Check the resource-based policy on the target. A Lambda function needs a policy that allows events to temazonaws.com to invoke it.
And do not forget about encryption. All events in EventBridge are encrypted at rest using a service-owned key by default, but for high-security environments, you can use a customer-managed key in the key management service. The same applies to Lambda environment variables and step function state data. If the exam mentions regulatory requirements like HIPAA or PCI-DSS, you should always look for the option that uses customer-managed keys for that extra layer of control and auditing.
One last thing for the exam candidates. Pay attention to the limits. EventBridge has limits on the size of the event payload, which is currently 256 kilobytes. If you need to pass a larger payload, you use the claim check pattern. You store the large data in an S3 bucket and just pass the bucket name and key in the event. The downstream consumer then fetches the data from S3. This is a classic architectural pattern that AWS expects a professional architect to know.
That is a great point. The claim check pattern is almost guaranteed to show up if the scenario involves large files or documents. Alex, this has been a dense session. I think we have covered the core pillars: orchestration versus choreography, scaling behaviors, and the patterns that ensure reliability and security.
We have. The key to the SAP-C02 is not just knowing what the services do, but knowing why you would choose one over the other in a given business context. Always prioritize the managed service solution that reduces operational overhead. If you can do it with a step function configuration instead of a Lambda function, that is usually the correct answer.
Exactly. It is about being a lazy but smart architect. Let the platform handle the heavy lifting of state management, retries, and scaling. That's the core philosophy we preach here at High Yield Audio Labs.
Final advice for the exam: read the requirements carefully. If they ask for the most cost-effective solution, your answer might be different than if they ask for the most resilient or the one with the lowest latency. Understanding those trade-offs is what separates a professional architect from an associate. This has been another technical deep dive. Good luck with your studies, and stay focused on the signal, not the noise. This has been a session from High Yield Audio Labs.
Alex, I was looking at a legacy architecture review for a multinational financial services firm recently, and it struck me how often we see teams misconfiguring the very edge of their network because they treat it like a simple content delivery network rather than a programmable security perimeter. Why is it that even senior architects often default to basic caching when the AWS Solution Architect professional exam expects so much more nuance in edge computing?
It is a common blind spot, Maya. They view the edge as a passive layer, but in the SAP-C02 mindset, the edge is where the battle for latency and security is won or lost before a single packet even touches your regional resources. That is exactly the focus of today's High Yield Audio Labs session. We are dissecting the surgical application of Amazon CloudFront and AWS Global Accelerator. We need to move beyond the marketing definitions and look at the actual mechanics of how these services handle state, compute, and protocol optimization. Let us start with a scenario I saw last year. A global e-commerce platform was suffering from a massive credential stuffing attack. Their web application firewall was at the regional level, and by the time the traffic hit the application load balancer, the sheer volume was already degrading the performance of their auto-scaling groups.
That is a classic mistake of waiting too long to make a decision. If you are not filtering at the edge, you are paying for the bandwidth and compute of your attacker. In that situation, I assume you moved the logic to the CloudFront distribution?
Precisely. But we did not just put a WAF on the distribution. We used CloudFront functions for the ultra-lightweight, high-scale header validation. For the listeners preparing for the exam, this is a critical distinction. CloudFront functions and Lambda at edge are not interchangeable. Maya, how would you explain the decision matrix between those two to an auditor who is worried about millisecond latencies?
I tell them to look at the complexity and the trigger point. CloudFront functions are your scalpel for viewer-facing logic. They run in a restricted JavaScript environment, meaning no access to the network or the file system, and they have a sub-millisecond execution time limit. If you are just rewriting a URL, normalizing a header, or performing basic token validation, you use CloudFront functions. They scale to millions of requests per second effortlessly because they are built on a process-based isolation model rather than full virtual machines. But the moment you need to talk to a database like DynamoDB, or if you need to inspect the body of a post request, you must step up to Lambda at Edge.
And that is where the architecture becomes interesting. Lambda at Edge gives you the power of a full Node.js or Python environment. You can access the request body, which is vital for things like A/B testing or real-time image transformation where the logic depends on more than just metadata. But on the exam, they will trip you up on the triggers. You have 4 distinct points: viewer request, origin response, and viewer response. If you are doing something that should affect the cache, like normalizing a cache key, you have to do it at the viewer request level. But if you are doing something that is origin specific, like fetching a secret from Secrets Manager to add an authorization header, you want that at the origin request level so it only executes when the cache is empty.
That origin request trigger is a huge cost optimizer too. There is no point running heavy logic on every single viewer request if you can run it once, cache the result at the edge, and serve the next 1,000 viewers from the cache. However, I want to pivot to the security side of CloudFront. We often talk about Origin Access Identity, or OAI, for securing S3 buckets, but the SAP-C02 is now heavily testing Origin Access Control, or OAC. Alex, why should architects be deprecating OAI in favor of OAC in their designs?
OAC is the mandatory standard now for any modern AWS architecture. OAI was limited. It did not support SSE-KMS, and it only worked for S3. OAC supports all S3 buckets in all regions, including those created after December 2022, and it supports AWS Signature version 4. More importantly, it allows you to sign requests to S3 compatible origins that require KMS encryption. If you see an exam question asking how to provide the most secure, fine-grained access to an S3 origin while supporting encrypted objects, OAC is always the answer. It also provides a stronger security posture by allowing you to restrict the bucket policy to only allow the specific CloudFront service principal.
And speaking of security, we cannot ignore field-level encryption. Most people think of SLTLS as the end-all for data in transit, but in high-compliance environments, you might need to ensure that even the back-end application doesn't see sensitive data in its raw form. CloudFront field-level encryption allows you to specify certain fields in a POST request, like a credit card number, and encrypt them with a public key at the edge before the data is forwarded to the origin. Only the specific microservice with the private key can decrypt it. It is a beautiful way to reduce the scope of your PCI DSS audits.
It really is. It shifts the security boundary all the way to the edge. Now let's talk about the other heavy hitter in this domain: AWS Global Accelerator. I find that many candidates get confused about when to use CloudFront versus Global Accelerator, especially when the goal is performance. Maya, how do you draw that line in a multi-region deployment?
It comes down to the protocol and the nature of the data. CloudFront is an application-level service. It is for HTTP and HTTPS. It is heavily focused on caching. Global Accelerator, on the other hand, operates at the network layer. It provides you with 2 static Anycast IP addresses that are broadcast from the AWS Edge locations. This is a game-changer for non-HTTP protocols like TCP or UDP. If you are running a global VoIP service, a gaming server, or a VPN, CloudFront cannot help you. Global Accelerator uses the AWS Global Network to route your traffic from the edge location closest to the user directly to your application load balancer, or EC2 instance, in any region. It bypasses the jitter and congestion of the public internet.
That point about the static IPs is vital for the exam. Imagine a scenario where a client has a hard-coded IP allow list in their firewall. You cannot give them the IP ranges of CloudFront because they change constantly, but you can give them the two static IPs from Global Accelerator. Also, think about the failover speed. CloudFront relies on DNS TTLs to move traffic between origins, which can take minutes to propagate globally. Global Accelerator performs health checks at the edge and can reroute traffic to a healthy regional endpoint in about 30 seconds. For a professional-level architect, that difference in mean time to recovery is a deciding factor.
I also want to mention the client IP preservation. With CloudFront, the origin sees the CloudFront IP, and you have to rely on the X-forwarded for header to see the user's IP. Global Accelerator, when used with an application load balancer, can preserve the original client IP at the packet level. This is often a requirement for certain security appliances or legacy applications that cannot parse headers.
Let's look at a war story involving a global financial ticker application. They needed sub-second updates for users across 5 continents. Initially, they tried CloudFront, but the overhead of the HTTPS handshake and the lack of support for their custom UDP-based protocol made it unusable. They switched to Global Accelerator, which allowed them to use their custom protocol over the AWS backbone. They used the listener weights to gradually shift traffic between regions during deployments, which gave them a level of control that DNS-based routing like Route 53 just couldn't match.
That is an excellent point. Route 53 is great, but it is a best effort redirection based on the user's DNS resolver location, not the user themselves. Global Accelerator sees the actual entry point of the packet. By the way, for those just joining this high-yield Audio Lab session, we are deep diving into the architectural trade-offs of AWS Edge Services for the SAP-C02 exam. Alex, let's talk about the interaction between these services and AWS Shield Advanced.
Shield Advanced is the silent guardian here. When you attach it to CloudFront or Global Accelerator, you get more than just DDoS protection. You get the response team access and cost protection against scaling charges caused by an attack. But the exam-specific detail is the proactive engagement. If you have Shield Advanced on your edge resources, the AWS DDoS response team will actually reach out to you if they see health checks failing during a suspected attack. This is why we often put CloudFront in front of even dynamic, non-cacheable content. It provides a massive, globally distributed surface area to absorb Layer 7 attacks that would otherwise melt a regional ALB.
And let's not forget the WF integration. A common exam trap is asking how to block specific countries or IP ranges. You can do this at the CloudFront level with geo-blocking or at the WF level. If you need it to be cost-effective and simple, the CloudFront native geo-restriction is fine. But if you need to block a country only for a specific subset of your application, say the admin login page, you need a WF rule associated with that CloudFront distribution.
Exactly. Precision is everything. Let's talk about one of the more complex scenarios, the multi-region, multi-origin setup. Suppose you have an application that must stay online even if an entire AWS region goes dark. You can use CloudFront origin groups to provide automated failover between 2 different origins. If the primary origin returns a 500 or 503 error, CloudFront automatically tries the secondary origin. This is a much more elegant solution for high availability static sites than relying on DNS failover.
It's important to note that origin groups only support 2 origins, a primary and a secondary. If you need more complex failover logic, you might need to use Lambda at Edge to programmatically change the origin based on health data or even a custom database of regional status. This is where the programmable edge concept really shines. You could have a Lambda at Edge function that checks a DynamoDB global table to see which region is currently the leader for a specific customer's data and route the origin request accordingly.
That brings us to the data sovereignty and regulatory side. Sometimes, you are not allowed to cache certain data in certain countries. How do you handle that? You use the Lambda at Edge viewer request trigger to inspect the user's country code, which CloudFront provides in a header, and you can then either block the request or modify the cache policy to set the TTL to 0 for that specific geography. It is about granular control.
I want to touch on the caching of dynamic content. A lot of students think caching is only for images and CSS. But in a high-traffic environment, even caching a JSON API response for 5 or 10 seconds can reduce the load on your database by 90%. Using CloudFront cache policies, you can precisely define which headers, query strings, or cookies should be part of the cache key. The exam will often give you a scenario where a site is slow because it is not caching, and the reason is usually that the cache key includes something unique like a session ID or a timestamp. The fix is always to strip those out of the cache key using a custom cache policy.
And conversely, the origin request policy allows you to pass information to the backend without including it in the cache key. This is a subtle but vital distinction. You might need the user's user agent for logging at the origin, but you don't want to create a separate cache entry for every single version of Chrome and Firefox out there. So you put the user agent in the origin request policy, but not in the cache policy.
Let's wrap up with some of the trickiest exam traps we have seen. One is the Lambda at Edge versus CloudFront functions for header manipulation. If the question mentions thousands of requests per second and simple header changes, it is always CloudFront functions. If it mentions third-party libraries or external API calls, it is Lambda at Edge. Another one is the Global Accelerator versus Route 53 latency routing. If the protocol is TCP or UDP, or if you need static IPs, it is Global Accelerator. If you are just doing standard web traffic and want the cheapest solution, it is Route 53.
Also, watch out for the signed URLs versus signed cookies question. Use signed URLs for individual files, like a single video download link. Use signed cookies when you want to provide access to multiple files, like an entire premium folder, without making the user change their URL for every object. And remember, you must use a CloudFront key pair and a trusted key group to manage these. Do not use the old style of using the AWS account root user to create CloudFront keys. That is a major security red flag.
This has been an incredibly dense session, Alex. We have covered the protocol-level optimizations of Global Accelerator, the programmable logic of the edge with Lambda and functions, and the deep security integration of OAC, WF, and Shield.
It's the difference between being a technician and being an architect, understanding not just what these services do, but the specific constraints and triggers that make them effective. That concludes our deep focus on edge computing and security. Thank you for tuning in to this session of High Yield Audio Labs. We have refined the signal, eliminated the noise, and hopefully given you the tools to approach the SAP-C02 with absolute confidence. Keep these concepts in mind. Visualize the packet flow at the edge, and we will see you in the next module. Most architects think they understand the perimeter when they slap a web application firewall in front of a CloudFront distribution, but for the SAP-C02 exam, that is where the real complexity actually begins. If you cannot articulate the precise cryptographic and routing differences between a REST API and an HTTP API, you are already behind the curve.
It is the subtle distinctions that catch people out. I was reviewing a legacy migration last week where they chose REST APIs because it was the default, but they were paying for features they never touched. This session of High Yield Audio Labs is designed to strip away those misconceptions and look at the clinical reality of modern API management on AWS.
Let us start with the choice between REST and HTTP APIs at the gateway level. The exam will frequently present you with a scenario where cost and latency are the primary drivers. In those cases, the HTTP API is almost always the correct answer. It offers up to 70% lower cost and significantly lower latency because it lacks the legacy baggage of the original REST implementation.
But the trade-off is the feature set. If the scenario mentions request transformation, API caching, or private integrations using a VPC link with a network load balancer specifically for a REST-based backend, you have to stick with the REST API. Alex, how do you see the custom authorizer logic fitting into that choice?
Lambda authorizers are the tactical scalpel of the API gateway when you move beyond simple.
A few months ago, a multinational financial group found themselves in a crisis that every solutions architect professional candidate should treat as a cautionary tale. They had successfully migrated 10 petabytes of sensitive transaction data into an Amazon S3-based data lake, but they had relied entirely on S3 bucket policies and IAM roles for access control. When an internal auditor asked for a report on exactly which data scientists had access to specific rows containing personally identifiable information within their Parquet files, the architecture collapsed under the weight of its own complexity. They could not provide the answer. This gap between basic storage and granular governance is exactly where we begin tonight on High Yield Audio Labs. I am Maya, and joining me is Alex. We are looking at the surgical precision required to master AWS analytics and data lakes for the SAP-C02 exam.
It is a common failure point, Maya. Architects often forget that while S3 is the foundation, a true enterprise data lake requires a control plane that understands the data itself, not just the objects. For the exam, you must distinguish between managing a bucket and managing a schema. That is where AWS Lake Formation becomes the centerpiece of our discussion. It is no longer enough to just talk about IAM. We have to talk about how Lake Formation wraps around the Glue data catalog to provide that cell level, row level, and column level security that regulators now demand.
And that transition is often where the exam questions get tricky. They will present a scenario where you have multiple accounts and you need to share a subset of a table with a third-party analytics team without moving the data. If you are thinking about cross-account S3 bucket policies, you are already behind the curve. Alex, when you are looking at a petabyte scale environment, how do you explain the shift from traditional IAM to the lake formation permission model?
I think of it as moving from perimeter security to data-centric security. In the old model, you gave a user an IAM policy that said they could call the GetObject action on a specific prefix. In a modern AWS data lake, we use lake formation to grant permissions on the actual database, table, or even specific columns. The critical mechanism for the exam is understanding the dual permission model. To access data through lake formation, a principal needs both the lake formation permissions on the data catalog objects and the underlying S3 permissions. However, the best practice architecture is to use lake formation to register the S3 location. When lake formation is in charge, it uses a service-linked role to access the data on behalf of the user. This means the individual users do not need direct S3 access at all. They only need permissions to talk to lake formation. This eliminates the risk of someone bypassing the governance layer by hitting the S3 API directly.
That is a vital distinction for the professional level. If the exam asks how to simplify cross-account sharing for a data lake, you should be looking for answers that involve lake formation and specifically its integration with AWS Resource Access Manager or the newer LF tags. Can we dive into the LF tags versus the named resource method? Because on a petabyte scale, managing permissions for thousands of tables by name is an administrative nightmare.
You are right. Named resource permissions are for small-scale operations. For the SAP-C02, you want to focus on tag-based access control, or LF tags. Think of it like attribute-based access control for your data. You define a tag, such as confidentiality, with values like public, internal, and restricted. You then associate these tags with your databases, tables, or columns. Instead of granting a user access to Table A and Table B, you grant them access to any resource where confidentiality equals internal. This scales beautifully. When a new table is added to the lake, you simply tag it, and the permissions are automatically applied. For cross-account scenarios, you can even share these tags across organizations using Resource Access Manager. This allows the consumer account to manage their own local permissions based on the tags you have shared, maintaining a decentralized but governed environment.
This brings us to the compute side of the house. Once the data is governed, how do we actually analyze it? The exam frequently pits Amazon Athena against Amazon Redshift. In a scenario with petabytes of data, the cost and performance implications of choosing one over the other are massive. Alex, when do you advise a client to stay serverless with Athena versus committing to a Redshift cluster?
It comes down to the frequency of the queries and the required latency. Athena is our primary tool for ad hoc, serverless analysis of data in S3. It is perfect for those. I wonder how many customers in the Northeast bought this product last Tuesday moments. It uses Presto and Trino under the hood, and you pay only for the data scanned. However, if you are running complex, repetitive analytical workloads where you need sub-second or very low-second response times, Redshift is the powerhouse. Specifically, for the SAP-C02, you must be intimately familiar with the Redshift RA3 instance type. RA3 is a total departure from the old DS2 or DC2 nodes because it decouples compute from storage.
That decoupling is the key. In the past, if you needed more storage in Redshift, you had to add more compute nodes, which was expensive and inefficient. With RA3 nodes and Redshift managed storage, the data sits in a high-performance storage tier backed by S3. The cluster only keeps the hot data in local SSDs. This allows you to scale your compute based on your processing needs while your storage can grow to petabytes automatically. It also enables one of the most powerful features for the exam, Redshift data sharing.
Exactly. Data sharing allows you to share live data across Redshift clusters without copying it. Imagine a central producer cluster that handles all the ETL and data ingestion. You can then have multiple consumer clusters, maybe one for the marketing team and one for the finance team. They can query the producer's data in real time. Since they are separate clusters, the marketing team's heavy queries won't slow down the finance team's reports. This is a massive architectural win for isolation and scalability. And if you need to query the data lake directly from Redshift, you have Redshift Spectrum. Spectrum is essentially Athena-like functionality built into your Redshift cluster, allowing you to join highly structured data in your local disks with vast amounts of semi-structured data in S3.
Let us look at the performance optimization for these tools, because that is where the professional part of the exam title comes in. If a candidate sees a question about Athena or Spectrum queries being slow or expensive, the answer is almost always related to data partitioning and file formats. We are looking for Parquet or ORC files. We are looking for snappy compression. And most importantly, we are looking for effective partitioning. Alex, what is the war story approach to fixing a failing data lake query?
I always start by looking at the file sizes. A common mistake is having millions of tiny files in S3. Every time Athena or Spectrum runs a query, it has to open each file, which adds significant overhead. We want files that are roughly 100 megabytes to 1 gigabyte in size. We use AWS Glue ETL jobs to compact these small files into larger ones and convert them into columnar formats like Parquet. Columnar storage is life-changing for analytics. If your table has 200 columns, but your query only needs 3, Athena only reads the data for those 3 columns. This can reduce the data scanned, and therefore the cost, by over 90%. Then there is partitioning. You should partition your data based on how it is queried, typically by year, month, and day. If you query for data from yesterday, Athena will use the partition metadata to skip every other folder in S3. This is what we call partition pruning.
We should also mention the Athena federated query. This is a frequent appearance on the exam for hybrid or complex environments. Sometimes data isn't in the lake yet. It might be in an RDS PostgreSQL database or a DynamoDB table. Athena Federated Query uses Lambda functions to connect to these data sources. It allows you to write a single SQL query that joins data from S3 with data from a live production database. While it's not as fast as having everything in Parquet, it's an incredible tool for real-time insights without waiting for an ETL pipeline to finish.
It is, but you have to be careful with the cost of those Lambda executions and the load on the source database. Another sophisticated tool that the exam likes to test is the Amazon Redshift Advisor and the concurrency scaling feature. If a cluster is experiencing bottlenecks because too many people are querying at once, ConShift scaling can automatically add transient capacity to handle the burst. The first hour of this scaling per day is usually free, which makes it a very attractive answer for cost-optimized architecture questions.
Speaking of cost, let us talk about the lifecycle of this data. Not all petabytes are equal. Some data is fresh and queried every hour. Some is for compliance and won't be touched for years. On high-yield audio labs, we often emphasize that the best architecture is the one that stays within budget. How do we integrate S3 storage classes into this analytics fabric?
This is where S3 intelligent tiering is a safe bet for the exam when the access patterns are unknown. But if we know the patterns, we move older data to S3 Glacier Instant Retrieval. It provides milliseconds access, which is perfect for Athena. If the data is truly archival, we use Glacier Deep Archive, but we have to accept that we can't query it directly with Athena without restoring it first. A common exam scenario involves a requirement to keep data for 7 years, but only query the last year frequently. The answer there involves a glue job that keeps the last year in Parquet/S3 standard and moves the rest to a different prefix or bucket with a lifecycle policy to Glacier.
Let us pivot to a live audit scenario. Imagine we are looking at a system where a company uses Glue for ETL, but their jobs are failing or taking too long as their data grows to the petabyte level. They are using standard Glue workers. What is our move?
We look at the glue worker type. For heavy lifting, we move from G.1x to G.2x or even higher. These provide more memory and disk space for Spark to handle shuffles and large joins. We also check if they have enabled job bookmarks. Without bookmarks, a glue job might try to reprocess the entire S3 bucket every time it runs, rather than just the new data. That is a massive waste of resources. Also, for the SAP-C02, keep an eye out for glue data quality. It is a newer feature that allows you to define rules, like this column should never be null, to catch bad data before it pollutes your lake.
And we cannot ignore the security of the pipeline itself. Encryption is non-negotiable. For a data lake of this scale, we are using AWS KMS with customer-managed keys. We need to understand the difference between SSE S3, which is handled by the service, and SSC KMS, which gives us the audit trail and cloud trail that we need for compliance. Alex, how do we handle the KMS throttling issue that often hits large-scale analytics?
That is a classic professional-level problem. When Athena or Redshift tries to read thousands of encrypted objects simultaneously, you can hit the KMS request rate limit. The solution is to use S3 bucket keys. This reduces the request traffic from S3 to KMS by using a bucket-level key for a short period to derive unique object keys. It can lower your KMS costs and prevent those dreaded throttling errors. It is a small checkbox with a huge impact on petabyte-scale performance.
Let us walk through a complex cross-region requirement. A company has their data lake in US, East, 1, but they have a team of analysts in EU, West, 1 who need to run queries. They are worried about data transfer costs and latency. What does the SAP-C02 candidate recommend?
This is where we look at Redshift data sharing across regions. It was a major update that simplifies this exact scenario. You can share data from a producer cluster in one region to a consumer cluster in another. While there are still data transfer costs, the management overhead is significantly lower than building a manual replication pipeline. If they are using Athena, we might consider S3 cross-region replication to move the Parquet files closer to the analysts, and then have a local Glue data catalog in the second region. Remember, the Glue data catalog is regional. You have to keep the metadata in sync if you want to query replicated data efficiently.
We should also touch on the data mesh concept, which is becoming more prevalent in exam scenarios. This is the idea that different business units own their own data, but share it through a central governance layer. Lake formation is the primary enabler here. A central data governance account can hold the lake formation permissions, and individual producer accounts can share their tables with this central account. The central account then grants permissions to consumer accounts. This hub and blood model is the gold standard for large enterprise AWS environments.
It is, and it solves the problem of the monolithic data team that becomes a bottleneck. By decentralizing ownership but centralizing governance, you allow the business to move faster. One more thing on the analytics side, don't forget about Amazon OpenSearch Service. While it's not a data lake tool in the traditional sense, it's often the right answer for log analytics or full-text search scenarios where SQL-based tools like Athena or Redshift might struggle with unstructured text or real-time dashboarding.
That is a great point. If the exam mentions real-time log analysis or sub-second search across application logs, think OpenSearch, not Athena. And if it mentions streaming data, we are looking at Kinesis Data Firehose to ingest that data directly into S3 or Redshift. Firehose can even handle the conversion to Parquet and the partitioning on the fly, which simplifies the architecture by removing the need for an intermediate Lambda function or glue job.
Let us recap the most critical points for the SAP-C02 regarding this topic. First, lake formation is your primary tool for granular security. Understand the service-linked role and how it replaces direct S3 access. Second, Redshift RA3 is the answer for high-performance, scalable data warehousing because it decouples compute and storage. Third, Athena is for serverless ad hoc queries, and its performance depends entirely on Parquet formatting and partitioning. Fourth, Glue is your ETL engine. Use bookmarks, the right worker types, and now, data quality rules. And finally, use KMS with S3 bucket keys to handle encryption at scale.
And always remember the why behind the architecture. AWS isn't just giving us a list of services, they're giving us a framework to solve business problems. The exam will test if you can choose the most cost-effective, secure, and performant path through those services. Whether it's a migration from a legacy Hadoop cluster or building a new AI-ready data lake, the principles remain the same: govern centrally, store efficiently, and compute elastically.
It is about being a surgeon with the tools. You don't use a sledgehammer to fix a watch. You don't use a full Redshift cluster for a query that runs once a week. And you don't use Athena for a dashboard that 1,000 executives are hitting every minute. Knowing those boundaries is what separates a professional architect from a practitioner.
This has been a deep dive into the heart of AWS data architecture. These concepts are the bedrock of the SAP-C02 exam, and mastering them puts you in an elite category of engineers. The precision we discussed tonight, from KMS bucket keys to lake formation tag-based access control, is what turns a passing score into a perfect one.
Success on the exam requires more than just reading the documentation. It requires visualizing these systems in motion, seeing the data flow from ingestion to insight, and anticipating where the bottlenecks will appear. When you can see the whole pipeline in your mind, the questions become much easier to navigate.
We will be continuing this series by looking at the integration of these data lakes with machine learning services like SageMaker in our next session. For now, focus on the governance and the storage. Those are the hardest parts to get right and the easiest parts to test.
I look forward to it. There is a lot to uncover when we start talking about how to actually use this petabyte-scale data to train models without compromising security.
This concludes our session on AWS Analytics and Data Lakes. Thank you for joining us for this deep work review on high-yield audio labs. Keep studying, keep building, and stay clinical in your approach. We will see you in the next module. I was reviewing a post-incident report from a financial services client yesterday. They had a textbook cryptojacking event. What stood out wasn't the breach itself, it was an exposed Jenkins server, but the timeline. They had Amazon Guard Duty enabled, but it took their SOC team 4 hours to notice the finding because they were drowning in low-fidelity noise from a legacy third-party CM. It's the classic signal-to-noise problem. Welcome to High Yield Audio Labs. I'm Maya.
That's a failure of architecture, not just operations. I'm Alex, and tonight, we are dissecting security posture management for the AWS SAP-C02 exam. We are going to surgically remove the confusion between threat detection, vulnerability assessment, and compliance monitoring. If you are sitting for the SAP-C02, you cannot just know what the services are. You need to know how they bleed into each other to form a cohesive defense.
Let's start with the eyes of the operation. Amazon Guard Duty. The exam loves to test the boundaries of what Guard Duty actually sees.
Precisely. Guard Duty is your intelligent threat detection service. It does not look at your code. It does not look at your operating system configuration. It looks at activity. It analyzes 3 foundational data sources: AWS CloudTrail Management Events, VPC Flow Logs, and DNS Query Logs.
And for the SAP-C02, candidates need to remember that enabling Guard Duty does not require you to turn on those logs manually.
Correct. That is a critical distinction. Guard Duty pulls that data directly from the AWS backend infrastructure. You do not pay for CloudTrail or VPC Flow log storage to feed Guard Duty. It consumes the stream directly. If you have 1,000 accounts in an AWS organization, you enable it via the delegated administrator, and it instantly begins profiling independent baselines for every account.
Let's drill into those data sources. The exam often presents a scenario where an EC2 instance is querying a known command and control domain. Which log source catches that?
That is a DNS query log finding. Guard Duty checks your DNS requests against threat intelligence feeds, both AWS internal threat intel and third-party feeds like Proofpoint and CrowdStrike. Even if the traffic is blocked by a security group, the DNS lookup happens first. Guard Duty sees the intent.
What about the newer data sources? The exam has updated. It's not just the big 3 anymore.
You are referring to EKS audit logs, RDS login events, and S3 data events. For the SAP level, you need to understand the EKS integration. Guard Duty can detect a compromised pod inside a Kubernetes cluster communicating with a mining pool. It analyzes the Kubernetes audit logs to see if an attacker is making unauthorized API calls within the cluster.
And Lambda protection?
Yes, Guard Duty now monitors Lambda network activity logs. If a function is hijacked to run malicious code, say, a reverse shell, Guard Duty flags the outbound connection to a suspicious IP. It also monitors the Lambda control plane API for unusual invocation patterns.
Let's shift to the why. Why does the exam penalize you for confusing Guard Duty with Amazon Inspector?
Because they answer 2 fundamentally different questions. Guard Duty asks, is anyone behaving badly right now? Inspector asks, is anything configured in a way that allows bad behavior? Guard Duty is dynamic. Inspector is static.
Let's open up Amazon Inspector, specifically Inspector v2. The classic version is effectively dead for the purposes of modern architecture. What is the architectural shift in v2?
The shift is the removal of the standalone agent. Inspector v2 leverages the AWS Systems Manager, the SSM agent. which should already be on your EC2 instances for fleet management. This reduces agent fatigue. You don't need a sidecar agent just for vulnerability scanning anymore.
So, for an SAP-C02 scenario involving a fleet of 10,000 EC2 instances, if the requirement is continuous vulnerability assessment with minimal operational overhead, the answer involves ensuring the SSM agent is active and enabling Inspector.
Exactly. And continuous is the keyword. Inspector v2 creates an event-driven architecture. It doesn't just scan on a schedule like a cron job. It scans when you launch an instance. It scans when you install a new package. It scans when a new CV is published to the database. It is a state machine for vulnerabilities.
It's not limited to EC2, though. The container registry scanning is a massive part of the exam now.
Yes, Amazon ECR scanning. There are two modes here, on push and continuous. On push is simple. You upload a Docker image, it gets scanned once. Continuous is for long-lived images. If an image is sitting in your repo for 6 months and a new log4j variant is discovered, on push won't catch it. Continuous scanning will alert you immediately, even if the image hasn't been touched.
A subtle point for the architects, Inspector also scans Lambda functions now. It analyzes the function code and the layers for known vulnerabilities.
Correct. It unzips the package effectively. It looks for Python dependencies or Node.js modules with known CVs.
Let's talk about the output. We have guard duty shouting about active threats and Inspector listing thousands of unpatched libraries. How do we make this usable? This brings us to AWS Security Hub.
Security Hub is this single pane of glass. But for the exam, think of it as a normalization engine. It ingests findings from guard duty, Inspector, Macie, IAM Access Analyzer, and AWS Firewall Manager. It converts them all into a standard format called ASFF, the AWS Security Findings format.
Why is ASFF important for a solutions architect?
Because of automation. If every tool outputted JSON with different schemas, writing remediation scripts would be a nightmare. With ASFF, a severity field is always in the same place. A resource ID is always in the same place. This allows you to build a unified response pipeline using Amazon EventBridge.
Security Hub isn't just a passive collector, though. It has its own opinion on your compliance.
That is the security standards feature. You enable frameworks like the AWS Foundational Security Best Practices, SIS AWS Foundations Benchmark, or PCI-DSS. Security Hub then runs continuous configuration checks, using AWS config rules under the hood to see if you are compliant.
I often see students confuse AWS config with Security Hub. How do you distinguish them in a tricky exam question?
AWS config is the recorder in the rule engine. It records the state of your resources over time. Security Hub is the dashboard that aggregates those config rules and maps them to compliance standards. If the question asks for historical resource configuration changes, the answer is config. If the question asks for a centralized view of compliance against CS benchmarks, the answer is Security Hub.
Let's talk about the multi-region problem. This is a staple of the SAP-C02.
It is. Guard duty, Inspector, and config are regional services. If you have resources in US, East, 1, and EU Central, 1, you have separate findings in each region. Security Hub allows for cross-region aggregation. You designate a home region, say US, East 1. Security Hub will pull findings from all other linked regions into that single dashboard.
So, if the requirement is centralized visibility across multiple accounts and regions, you set up an AWS organization, designate a delegated administrator for Security Hub, and enable cross-region aggregation.
That is the gold standard architecture.
Let's construct a scenario. A developer accidentally commits an AWS access key to a public GitHub repository. 10 minutes later, that key is used to launch unauthorized EC2 instances for crypto mining in a region you don't normally use. Walk us through the detection flow.
This is a layered defense scenario. First, the commit itself. If you have simple regex scanning in your Git pipeline, you might catch it there. But let's assume it gets out. AWS actually scans public GitHub repositories. They will likely detect the exposed key and issue a compromised credentials notification.
But let's say the attacker is fast. They use the key.
The moment they use the key, CloudTrail logs the API call, specifically the run instances call. GuardDuty analyzes this CloudTrail event. It sees an API call coming from an anomalous IP address, perhaps a Tor exit node or a geolocation you've never operated in. GuardDuty generates a finding, unauthorized access, IAM user/Tor IP caller.
Simultaneously, the instances launch.
Right. The instances start passing traffic to a mining pool. GuardDuty sees this network traffic via VPC flow logs and generates a second finding. Cryptocurrency, EC2/BitcoinTool.B.
Now, where does Security Hub fit in?
Both GuardDuty findings are sent to Security Hub in the ASFF format. Because you have cross-region aggregation enabled, even though this happened in AP Southeast 1, the finding appears in your main dashboard in US East 1.
And the response? We can't rely on a human watching a dashboard.
No, you need automated remediation. In Security Hub, you can use custom actions. But the more robust way is an event bridge rule. The rule matches the specific GuardDuty finding types. It targets a Lambda function.
And what does that Lambda function do?
For the IAM key, the Lambda function hits the IAM API and deactivates the access key. For the EC2 instances, the Lambda hits the EC2 API to stop or terminate the instances and perhaps modifies the security group to isolate them for forensics.
That's the security posture management lifecycle. Detect, aggregate, remediate.
There is another layer we need to discuss. Amazon Detective. It often appears as a distractor in these questions.
Yes. When do I use GuardDuty versus Detective?
GuardDuty is the alarm bell. Detective is the magnifying glass. GuardDuty tells you something happened. Detective helps you understand the scope and the root cause. It ingests the same logs, VPC flow, CloudTrail, EKS audit, and builds a graph model. It visualizes the relationships. This IP talked to this instance, which assumed this role, which created this bucket.
So if the exam question asks for root cause analysis or visualizing the behavior of an entity over time after a breach, you select Amazon Detective.
Precisely. Detective keeps up to a year of data retention for this graph, whereas GuardDuty findings are generally transient if you don't archive them.
Let's circle back to Inspector for a moment. We talked about EC2 and ECR. But what about the concept of deep inspection for EC2?
This refers to Inspector's ability to look inside the OS packages. But there is a nuance with network reachability scans. Inspector can also perform network reachability assessments without an agent. It analyzes your security groups in ACLs, route tables, and internet gateways to determine if ports are reachable from the internet.
Is that still Inspector? I recall that being a separate feature.
It is part of the Inspector suite, specifically Inspector Network Reachability. It's distinct from the host assessment, which needs the agent. This is purely a configuration analysis of the networking stack. If you have port 22 open to 0.0.0.0/0, Inspector Network Reachability will flag it, even if the instance is turned off.
That is a key exam discriminator. How do you identify instances with open SSH ports without installing agents or running active network probes? The answer is Inspector Network Reachability, or AWS Reachability Analyzer.
Correct. Reachability Analyzer is more for troubleshooting connectivity. Why can't a talk to B? Inspector Network Reachability is for security posture. Who can talk to me from the internet?
Let's talk about managing exceptions. In the real world and in the exam, sometimes you need to accept a risk. You have a legacy server that must run an old version of Java. Inspector flags it. You don't want your compliance score to tank.
In Security Hub, you can set the workflow status of a finding to suppressed. This acknowledges the finding but removes it from your active metrics. However, the SAP-C02 checks if you know how to audit the suppressions. You shouldn't just suppress and forget. You need a process to review suppressed findings.
Does Systems Manager, Patch Manager play a role here?
It does. It is the natural partner to Inspector. Inspector finds the vulnerability, Patch Manager fixes it. You can create a patch baseline in Systems Manager. When Inspector finds a missing patch, you can trigger a Systems Manager run command to apply the patch during a maintenance window.
So, the architecture is Inspector scans dash sends finding to Security Hub dash Event Bridge triggers Systems Manager automation dash patch is applied.
That is this self-healing infrastructure pattern.
I want to touch on the cost aspect. Guard duty can get expensive if you have massive VPC flow logs.
It can. But remember, guard duty analyzes the logs without storing them. It is generally cheaper than shipping all those flow logs to S3 and running Athena queries on them. However, you can use S3 data event protection selectively. You don't have to enable it for every bucket. You should enable it for your critical buckets, those containing PII or financial data.
And for Inspector?
Inspector v2 is priced per instance scan hour and per image push. It is much more predictable than the old assessment run model.
Let's review the integration with AWS organizations again. It is fundamental.
The delegated administrator concept is ubiquitous now. You designate a security account. Let's call it the security tooling account. From the management account, you delegate guard duty, inspector, and security hub administration to this security tooling account. This allows your security team to manage policies for the entire organization without logging into the root payer account.
And auto-enable.
Yes, in the delegated administrator account, you turn on auto-enable for guard duty and inspector. This ensures that when a developer creates a brand new AWS account in the organization on a Friday night, the security services are instantly active. No manual intervention required.
A specific exam trick I've seen involves account compromise versus instance compromise.
Good distinction. An instance compromise is usually malware or a shell on a VM. Guard duty catches this via VPC flow logs or DNS. An account compromise means IAM credentials are stolen. Guard duty catches this via CloudTrail, looking for API calls from unusual locations or API calls that break behavioral baselines, like a user who only ever reads S3 suddenly, trying to terminate instances.
There is a finding type called Penteist, IAM user / Kali Linux.
Yes, guard duty can fingerprint tools. If it sees API calls coming from a user agent associated with Kali Linux or other pentesting frameworks, it alerts. It assumes you aren't running unauthorized pentests against your own production environment.
What about false positives?
They happen. You can use trusted IP lists in guard duty. If you have a corporate HQ IP range that does a lot of scanning, you can whitelist it so guard duty doesn't scream every time your internal scanner runs.
And threat intel lists?
You can upload your own. If your industry has a specific set of malicious IPs, say known competitor scrapers or industry-specific attackers, You can upload that list to GuardDuty. It will alert on any communication with those IPs.
Let's summarize the architecture for a security posture management question on the SAP-C02.
1. Enable GuardDuty in all regions and accounts via organizations for active threat detection. 2. Enable Inspector v2 for continuous vulnerability scanning of EC2, ECR, and Lambda. 3. Enable Security Hub to aggregate everything into a single view, ASFF, and check against compliance standards, CS/PCI. 4. Use EventBridge to act on findings automatically. 5. Use Detective for deep dives and root cause analysis. 6. Use Systems Manager to patch the vulnerabilities Inspector finds.
And don't forget the human element. The security posture isn't just tools. It's the process of reviewing these dashboards.
True, but for the exam, AWS wants to see automation. They want to see that you have removed the human bottleneck from the detection and initial containment phases.
One last question that stumps people. Which service creates the finding if an S3 bucket is public?
That's tricky. Multiple services can see it. S3 itself will warn you. Trusted Advisor will warn you. But in the context of security posture, Security Hub, via config rules, or IAM Access Analyzer are the primary answers. IAM Access Analyzer specifically uses mathematical logic to prove that a resource-based policy allows external access. It generates a finding in Security Hub.
So if the question asks for mathematically proven external access verification, it's IAM Access Analyzer.
Every time.
And if it asks for detecting anomalous data exfiltration from S3, that's GuardDuty.
Exactly. Access Analyzer checks the permission, the potential. GuardDuty checks the traffic, the reality.
That distinction is pure gold.
One final war story. I had a client who ignored GuardDuty findings for SSH brute force because they thought our firewall blocks it. It turned out the brute force was coming from inside the VPC, from a compromised Bastion host. GuardDuty saw the internal private IP traffic. Firewalls don't help if the threat is already inside the perimeter. Defense in depth means assuming the perimeter will fail.
And that is why we monitor behavior, not just borders.
Precisely.
We've covered the triad: GuardDuty for threats, Inspector for vulnerabilities, Security Hub for compliance. Mastering the interplay between these three is non-negotiable for the SAP-C02.
If you can visualize the flow of JSON data from a log source, to a detection engine, to an aggregator, to an automation rule, you will pass this domain.
This has been another session of High Yield Audio Labs. I'm Maya.
I'm Alex. Trust the architecture, but verify the logs. Good night. The most dangerous assumption in cloud architecture isn't that your perimeter is secure. It's the assumption that the state of your infrastructure today is the same as it was yesterday. Drift is entropy, and in a regulated environment, entropy is a violation. If you cannot prove the exact configuration of a resource at a specific timestamp in the past, you have already failed the audit.
That is the core of the SAP-C02 domain we are dissecting tonight. Welcome back to High Yield Audio Labs. I am Maya, here with Alex, and we are entering deep focus on compliance and audit automation. Specifically, we are looking at the mechanism of governance, AWS config, and CloudTrail. Alex, for the exam, candidates often conflate monitoring with observability. But compliance is neither. What is the precise mental model for AWS config?
Config is a time machine. That is the only way to think about it. It is not a real-time intrusion detection system. That's GuardDuty. Config is a configuration history recorder. It captures the state of a resource, a configuration item, or CI, every time it changes. It records the relationships between resources. If an EC2 instance is attached to a security group, and that security group is modified, Config records the change in the relationship. For the SAP-C02, you need to understand that config is your source of truth for what did this look like at 2 a.m. last Tuesday.
And that leads directly to the concept of config rules. The exam loves to test managed rules versus custom rules. Let's clarify the distinction. Managed rules are prepackaged by AWS. Things like encrypted volumes or SSH restricted. You just turn them on. But where does the complexity lie?
The complexity and the exam trap lies in custom rules. A custom rule is simply a Lambda function. You write the logic. If the logic returns -compliant, config flags the resource. The trap is usually about scope and trigger type. There are two trigger types: configuration changes and periodic. A configuration change trigger fires the Lambda immediately after config detects a change to a specific resource type. A periodic trigger runs on a schedule, say, every 24 hours.
Right. So if I have a requirement to ensure that no security group allows port 22 from 0.0.0.0, I would use a configuration change trigger. I want to know the second that rule is violated. But if I need to check if an IAM key is rotated every 90 days, that's a periodic trigger. I don't need to check that every millisecond.
Exactly. Now, let's layer in remediation. Config doesn't just report, it can act. This is done via SSM automation documents. When a rule becomes non-compliant, config can trigger an SSM document to fix it. For example, if a security group opens port 22 to the world, config triggers an SSM document that removes that ingress rule. This is auto-remediation.
A critical exam scenario involves multi-account environments. We are talking about AWS organizations. How do we deploy these rules across hundreds of accounts without drifting ourselves?
Conformance packs. This is the answer. A conformance pack is a collection of config rules and remediation actions defined in a YAML template, basically CloudFormation. You deploy this pack from the organization's management account or a delegated administrator account to all member accounts. It ensures an immutable baseline. If you are asked how to ensure HIPAA or PCI DSS compliance across an entire organization, the answer is almost always deploy a conformance pack containing the relevant config rules.
And within that multi-account architecture, we need to talk about visibility. If I am the auditor, I do not want to log into 500 accounts to see their compliance status.
You use an aggregator. An AWS config aggregator collects configuration and compliance data from multiple accounts and regions into a single account. This gives you a dashboard view. Be careful though, the aggregator is a view. It doesn't change the data in the source accounts. It just aggregates the state.
Let's pivot to the other side of the equation. Config tells us what changed. CloudTrail tells us who changed it.
CloudTrail is the flight recorder. It records API calls. Every time someone uses the console, the CLI, or an SDK, that is an API call. CloudTrail logs the identity of the caller, the time, the source IP, the request parameters, and the response elements.
The SAP-C02 exam distinguishes heavily between management events and data events. This is often a cost optimization question disguised as a security question.
Correct. By default, trails log management events. These are control plane operations. Create bucket, run instances, modify security group. These are low volume, high value. They tell you about changes to the infrastructure itself.
And data events?
Data events are data plane operations. Get object, put object in S3, invoke in Lambda, DynamoDB object level actions. These are high volume, extremely high volume. They are disabled by default because if you turn them on for a busy S3 bucket, your CloudTrail costs will skyrocket. The exam will give you a scenario. You need to audit who accessed a specific sensitive file in S3. The solution must explicitly mention enabling data events for that specific bucket. If the answer just says enable CloudTrail, it is wrong.
There is also the concept of global service events. Things like IAM, Route 53, and CloudFront. Where do these logs go?
This is a classic trick. For most services, CloudTrail logs are regional. If you launch an instance in US, West 1, the log is in US, West 1. But IAM is a global service. Its endpoint is physically located in US, East 1, in Virginia. So, IAM API calls are logged in the trail that includes global services, which usually deposits logs in the US, East 1 bucket, regardless of where the call originated. If you are looking for an IAM user creation event in the Oregon region logs, you won't find it. It's in Virginia.
Let's talk about integrity. As an auditor, if I see a log file, my first question is, has this been tampered with? A hacker's first move is often to scrub the logs. How does AWS prevent this?
CloudTrail log file integrity validation. When you enable this, CloudTrail generates a digest file every hour. This digest contains a hash of the log files delivered in that hour, and the digest itself is signed with a private key. You can use the public key to verify that the log files have not been modified or deleted since they were delivered. It creates a chain of custody. If a hacker deletes a log line, the hash won't match.
And regarding retention?
CloudTrail keeps 90 days of management events in the console for free. This is the event history. But for long-term retention, which is required for almost all compliance frameworks, you must configure the trail to deliver logs to an S3 bucket. Once in S3, you should apply an object lock policy in compliance mode to make them worm. Write once, read many. That makes them immutable.
Let's synthesize this. We have config recording the state and CloudTrail recording the API calls. But looking at raw logs is impossible at scale. This brings us to CloudTrail Insights.
Insights is anomaly detection. It analyzes your historical API usage patterns. If it sees a spike in terminate instances or access denied, errors that deviates from the baseline, it generates an insight event. This is crucial for operational health and security. It's not for deep forensics on a single packet. It's for spotting a breakout.
I want to walk through a scenario I saw recently. A client had a strictly locked down production account. But suddenly, a developer was able to launch a massive instance type that wasn't on the approved list. Config was running. CloudTrail was running. Why didn't the system stop it?
Because detection is not prevention. This is the nuance. Config detects the change after it happens. It's asynchronous. The developer makes the API call. EC2 validates the request against IAM policies. If IAM allows it, the instance launches. Minutes later, config records the change, evaluates the rule, marks it non-compliant, and potentially triggers a remediation. But for that window of time, the resource existed. If you want prevention, you need service control policies, SCPs, or IAM boundaries. Config is for governance and remediation, not inline blocking.
That is a vital distinction for the exam. If the question asks to prevent a non-compliant resource from ever being created, config is the wrong answer. You need SCPs or IAM. If the question asks to flag and correct non-compliant resources, config is the answer.
Precisely. Now, let's go deeper into the organization trail. In a multi-account structure, you create an organization trail in the management account and apply it to the entire organization. Why is this superior to individual trails?
Because member accounts cannot modify or delete it. It is enforced from the top down. Even the root user of a member account cannot stop an organization trail created by the management account. It guarantees that visibility cannot be turned off by a rogue admin or an attacker who compromises a member account.
Correct. And where do those logs go? They should go to a dedicated log archive account. We separate concerns. The management account controls the trail configuration, but the logs are shipped to an S3 bucket in a completely different account, the log archive account. This prevents the management account from being a single point of failure for log integrity.
Let's touch on AWS Audit Manager. It is newer, but it appears on the SAP-C02. How does it fit with config and CloudTrail?
Think of Audit Manager as the report generator. Config and CloudTrail provide the raw data, the evidence. Audit Manager maps that evidence to specific compliance frameworks like PCI, GDPR, or NIST. It automates the collection of evidence. Instead of taking screenshots of your console for an auditor, Audit Manager pulls the config rule status and CloudTrail logs and packages them into an assessment report. It saves human hours.
Okay, Alex. I want to construct a complex exam scenario. High-yield Audio Labs listeners need to visualize this. Imagine a scenario where a company requires that all S3 buckets must be encrypted. If a bucket is created unencrypted, it must be fixed within 15 minutes. The security team must be notified immediately. How do we architect this?
We start with a config rule. S3, bucket, server, side, encryption, enabled. We set the trigger to configuration change. Step 2, remediation. We associate an SSM automation document with that rule. The document will execute put bucket encryption. We can set this to auto-remediate, but the requirement says fixed within 15 minutes, which implies we might want a manual gate or a slight delay, but let's assume auto-remediation for speed. Step 3, notification. Config sends configuration stream updates to Event Bridge. We create an Event Bridge rule that looks for config rules compliance change where new evaluation result is NON_compliant. Step 4, the target. The Event Bridge rule targets an SNS topic, which sends an email to the security team. So the flow is bucket created dash config detects change dash config evaluates rule dash rule fails dash event bridge detects failure dash SNS notifies team dash config triggers SSM dash SSM encrypts bucket.
That is the complete life cycle. The exam might also ask about config custom resources. When do we need those?
Config natively supports most AWS resources, EC2, RDS, S3, etc. But what if you were using a third-party tool like GitHub or an on-premise server? You can define a custom resource in config. You have to write the code to publish the configuration of that external resource into config. It allows you to use AWS config as a centralized CMDB configuration management database for hybrid environments.
Let's clarify the pricing aspect briefly, as it often impacts architectural decisions in exam questions. Config rules are not free.
No, they are not. You pay per configuration item recorded and per rule evaluation. If you have a rule that checks every time a security group changes, and you have a script that updates security groups every second, you will have a massive bill. The exam might present a scenario where a customer is seeing unexpected config costs. The answer is usually to check for high-churn resources, resources that change configuration very frequently, and exclude them from recording if they aren't critical.
Or use periodic triggers instead of change triggers for volatile resources.
Exactly.
Another subtle point, CloudTrail event history versus CloudWatch logs.
CloudTrail event history is just a lookup table in the console for the last 90 days. You can't perform complex analytics on it. To search, filter, and alert on logs effectively, you must send the CloudTrail logs to CloudWatch logs. Once they are in CloudWatch logs, you can use metric filters to turn log data into numerical metrics. For example, count how many times console login failed. Then you create a CloudWatch alarm on that metric.
This is the standard pattern for real-time security alerting. CloudTrail - CloudWatch Logs - Metric Filter - Alarm - SNS.
Yes, and if you need deeper analytics, like SQL querying, you send the logs to S3 and use Athena. Athena is for ad hoc investigation. Show me all API calls from IP 1.2.3.4 in the last year. That's an Athena query on CloudTrail logs in S3.
Let's double back to conformance packs. Can they be immutable?
They can be drift resistant. If someone modifies a rule deployed by a conformance pack, config will detect the drift. But to make the pack itself tamper-proof, you control the permissions. Only the automation role or the admin should have permission to put organization conformance pack.
What about the process integrity aspect? If an attacker gains access to an EC2 instance, they might try to stop the CloudWatch agent or disable logging commands. How do we audit the absence of logs?
That is difficult, but config can check if the log agent is installed and running via SSM managed instance rules. However, for network-level silence, you rely on VPC flow logs. CloudTrail tracks API calls. VPC flow logs track network traffic. They are the two pillars of visibility. If CloudTrail says instance launched and VPC flow log shows outbound traffic on port 4444, you have a compromise.
Let's talk about the invalid events. Often, looking at what failed is more important than what succeeded.
Absolutely. Access denied and unauthorized operation are your primary indicators of compromise or misconfiguration. If you see a burst of access denied calls on an S3 bucket from a specific IAM role, that role has likely been compromised and is being used for reconnaissance. The attacker is fuzzing your permissions to see what they can do. CloudTrail Insights automatically flags this pattern.
I want to briefly touch on AWS Artifact. It is simple, but it's a guaranteed point.
AWS Artifact is the portal where you download AWS compliance reports. If an auditor asks for AWS SOC2 report or ISO 27001 certification, you go to Artifact. You don't generate these. AWS provides them. It also hosts the BAA, Business Associate Agreement, for HIPAA. If the question asks, where do you accept the BAA? The answer is AWS Artifact.
Simple, but essential. Now let's look at a scenario question involving cross-account access. User A in account A assumes a role in account B. Where is the log?
This is the cross-account CloudTrail question. In account A, the source, you see the assume role call. In account B, the target, you see the assume role event in the trail and subsequent actions taken by that role. The key is correlating them. The assume role event provides a temporary credential ID. You trace that ID in account B's logs to see what the user actually did. The logs are split between the accounts. You need access to both or an aggregator/central log archive to reconstruct the full narrative.
And this reinforces why a centralized logging account is mandatory for enterprise architecture.
Without it, you are chasing ghosts across silos.
We are approaching the end of the session. Let's do a rapid-fire review of the key terms for compliance automation. I'll say the requirement, you give the AWS tool. Detect changes to resource configuration.
AWS config.
Record API activity for forensic audit.
CloudTrail.
Automate response to non-compliant resources.
Config rules with SSM remediation.
Prove to an auditor that AWS is compliant with PCI DSS.
AWS Artifact.
Prove to an auditor that your workload is compliant.
AWS Audit Manager.
Ensure new accounts automatically have config and CloudTrail enabled.
Control Tower or AWS organizations with a landing zone. Control Tower sets this up by default using guardrails.
Excellent distinction. Guardrails and control tower are essentially SCPs, preventive and config rules, detective.
Correct.
One final war story before we close. I once audited a company that had perfect CloudTrail coverage, but failed to secure the S3 bucket where the logs were stored. The bucket was public.
That is a catastrophic failure. It highlights the security of the security tools concept. The S3 bucket for logs must be the most secure resource in your infrastructure. Encryption with KMS, using a customer-managed key for rotation. Strict bucket policy allowing only the CloudTrail service principal to write. MFA delete enabled to prevent deletion and object lock for immutability. If you lose the logs, you have lost the ability to explain what happened. You are flying blind.
Security of the security tools. I like that. Listeners, write that down.
The exam will test your ability to layer these services. It is never just turn it on. It is turn it on, secure the output, automate the response, and centralize the visibility.
This has been a deep dive into compliance and audit automation for the SAP-C02. We hope this session has solidified the difference between simply running on AWS and governing AWS.
Governance is not a constraint. It is the foundation of velocity. When you know you are compliant, you can move faster.
Thank you for listening to High Yield Audio Labs. As you sleep on this information, let your brain map the flow. Config record state, CloudTrail records action, and automation enforces the standard.
Good luck. We will see you in the next module. And when the CFO finally saw the bill, it wasn't the EC2 compute that shocked him. It was the inter-region data transfer. They had architected for high availability across 3 regions, but hadn't calculated the cost of replicating petabytes of data in real time. That replication link alone cost more than their entire production cluster. It's a classic tragedy, technically sound, financially ruinous.
Which brings us perfectly into focus for this session on High Yield Audio Labs. Tonight, we are dissecting cost optimization at scale for the SAP-C02 exam. We aren't just talking about turning off unused instances. We are talking about architectural economics.
Precisely. For the SAP-C02, you need to understand that cost optimization isn't an afterthought. It is a non-functional requirement, just like security or latency. If you design a system that scales technically but bankrupts the company at peak load, you have failed as a solutions architect.
Let's start with the heavy hitter, compute. The exam loves to test the nuance between savings plans and reserved instances. Alex, walk us through the decision matrix. When does a candidate choose one over the other?
The default answer in modern AWS architecture is almost always savings plans, but you have to know why to answer the edge cases. Savings plans offer the same savings as convertible reserved instances, but with significantly more flexibility. There are 2 types you must memorize: compute savings plans and EC2 instance savings plans.
Break down the flexibility difference. If I commit to a compute savings plan, what am I actually locking myself into?
You are locking into a specific dollar amount per hour, not a specific instance family. Compute savings plans apply to EC2, Fargate, and Lambda usage. Crucially, they apply across any region, any instance family, any size, and any tenancy. If you move your workload from C5 instances in Virginia to M6 instances in Tokyo, the compute savings plan automatically covers it up to your commitment amount. It offers up to 66% savings.
Contrast that with the EC2 instance savings plan. The savings are deeper, up to 72%, but the handcuffs are tighter.
Correct. With EC2 instance savings plans, you must commit to a specific region and a specific instance family within that region. For example, M5 instances in US East 1. You can change the size, go from large to X large, and you can change the operating system, but you cannot change the family or the region. If you migrate to C5 instances, that plan does nothing for you.
And here is the exam trap I see often: reserved instances, or RIs. They feel like legacy tech, but they still exist. Why would a candidate select RIs over savings plans in a scenario question?
2 specific reasons. First, the secondary market. Standard reserved instances can be sold on the AWS Reserved Instance Marketplace if you no longer need them. Savings plans cannot be sold. If a company anticipates a potential liquidation of assets or a massive strategy shift where they might want to recoup costs, RIs offer an exit strategy. Second, capacity reservations.
Let's drill into that. Savings plans are purely a billing construct. They do not guarantee that an instance will be available when you try to launch it.
Exactly. If you need a guaranteed capacity reservation, say for a critical launch event in a specific availability zone, you need zonal reserved instances. A zonal RI provides a capacity reservation in that specific AZ. A regional RI does not. It only provides the billing discount. So, if the question asks for both a discount and a capacity guarantee, you are looking for zonal RIs or on-demand capacity reservations coupled with a savings plan.
Moving to storage. S3 costs can bleed a budget dry if not managed. We all know the storage classes: standard, intelligent tiering, standard IA, one zone IA, glacier, and deep archive. But the SAP-C02 asks about lifecycle transitions. What is the subtle cost often missed during transitions?
Transition requests. Every time you move an object from one class to another, there is a request charge. If you have millions of tiny objects, say log files or IoT telemetry, and you aggressively move them to Glacier Deep Archive after one day, the transition costs might exceed the storage savings.
This is where S3 intelligent tiering usually becomes the right answer. It automates this movement. But surely there is a catch?
There is a monitoring fee per 1,000 objects. For large objects, it's negligible. For millions of small kilobyte-sized files, that fee adds up. Also, intelligent tiering has a minimum storage duration of 30 days for the overhead calculation on objects smaller than 128 kilobytes. If you delete an object quickly, you might still pay for the full 30 days. However, for unpredictable access patterns, intelligent tiering is the exam's golden child. It moves data between frequent, infrequent, and archive access tiers based on real access patterns without performance impact.
Let's talk about visibility. You cannot optimize what you cannot see. The exam will reference S3 Storage Lens.
S3 Storage Lens is your dashboard for visibility. It provides organization-wide visibility into object storage usage and activity trends. It can identify outliers, like buckets with incomplete multi-part uploads that are just sitting there accumulating cost. If the scenario asks about discovering hidden S3 costs across hundreds of accounts, Storage Lens is the answer.
Speaking of hundreds of accounts, let's pivot to data transfer. This is the silent killer. A common architecture pattern involves an NT gateway. Alex, why is the NT gateway such a frequent villain in cost scenarios?
Because you pay for the gateway hour and per gigabyte of data processed. If you have a fleet of private instances downloading gigabytes of patches or updates from S3, pushing that traffic through an NAT gateway is burning money.
The fix?
Gateway VPC endpoints. For S3 and DynamoDB, you must use Gateway VPC endpoints. They are free. There is no hourly charge and no data processing charge. You route the traffic internally within the AWS network, bypassing the NAT gateway entirely. It is a zero-cost architectural improvement.
And for other services, like Kinesis or CloudWatch?
That requires interface VPC endpoints, powered by PrivateLink. These are not free. You pay an hourly rate and per gigabyte. However, they are often cheaper and definitely more secure than traversing the public internet or a NAT gateway. But for S3 and DynamoDB, always look for the gateway endpoint first.
Let's escalate to the organizational level. The SAP-C02 focuses heavily on multi-account strategies. How do we control costs before they happen?
Service Control Policies, or SCPs, in AWS organizations. You can write a policy that strictly denies the launch of expensive instance types. For example, you can deny the X1 E.32's large instances in developer accounts. This is proactive governance. You don't wait for the bill, you prevent the resource creation.
And cost allocation tags. You cannot perform chargeback without them.
Correct. Tags are just metadata until you activate them in the billing and cost management console. Once activated, they appear in the cost and usage report. A classic exam scenario involves a company that tagged everything but still cannot see the breakdown in the billing report. The missing step is always activating the user-defined cost allocation tags.
Let's discuss the cost and usage report, the CUR.
The CUR is the most granular data source available for AWS costs. It delivers line item details to an S3 bucket. It is the raw data. If a question asks about building a custom dashboard or ingesting billing data into a third-party analysis tool or Amazon Athena, you need the CUR. It is the source of truth.
What about AWS budgets versus AWS cost anomaly detection?
AWS budgets is reactive to a threshold. You set a limit, say $10,000, and it alerts you when you reach 80% or are forecasted to exceed it. Cost anomaly detection uses machine learning to identify spikes that deviate from your normal baseline. It captures the unknown unknowns. If a developer accidentally leaves a massive Lambda loop running, anomaly detection catches it faster than a static budget alert might.
Now, a very specific service for the solution providers out there, AWS Billing Conductor. This is a newer addition to the exam scope.
Crucial for the SAP-C02. AWS Billing Conductor is designed for customers who act as managed service providers or have a chargeback model where they want to show a different price to their internal teams or end customers. It allows you to create pro forma billing views. You can take your actual AWS bill, which might include volume discounts and savings plan benefits, and present a non-discounted or marked up view to your tenant accounts. If the question mentions custom pricing, margins, or showback not matching the payer invoice, the answer is Billing Conductor.
Let's do a rapid fire on networking transfer costs again. Data transfer in is generally free. Data transfer out is expensive. How does CloudFront fit into cost optimization?
CloudFront isn't just for speed, it's for wallet protection. Data transfer out from EC2 to the internet is pricey. Data transfer out from EC2 to CloudFront is free. You only pay for the transfer from CloudFront to the edge, which is typically cheaper per gigabyte than direct EC2 egress, especially at volume. Plus, caching means fewer requests hit your origin, reducing compute load. It effectively acts as a shield for both your servers and your budget.
Another scenario, a company has a massive amount of data in DynamoDB. Read costs are skyrocketing. They're doing full table scans.
That's an anti-pattern. First, switch to query operations instead of scans. Second, implement DynamoDB Accelerator or DAX. DAX is a write-through caching service. If you have read-heavy workloads, DAX returns cached responses in microseconds and spares you the read capacity unit consumption on the main table. You pay for the DAX cluster, but you save significantly on provisioned throughput for the database.
Let's circle back to spot instances. We know they are cheap, up to 90% off. But when can we actually use them in a production architecture?
Only for stateless, fault-tolerant, flexible workloads. Containerized microservices, batch processing jobs, CI/CD pipelines, and high-performance computing grids. The architecture must handle interruption. A great pattern is using spot instances in an auto-scaling group mixed with on-demand instances. You set a base capacity of on-demand for stability and scale out with spot for the peaks.
Is there a tool that helps manage that mix automatically?
Attribute-based instance type selection in auto-scaling groups is powerful, but for recommendations, you look at AWS Compute Optimizer. It analyzes your utilization metrics over the last 14 days, or up to 3 months if you enable the paid feature, and tells you if you are over-provisioned. It might say, you are running on an M5.large, but you only use 10% CPU. Downgrade to an M5.small. It now supports Lambda functions and EBS volumes too.
A quick note on EBS volumes. Users often orphan them.
Yes, when you terminate an EC2 instance, the root EBS volume is usually deleted by default. However, additional attached volumes are not deleted by default. They persist and you pay for them. A common cost leak is thousands of unattached EBS volumes from terminated instances. The fix is a lifecycle policy in Data Lifecycle Manager or a config rule to detect and delete available volumes.
You mentioned Data Lifecycle Manager. Let's talk about snapshots.
Snapshots are incremental, which saves space, but they still cost money. You need a policy to expire old snapshots. You rarely need a daily snapshot from 3 years ago. Use Data Lifecycle Manager to automate the creation and deletion of EBS snapshots and EBS-backed AMIs.
Let's pause and breathe. We are about halfway through this session on High-Yield Audio Labs. If you are drifting, focus. We are shifting to database optimization. RDS versus Aurora.
Aurora Serverless is the keyword here. For workloads with infrequent, intermittent, or unpredictable traffic, Aurora Serverless v2 scales instantly. It shuts down to a fraction of a cost when idle. Compared to provisioning a massive RDS instance that sits idle at night, Serverless is a huge win.
But what if the workload is steady state?
Then provisioned instances with reserved instances are cheaper. Serverless carries a premium per capacity unit. It is cost-effective only when the idle time is significant. Do not default to Serverless for a database that takes constant traffic 24/7. You will overpay.
Let's talk about Amazon Redshift. It's expensive.
It is. For Redshift, Pause and Resume is a feature for on-demand clusters. If your data analysts only run queries from 9 to 5, pause the cluster at 5 p.m. You stop paying for compute. You only pay for storage. Also, use Redshift Spectrum. Instead of loading all petabytes into the Redshift cluster's local storage, keep the cold data in S3 and query it directly using Spectrum. S3 storage is vastly cheaper than Redshift SSDs.
What about EFS, Elastic File System?
EFS leads the league in sticker shock. The standard storage class is pricey. You absolutely must enable EFS lifecycle management. It automatically moves files that haven't been accessed in, say, 7 days to the EFS infrequent access class, which is up to 92% cheaper. The performance trade-off is slightly higher latency, but for a file share where most files are archival, it is mandatory.
Let's look at a complex scenario involving multiple regions and compliance. A company needs to store data in 3 regions for disaster recovery. They're using S3 cross-region replication, CRR. The CFO is screaming about the transfer costs.
This is tricky. CRR incurs data transfer out charges from the source region. To optimize, you have to ask, do we need to replicate everything? You can use S3 replication time control, RDC, to prioritize critical data, but that costs more. The real savings come from filtering. Only replicate the prefixes or tags that are compliance critical. Do not replicate temporary logs. Also, ensure the destination bucket is using a cheaper storage class like Standard IA or Glacier Instant Retrieval immediately upon ingestion.
I want to touch on Trusted Advisor. It is often the first place to look.
Trusted Advisor is the low-hanging fruit scanner. It has a cost optimization pillar. It will explicitly list idle load balancers, underutilized EC2 instances, and unassociated elastic IP addresses. Remember, you pay for an elastic IP if it is not attached to a running instance. It's a penalty for hoarding addresses. Trusted Advisor flags these immediately.
Let's go deeper into the why. Why does AWS charge for unassociated elastic IPs?
IPv for exhaustion. Public IP addresses are a scarce resource. AWS wants to discourage you from reserving them and not using them. It is an economic nudge to efficient behavior.
Alex, give me a war story about data transfer that isn't obvious.
I once audited a microservices architecture running on ECS. They had chatty services talking to each other across availability zones. Every time service A in zone A called service B in zone B, they paid a cross-AZ data transfer fee. They were doing terabytes of internal RPC calls a day.
The solution?
We re-architected for data locality. We used ECS task placement strategies to try and pack communicating services onto the same host, or at least the same availability zone. We also implemented service discovery that prioritized local endpoints. By keeping traffic within the AZ, the data transfer cost dropped to 0.
That is a critical concept, zone affinity. It applies to Kubernetes and EKS as well.
Absolutely. In EKS, there is a setting in the kubeproxy or service mesh to keep traffic topology aware. If you can serve a request from a pod in the same node or zone, do it. It reduces latency and eliminates cost.
What about logging? CloudWatch logs can get expensive with high ingestion rates.
Ingestion fees and archival storage fees. The optimization here is twofold. First, do not log everything at debug level in production. Change the log level to error or info. Second, use export tasks. Don't keep logs in CloudWatch forever. Export them to S3 and then transition them to Glacier. S3 is much cheaper for long-term retention than CloudWatch log storage.
And VPC flow logs?
Same logic. You don't need to capture all traffic all the time if you are just spot checking. But if you do, send them directly to S3, not to CloudWatch logs. It is cheaper to write to S3 than to ingest into CloudWatch.
Let's summarize the hierarchy of cost optimization for the exam. If a question asks for the most cost-effective solution, what is the order of operations?
First, eliminate the need. Can you use a serverless solution that scales to 0? If yes, that wins. Second, if you need servers, right-size them. Use Compute Optimizer. Don't pay for idle CPU. Third, choose the right pricing model. Spot for interruptible, savings plans for steady state. Fourth, optimize the network. Keep traffic local. Use endpoints. Cache at the edge. Fifth, optimize storage. Tier data aggressively.
And remember the operational overhead factor. The exam might offer a solution that saves $10 on infrastructure, but requires a team of engineers to maintain custom scripts. That is not the most cost-effective solution because human time is expensive. Managed services often win because they reduce operational cost.
Correct. Total cost of ownership, TCO, includes the salary of the people managing the blinking lights.
One final trap. The AWS free tier is not an architectural strategy for enterprise.
Laughs dryly, no. Never rely on free tier limits in a production design or an exam answer. We are designing for scale, not for a student project.
Let's talk about Carpenter for a moment. It's becoming relevant in the container space.
Carpenter is an open-source autoscaler for Kubernetes. Unlike the standard cluster autoscaler which waits for pending pods and then adds a node group, Carpenter looks at the specific resource requirements of the pending pods and provisions the exact right instance type to fit them. It calls the EC2 Fleet API directly. It can mix spot and on-demand, and it removes nodes that are underutilized by consolidating pods. It is extremely aggressive at bin packing, which drives down compute costs in EKS clusters significantly.
Aggressive bin packing. I like that phrase. It summarizes the goal. You want your utilization to be high. If you are paying for a CPU cycle, you should be using it.
That is the essence of cloud economics. Capacity planning in the old data center world was about peak provisioning, buying enough hardware for Black Friday and letting it sit idle the rest of the year. Cloud cost optimization is about just-in-time provisioning and continuous right-sizing.
We have covered a lot. Savings plans, RIs, S3 tiers, gateway endpoints, billing conductor, and the importance of data locality.
The SAP-C02 exam will test your ability to synthesize these. You will get a scenario with a complex, multi-region, multi-account setup, and you will have to identify the one lever that pulls the cost down the most without breaking the application.
Often, that lever is simply turn it off.
Instance Scheduler, a simple AWS solution that stops EC2 and RDS instances outside of business hours. If you only run dev environments from 8 a.m. to 6 p.m. on weekdays, you save nearly 70% compared to running them 24/7. It's simple, it's effective, and it's a valid exam answer for non-production environments.
Before we close, a quick word on resource groups.
You can group resources using tags. This allows you to view cost and usage metrics for a specific project or application stack as a single unit. It helps in identifying which specific application is the budget hog.
Excellent. We are at the end of the session.
Remember, cost optimization is an infinite loop. Monitor, analyze, act, repeat. The cloud changes, prices change, and your workload changes.
This has been a deep focus session on cost optimization for the SAP-C02. You have the tools. You know the traps. Go dominate that exam. This is High Yield Audio Labs.
Signing off. Keep your architecture clean and your costs lower.
I was reviewing a postmortem for a major outage at a fintech client last week. They had dashboards everywhere. Green lights on CPU, memory, and disk I/O across the board. Yet, their checkout API was failing for 30% of users. It took them 4 hours to find the root cause was a single downstream dependency throttling requests. It makes you wonder, if you're monitoring everything but seeing nothing, are you actually observing the system?
That is the classic monitoring versus observability trap. Monitoring tells you the system is healthy. Observability tells you why the users are unhappy. Welcome to High Yield Audio Labs. I'm Alex.
I'm Maya. And tonight, we are dissecting the observability and performance domain for the AWS SAP-C02 exam. This isn't just about reading CloudWatch graphs. This is about architecting full-stack visibility that scales across hundreds of accounts and thousands of microservices.
Precisely. The SAP-C02 exam doesn't care if you know how to create a metric. It cares if you know how to trace a request ID from an API gateway in East, one through a Lambda function, into a DynamoDB table and back out, while filtering out noise. We need to start with the heavy lifter, CloudWatch Logs Insights.
It's a favorite on the exam. I often see candidates confuse standard log groups searching with Logs Insights. The key differentiator is the query capability. Standard search is grep. Insights is SQL for your logs.
Right. When you are architecting for scale, you cannot just search for an error string. You need aggregation. For the exam, Remember that Logs Insights allows you to use specific query syntax to perform aggregations on log data. Commands like stats, filter, sort, and limit.
Let's drill into a scenario. You have a fleet of EC2 instances behind an application load balancer. Users report intermittent 500 errors. The logs are massive, terabytes a day. How do you find the pattern without spending a fortune scanning everything?
You optimize the query time range first, but technically, you use the stats command. You'd run a query like filter at message like /error/stats count asterisk by bin 5m. This spins the error counts into 5-minute intervals. The exam might ask you how to visualize this. Logs Insights can generate visualizations directly from these queries if you use the stats command.
And the cost factor?
Crucial. You pay per gigabyte of data scanned. So, if you are designing a solution for a cost-conscious client, you don't just dump everything into one massive log group. You structure your log groups logically or use retention policies to age out data. But for the query itself, there is no index you manage. AWS manages the compute. You just pay for the scan.
Okay, let's pivot to a specific exam pattern, high cardinality data. You have a SaaS application. You want to know which specific tenant ID is generating the most API calls and potentially causing throttling. Standard metrics struggle here because you can't have a custom metric for every single user ID. That's too expensive.
That is the textbook use case for CloudWatch Contributor Insights.
Explain the mechanism. How does it differ from Logs Insights?
Logs Insights is reactive. You run a query when you want to know something. Contributor Insights is continuous. It analyzes log data in real time to build time series data for the top N contributors. So, you define a rule, say, extract the tenant ID field from these structured logs. Contributor Insights then maintains a dynamic leaderboard of the top talkers.
So if the exam presents a scenario where you need to identify top talkers or who is throttling my DynamoDB table in near real time with minimal operational overhead, Contributor Insights is the answer?
Absolutely, especially for DynamoDB. DynamoDB has built-in integration with Contributor Insights. You can turn it on with one click to see the most frequently accessed partition keys. That is a silver bullet for hot partition questions. If you try to do that with Logs Insights, you have to run the query repeatedly. Contributor Insights gives you that dashboard continuously.
Let's move down the stack. We have logs, but logs are siloed. They show you what happened inside a single component. In a microservices architecture, the complexity is in the white space between the components. We need distributed tracing. We need AWS X-Ray.
X-Ray is the glue. It provides the end-to-end view of a request as it travels through your application. The fundamental unit here is the trace, which consists of segments and subsegments.
I always tell people to visualize the X-Ray service map. It's a directed graph. But the exam gets tricky on implementation. Specifically, the X-Ray daemon.
Correct. If you are on EC2, you install the X-Ray daemon. It listens for traffic on UDP port 2000. Your application SDK sends trace data to the daemon, and the daemon buffers and sends it to the X-Ray API in batches. This buffering is important for performance. You don't want your application making a synchronous HTTP call to AWS for every single trace.
What about ECS and Lambda?
For Lambda, it's a checkbox, enable active tracing. The X-Ray daemon runs in the Lambda execution environment automatically. For ECS or Fargate, you typically run the X-Ray daemon as a sidecar container. It sits alongside your application container, sharing the network namespace, so your app still sends data to localhost on UDP 2000.
Here is a concept that trips everyone up: annotations versus metadata. If I want to filter traces by user ID or game session ID in the X-Ray console, which one do I use?
You use annotations. This is binary. Annotations are indexed. You can use filter expressions on them. Show me all traces where user ID equals 1234. Metadata is not indexed. It is just extra key value data you store for debugging when you are looking at a specific trace. You cannot search by metadata.
Annotations are for search, metadata is for context. Got it. Now, sampling rules. In a high-throughput system, tracing every single request adds latency and cost. How do we manage that?
You configure sampling rules. By default, X-Ray records the first request each second, and then 5% of any additional requests. This is the reservoir and fixed rate model. But for the exam, know that you can centralize these rules. You store the sampling rules in the X-Ray console, and the X-Ray daemon fetches them. This allows you to change the sampling rate dynamically without redeploying your code.
Let's shift gears to the open source ecosystem. AWS has moved heavily into managed open source services. Specifically, Amazon Managed Service for Prometheus, AMP, and Amazon Managed Grafana, AMG. Why would an architect choose these over native CloudWatch?
It usually comes down to two things: Kubernetes and ecosystem compatibility. If a company is migrating a massive generic Kubernetes workload to EKS, they are likely already using Prometheus. Rewriting all their alerts and dashboards to CloudWatch is high friction. AMP lets them keep their PromQL queries.
And from an architecture standpoint, how does the data get into AMP?
We use the AWS distro for OpenTelemetry, or ADOT. The ADOT collector runs in your EKS cluster. It scrapes the metrics from your pods, standard Prometheus scraping, and then remote writes them to the AMP workspace endpoint.
The exam might ask about high availability here. Prometheus servers are stateful and notoriously hard to scale manually.
That is the value proposition of AMP. It is serverless. It handles the ingestion, storage, and querying scalability across multiple availability zones automatically. You don't manage the storage retention or the replication. It essentially gives you a multi-AZ Prometheus with a remote write endpoint.
And Grafana sits on top.
Right. Amazon Managed Grafana handles the visualization. It integrates with AWS SSO Identity Center for authentication, which is a big security win. It can query AMP, CloudWatch, X-Ray, and even on-premise data sources simultaneously. If the requirement is unified dashboarding for hybrid environments, think Grafana.
Let's talk about the intersection of these tools. The SAP-C02 exam loves output integration questions. For example, if X-Ray detects high latency, how do we alert on it?
X-Ray itself isn't an alarming engine, but X-Ray publishes metrics to CloudWatch. So you get latency and error rate metrics in CloudWatch derived from your traces. You create a CloudWatch alarm on those metrics.
And what about cross-account observability? We are in a large organization with a control tower setup. We have 50 production accounts. I don't want to log into 50 consoles to debug a transaction.
You need the CloudWatch Observability Access Manager. This allows you to designate a central monitoring account. You create a sink in the monitoring account and a link in the source accounts.
Wait, clarify the sink and link terminology.
Think of the sink as the drain where all the data flows. You create a sink in the central account. It defines what kind of data it accepts: logs, metrics, traces. Then, in your 50 source accounts, you create a link that points to that sink's ARN. Once established, the data doesn't physically move. That's a misconception. Instead, the central account gets permission to view and query the data residing in the source accounts seamlessly. It's a cross-account view overlay.
That distinction is vital. The data stays in the source account for compliance and data sovereignty, but the view is aggregated. Does this apply to X-Ray as well?
Yes. X-ray traces can be viewed across accounts if the permissions are set up correctly. However, for a truly unified trace across accounts, like a Lambda in account A calling a Lambda in account B, you need to ensure the trace header is propagated. X-ray passes a trace header XAMZ and trace ID. If your application code drops that header when making a downstream call, the trace breaks.
So, context propagation is a code-level responsibility, but the visualization is an infrastructure-level configuration.
Exactly.
Let's do a rapid-fire scenario round. I'll give you a requirement. You give me the specific AWS config or service.
Hit me.
Requirement: you need to detect if a specific deployment version of your application is causing an increase in error rates compared to previous versions. You are using X-ray.
You use X-ray groups. You create a group based on a filter expression like service, my app, and annotation version equals v2. Then you can compare the inside group analytics against the all traces analytics.
Requirement: you have a strict SLA. You need to know immediately if 99% of your requests take longer than 500 milliseconds.
CloudWatch alarms on a percentile metric. You don't use the average statistic. You configure the alarm on P99. Average hides the outliers.
Requirement: you need to archive all application logs for 7 years for compliance, but you want to minimize storage costs in CloudWatch.
You create a subscription filter on the CloudWatch log group. Stream the logs to Kinesis Data Firehose and set the destination to S3 Glacier Deep Archive. Then set the CloudWatch retention to something short, like 14 days.
Why Firehose? Why not just export to S3?
Export to S3 is a batch operation. It's not real-time. Firehose is near real-time streaming. If the exam asks for continuous archiving, it's Firehose. If it asks for a one-time backup, it's export.
Requirement: you are using Amazon Managed Service for Prometheus. You want to alert if a custom business metric drops below a threshold.
You use the Alert Manager component within AMP. You define alerting rules in PromQL. These alerts can push to Amazon SNS.
Let's loop back to the concept of cardinality in logs insights. I've seen exam questions about extracting data from unstructured logs.
If your logs are JSON, CloudWatch parses them automatically. You can just reference the fields like http.status. But if they are raw text, you have to use the parse command in logs insights. For example, parse at message, asterisk, asterisk as level, detail. This extraction happens at query time. It is powerful but slower than structured logging.
So the architectural recommendation is always log in JSON.
Always. Structured logging is non-negotiable for modern observability.
What about the service lens map in CloudWatch? How does that relate to X-ray?
Service Lens is effectively the UI that unifies CloudWatch metrics and X-ray traces. It gives you the map, but when you click a node, it overlays the infrastructure metrics, CPU, memory, alongside the transaction metrics, latency, request count. It bridges the gap between my server is slow and my code is slow.
One final deep dive: synthetic monitoring. We talked about passive monitoring, watching real traffic. What about active monitoring?
Amazon CloudWatch Synthetics. Canaries. These are configurable scripts, Node.js or Python, that run on a schedule. They act like a headless browser or an API client. They hit your endpoints to verify availability and latency even when no real users are on the system.
Where do these canaries run?
They run in Lambda layers managed by the synthetic service, but, and this is key, they can be attached to your VPC. This allows them to test private internal endpoints that are not exposed to the public internet.
A common exam trap: a canary fails, but the application is up.
False positive. Usually network configuration. If your canary is attached to a VPC, It needs a path to S3 and CloudWatch to store its results. If you put it in a private subnet without a NAT gateway or VPC endpoints for S3 and CloudWatch, the canary will fail to report status, even if the app is fine.
That is a very specific, very likely exam scenario. Canary failing, app healthy, check VPC endpoints.
Exactly. Also, consider the UI canary versus the API canary. A UI canary loads the page and can take screenshots. This is great for visual monitoring, detecting if a CSS change broke the checkout button.
We have covered the logs, the traces, the metrics, and the synthetics. To wrap up this session, Alex, summarize the core philosophy for the SAP-C02 candidate.
The philosophy is integration. Do not think of these tools in isolation. X-Ray feeds CloudWatch. CloudWatch feeds auto-scaling. Insights feed operational dashboards. The exam wants to see that you can weave these distinct services into a cohesive safety net. You are not just building a system that works. You are building a system that tells you when it is about to break.
And remember the cost-performance trade-offs. Sampling for X-ray, retention policies for logs, and aggregation for metrics.
Correct. You can monitor everything, but you will go broke. You can monitor nothing, and you will go down. The architect's job is to find the balance.
This has been a High Yield Audio Labs production. We hope this session brings you one step closer to that passing score.
Sleep on this. Let the architecture settle in your mind. Good luck with your prep.
End of transmission. I want to start with a number that should terrify every architect listening to this. 4 hours. That was the RTO recovery time objective for a major financial services client I audited last month. They had multi-region active-active stamped all over their architecture diagrams. They were spending $40,000 a month on cross-region data transfer alone. But when we simulated a region failure during the game day, do you know how long it actually took them to restore service?
Let me guess. It wasn't 4 hours.
It was 26 hours. And the reason wasn't the database. The data replicated perfectly. It was the service quotas. They had never requested the GPU instance increases in us, West 2. They had the data, but nowhere to compute it. Welcome to High Yield Audio Labs. I'm Maya.
And I'm Alex. That story is the perfect opening for tonight's deep focus session. We are dissecting the most expensive, complex, and misunderstood domain of the SAP-C02 exam, disaster recovery. Specifically, we're targeting the high availability patterns, AWS Elastic Disaster Recovery, or DRS, cross-region strategies, and the elusive active-active architecture.
This is Module 18. If you are listening to this, you likely understand the basics of backups. We aren't talking about cron jobs running S3CP. We are talking about enterprise-grade, sub-minute RPO, and the architectural decisions that separate a passing score from a failure on the SAP-C02.
Exactly. The exam doesn't care if you know how to enable cross-region replication. It cares if you know when to use it versus AWS backup, versus DRS, versus a pilot-light strategy. It's about the trade-off between cost and recovery time. So, Maya, let's cut the noise. When you see a question asking for lowest possible RTO with a strict budget constraint, what is the first service that should flash in your mind?
AWS Elastic Disaster Recovery, DRS. It's the successor to Cloud Endure, and it's the default answer for I need to replicate on-premise or EC2 workloads to a DR region with minimal downtime, but I don't want to pay for idle instances.
Precision is key here. Explain the architecture of DRS. How does it achieve that low RPO without the high cost of a warm standby?
It uses block-level replication. That's the critical differentiator. You install the AWS replication agent on your source servers, physical, virtual, or EC2. This agent continuously replicates block storage changes to a staging area in your target AWS region.
And that staging area is crucial for the exam. The staging area creates lightweight, low-cost EC2 instances, usually T3.small or similar, that just handle the replication data. They aren't running your application. They are just catching the blocks and writing them to EBS volumes. This is why it's cheaper than warm standby. You aren't paying for your production-sized fleet until you actually trigger a failover.
Right. And when you do trigger that failover, DRS spins up the actual recovery instances based on a launch template you defined. It converts those replicated EBS volumes into bootable volumes for your target instance type. The RPO recovery point objective is typically in the seconds range because it's continuous replication. The RTO is minutes because you have to wait for the conversion and boot process.
Here is a classic exam trap I've seen. The scenario describes a requirement for instant failover or zero downtime. Can you use DRS?
No, absolutely not. DRS has a non-zero RTO. It involves spinning up instances. If the requirement is zero downtime or immediate failover, you are looking at multi-region active-active, not DRS. DRS is for rapid recovery, not instant continuity.
Correct. Let's pivot to that beast, active-active. I often see candidates select active-active for every DR question because it sounds the most robust. Why is that a mistake?
Because of complexity and data consistency. True active-active means you are accepting writes in two regions simultaneously. The CAP theorem comes into play immediately. If you have a network partition between regions, you cannot have both consistency and availability. You have to choose. For SAP-C02, unless they explicitly mention conflict resolution or eventual consistency is acceptable, active-active is rarely the answer for strong consistency financial apps.
But there is a specific AWS service that makes active-active viable for the exam.
DynamoDB Global Tables.
Exactly. If the scenario mentions a serverless architecture or microservices requiring multi-region resilience with local read/write performance, DynamoDB Global Tables is the answer. It handles the multi-master replication for you. But, and this is a big but, you have to design your application to handle conflict resolution. Last writer wins is the default.
Let's complicate the scenario. What if it's a relational database? What if it's Aurora? Can you do active-active with Aurora?
Not easily. Aurora Global Database is primarily an active-passive architecture. One primary region for writes, up to 5 secondary regions for reads. You can promote a secondary to primary, typically in under a minute, but you aren't writing to both simultaneously. There is a write forwarding feature, where read replicas can forward writes to the primary, but that's not true active-active. It just looks like it to the application. For the exam, if you need relational data written in 2 regions simultaneously, you are entering the danger zone of custom application logic or very specific proprietary database features. Stick to Aurora Global Database for low RTO disaster recovery, not necessarily active-active writes.
Let's talk about the pilot light versus warm standby distinction. This is pure semantics, but the exam treats them as distinct architectural patterns. How do you distinguish them in a scenario?
It comes down to what is running. In a pilot light strategy, the data is live, but the compute is off. You have your database data replicating, maybe an RDS read replica in the DR region, or your S3 data replicating. But your application servers, your auto-scaling groups, they are defined, but the instance count is 0. You have the pilot light on, the database, so you can ignite the rest of the system quickly.
And warm standby?
Warm standby means the compute is running, but at a reduced capacity. You have your load balancers, your app servers, everything is functional in the DR region, but maybe you're running 2 instances instead of 20. It can handle a trickle of traffic, maybe synthetic monitoring probes, and can scale up quickly. Pilot light, compute is off. Warm standby, compute is on, but small.
And hot standby or multi-site active-active means full capacity, running in both places, taking traffic. Cost goes up exponentially as you move from backup to pilot light to warm standby to active-active.
Let's discuss AWS backup. It's not just for within a region anymore. The SAP-C02 loves to ask about compliance and ransomware in the context of Doctor.
This is where AWS Backup Vault Lock comes in. If you see a requirement for worm compliance, write once, read many, or protection against malicious deletion by a compromised administrator account, the answer is Vault Lock. It enforces a governance mode or compliance mode on your backup vaults.
And the cross-region copy feature of AWS Backup is the simplest way to hit a generic DR requirement for many services. You don't need to script Lambda functions to copy EBS snapshots anymore. You create a backup plan, define a copy rule to a destination region, and AWS handles the rest. It supports DynamoDB, EBS, RDS, EFS, FSX. It's the easy button for RPO measured in hours or days.
Let's go back to my opening story, the service quotas. That is a silent killer in Doctor when you use DRS or Pilot Light. You are essentially promising that you can launch 500 instances in S, East, 1 when S, West, 2 fails. But does AWS guarantee that capacity is waiting for you?
No, they do not. Unless you use on-demand capacity reservations, ODCR. And this is a very difficult exam trade-off. Capacity reservations cost money. You pay for the instances whether you run them or not. So if you use DRS to save money on compute, but then buy capacity reservations to guarantee the failover, you've negated some of the cost savings.
So what's the architectural compromise?
You reserve capacity for the critical core, the minimal viable product. You might reserve capacity for the database layer and the authentication services. For the stateless front-end web servers, you might rely on the spot market or general on-demand availability, accepting the risk. Or you use a multi-region active-active approach where you are already paying for the compute, effectively reserving it by using it.
Another service that appears frequently in high-end DR questions is Route 53 Application Recovery Controller. This isn't just standard DNS failover.
No, standard Route 53 health checks are great for simple failover. But Application Recovery Controller is for when you need manual, rigorous control over the state of your failover. It uses routing controls, simple on-off switches that you can toggle via API or the console. It separates the decision to failover from the mechanism of failover.
It also has readiness checks. It can look at your auto-scaling group limits, your quotas, your capacity in the recovery region, and tell you, hey, if you tried to fail over right now, you would fail. It solves the exact problem your client had.
Exactly. It audits your readiness continuously. If you see a question about ensuring DR readiness at scale or preventing flapping during complex failovers, look for Route 53 Application Recovery Controller.
Let's run through a war story scenario. A client has a 15-minute RPO and a 4-hour RTO. They have a 10 terabytes Oracle database on EC2 and a fleet of 50 web servers. They want to minimize cost. What do you build?
15-minute RPO for a 10 terabytes Oracle database on EC2 is tight for just snapshots. I would look at DataGuard if they have the license, replicating to a standby instance in the DR region. That's a pilot light for the DB. For the web servers, I'd use an AMI copy strategy or simply use infrastructure as code, CloudFormation/Terraform, to redeploy the stateless tier. I wouldn't pay for replication agents for the web servers if I can just redeploy them from code in 4 hours.
4 hours is plenty of time to hydrate an auto-scaling group from a golden AMI. So you only pay for the storage of the AMIs and the running standby DB instance.
Correct. Now, tighten the screws. RPO is 5 seconds. RTO is 5 minutes. Same stack.
Now you need AWS DRS. You can't redeploy web servers from scratch in 5 minutes reliably at that scale. DRS gives you that sub-second RPO for the data volume on the Oracle server, if compatible, and the web servers are ready to launch. Or you might even need a warm standby for the database to avoid the recovery time of mounting volumes.
And if I say RPO 0, RTO 0?
Then we are rebuilding the application to use DynamoDB global tables, S3 cross-region replication with multi-region access points, and we are running active fleets in both regions behind a Route 53 geolocation policy. And the bill just went up 10x.
High-yield Audio Labs listeners, remember this. Disaster recovery is an insurance policy. Your job as an architect is to sell the right premium for the right coverage. The business will always say they want RPO 0/RTO 0 until you show them the price tag.
Let's touch on S3 specific, Doctor. We mentioned cross-region replication, CRR. But what about S3 multi-region access points, MRAP?
MRAP is a global endpoint, bucket wrap. It automatically routes traffic to the lowest latency bucket. If a region goes down, MRAP can reroute traffic to the other bucket. It simplifies the client-side logic immensely. You don't need to change application config to point to my bucket west instead of my bucket east. The application just talks to the MRAP.
And for compliance? S3 object lock.
Yes. If the question mentions SEC Rule 17a-4 or needing to prevent object deletion for legal hold, you combine S3 replication with S3 object lock in compliance mode on the destination bucket. That is a fortress.
We're coming up on time. Let's recap the hierarchy of RTO/RPO strategies.
At the bottom, high RTO/RPO, low cost, backup and restore. Use AWS Backup cross-region copy. Next step up, Pilot Light. Data is live, replication, compute is dead. Next, Warm Standby. Data is live, compute is running but small. Next, AWS Elastic Disaster Recovery, DRS. Continuous replication, rapid spin-up. RPO seconds, RTO minutes. Top tier, multi-site active. Everything running everywhere. Route 53 handles the traffic flow. RPO/RTO near zero.
And don't forget the enablers. Route 53 application recovery controller for managing the shift, and S3 MRAP for global data access.
One final tip. Test your doctor the exam might ask about game days. You cannot claim to have a DR strategy if you haven't simulated a failure. AWS Fault Injection Simulator, FIS, is the service for this. It introduces chaos, kills instances, adds latency, throttles APIs to prove your architecture stands up.
That's it for disaster recovery. This is a module you will want to listen to again. The nuance between Pilot Light and Warm Standby is where they catch you.
Sleep well, and let those architectures settle in. We'll see you in the next module where we tackle security governance. This is High Yield Audio Labs, signing off.
Here is a scenario that breaks the spirit of even the most seasoned architects. You have designed a perfect, immutable infrastructure using CloudFormation. You have tested it in your sandbox. It is flawless. Then, you attempt to deploy it across 300 accounts in an AWS organization, and suddenly, you're drowning in permission errors, drift alerts, and region mismatches. Why does the theoretical perfection of infrastructure as code collapse so often when it hits the reality of multi-account governance?
That is the exact friction point we are dissecting tonight. It is the difference between writing code and governing an ecosystem. Welcome to this high-yield audio lab session. I'm Alex.
And I'm Maya. Tonight we are doing a deep surgical dive into Domain 3 of the SAP-C02 exam, designed for new solutions, specifically focusing on the governance of CI/CD pipelines and infrastructure as code at an enterprise scale.
The exam does not care if you can write a CloudFormation template to launch an EC2 instance. The associate exam tested that. The professional exam asks, how do you force 500 developers to launch only compliant EC2 instances without you approving every single ticket?
Exactly. It's about vending capability, not just provisioning resources. Let's start with the heavy lifter, CloudFormation stack sets.
Stack sets are the answer to the write once, deploy everywhere requirement. If you see a question about deploying a standard VPC configuration or a baseline set of IAM roles to every new account that joins your organization, the answer is almost certainly stack sets.
But the devil is in the implementation details, specifically the permission models. Alex, walk us through the difference between self-managed permissions and service-managed permissions.
This is a critical distinction. In the old days, we used self-managed permissions. You had to manually create an administration role in the central management account and an execution role in every single target account. You had to establish a trust relationship where the target account trusted the management account.
Which is an operational nightmare if you are adding 5 accounts a week.
Precisely. That is why for the SAP-C02, you generally want to lean towards service-managed permissions. This integrates stack sets directly with AWS organizations. You don't manage the roles manually. When you add a new account to an organizational unit, or OU, stack sets automatically detects it and deploys the stack instances to that account.
So if I have an OU for production, and I have a stack set targeting that OU, any new account I drop in there gets my baseline immediately?
Immediately. And conversely, if you remove an account, you can configure the stack set to either retain or delete the stack resources. That is a setting called account removal behavior. Be careful with that on the exam. If the question involves data retention for compliance, you do not want to auto-delete an S3 logging bucket just because an account moved OUs.
Let's pivot to the pipeline itself. Code pipeline. The classic architectural pattern for the exam is a multi-account pipeline. Source code in a shared services account, deploying to dev, test, and prod accounts. Where do people fail here?
Artifact encryption. This is the silent killer. By default, S3 buckets use server-side encryption with S3, managed keys, SSE, S3. But if code pipeline in account A puts an artifact into a bucket, and code deploy in account B tries to read it, SSE, S3 will not work easily because the keys are local to the account.
So the target account cannot decrypt the build artifact.
Correct. For cross-account pipelines, you must use a customer-managed key, a CMK, in KMS. The pipeline's artifact bucket must be encrypted with this CMK.
And the key policy?
The key policy in the shared services account must explicitly allow the cross-account roles in dev, test, and prod to perform KMS, decrypt, and KMS, describe key. Without that specific permission on the CMK, your pipeline will fail at the download artifact stage every single time.
I've seen exam questions that try to trick you by suggesting you just update the S3 bucket policy.
S3 bucket policies control access to the object, but if you can't decrypt the object, access doesn't matter. It's a two-layer lock. Bucket policy for the door, KMS policy for the box inside. You need both.
Let's talk about the Cloud Development Kit, the CDK. The exam is seeing more CDK references. We are moving away from pure JSON and YAML templates into TypeScript and Python. How does the governance model change?
It changes because the abstraction level rises. With CDK, we talk about constructs. Level 1 constructs are just raw CloudFormation resources. Level 2 are curated, with sensible defaults. But for the exam, and for governance, we care about Level 3 constructs.
These are the architectural patterns.
Right. You can write a Level 3 construct that defines the corporate standard microservice. It includes the Fargate task, the load balancer, the auto-scaling rules, and the CloudWatch alarms, all pre-wired. You publish this to AWS Code Artifact.
And then developers just import that package and instantiate it.
Exactly. They write 5 lines of code, but they deploy 500 lines of CloudFormation. Governance is baked in. You don't have to audit their template for encryption settings if the construct forces encryption by default.
But what if they try to drift? What if a developer tries to modify the security group created by that pipeline manually?
Drift detection is your friend, but automatic remediation is your savior. CloudFormation supports drift detection, which compares the current state of the stack resources against the template. You can run this on a schedule.
On the exam, if they ask for near real-time compliance, CloudFormation drift detection might be too slow because you have to trigger it.
Correct. For real-time, you look at AWS config. Config records the configuration change the moment it happens. You set up a config rule. If a security group allows port 22 from 0.0.0.0, the config rule marks it as non-compliant.
And the remediation?
You use Systems Manager automation documents triggered by that config rule, or an event bridge rule that fires a Lambda function. The pattern is detect via config, remediate via automation.
Let's go deeper into Service Catalog. This is often the answer to how do I let non-technical users launch complex infrastructure?
Service Catalog is essentially a vending machine. You create portfolios of products. A product is just a CloudFormation template. You grant access to these portfolios to IAM users, groups, or roles.
The crucial exam concept here is launch constraints.
Yes, normally, if a user wants to launch an EC2 instance, they need EC2, run instances permission. But you don't want to give a data scientist full EC2 permissions. They might launch a massive instance type and bankrupt you.
So you attach a launch constraint to the product in Service Catalog.
Exactly. The launch constraint specifies an IAM role that Service Catalog assumes to provision the resources. The user, the data scientist, does not need EC2 permissions at all. They only need Service Catalog, provision product. The service assumes the role launches the instance. This is the principle of least privilege in action.
There is also the concept of template constraints.
That restricts the parameters. You can say, for this product, the only allowed instance types are t3.micro and t3.small. Even if the underlying CloudFormation template allows any string, the Service Catalog constraint restricts the drop-down menu the user sees.
Let's weave this back to CI/CD. How do we ensure that the CloudFormation templates we are putting into Service Catalog or deploying by a code pipeline are secure before they are deployed?
This is shifting left. You validate early. You should be using tools like CFNAG or CFNGuard in the build stage of your code pipeline.
CFNGuard is becoming very prominent. It's a policy as code tool.
It allows you to write rules like all S3 buckets must have bucket encryption enabled. You run this check-in code build. If the template fails the rule, the build fails. The pipeline stops. The insecure infrastructure never reaches the deployment stage.
What about dealing with legacy infrastructure? The exam often presents a scenario where a company has hundreds of existing resources created manually, and they want to bring them under CloudFormation management.
That is a resource import operation. You create a template that matches the existing resources and then use the import feature. But a more subtle exam topic is the retain deletion policy.
Explain that.
When you are refactoring stacks, sometimes you need to remove a resource from one stack and move it to another without deleting the actual database or bucket. You set the deletion policy to retain. You delete the stack, the resource stays behind, orphaned. Then you import it into the new stack.
Let's talk about the deployment strategies in Code Deploy, specifically for Lambda and ECS. The exam loves blue/green.
For ECS, blue/green is handled by code deploy using a pair of target groups. You have your live traffic going to target group blue. You spin up your new task set on target group green. Code deploy manipulates the listener rules on the application load balancer to shift traffic.
And the advantage?
Instant rollback. If the alarms go off during the traffic shift, code deploy simply flips the listener rule back to blue. It's safe.
For Lambda, we have canary deployments.
Canary and linear. Linear shifts traffic in equal chunks, say 10% every minute. Canary shifts a small amount, waits for a verification period, and then shifts the rest. Canary 10% 5 minutes means send 10% of traffic to the new version, wait 5 minutes. If no errors, send the remaining 90%.
Is there a scenario where you would use all at once for production?
Only if downtime is acceptable or if the architecture is stateless and idempotent. But for the exam, all at once is rarely the right answer for mission-critical production systems. It's a dev/test strategy.
I want to revisit the multi-account strategy with AWS organizations, specifically Service Control Policies, SCPs. How do SCPs interact with your CI/CD pipeline roles?
This is a common point of confusion. An SCP is a filter. It never grants permissions. It only allows or denies. If your organization root has an SCP that denies S3, put object for a specific region. It does not matter if your pipeline role has administrator access. The SCP blocks it.
So if my pipeline is failing with an explicit deny, and I've checked the IAM policy and the resource policy,
check the SCP, especially if the denial is region-specific or service-specific. A common pattern is an SCP that whitelists only specific AWS regions. If your pipeline tries to deploy a stack to a region not on that list, it will hard fail.
And SCPs affect the root user of the member account too.
Yes, that is the only thing that can restrict the root user. This is vital for governance. You can use an SCP to prevent member accounts from disabling CloudTrail or AWS config. Even the root user of that member account cannot turn off the logging.
Let's discuss immutable infrastructure versus mutable.
Mutable means you SSH into a server and run yum update. Immutable means you bake a new YAMI with the updates, terminate the old server, and launch the new one.
For the SAP-C02, immutable is almost always the preferred architecture.
Correct. It eliminates configuration drift. If a server is acting up, you don't fix it. You kill it and replace it. This integrates perfectly with auto-scaling groups and launch templates. Your CI/CD pipeline should be building AMIs using EC2 Image Builder, not just pushing code.
EC2 Image Builder Pipeline. That's a good specific topic.
It's a managed service. It creates a pipeline that spins up a build instance, applies your components, like installing Java, hardening the OS, installing the CloudWatch agent, then syspreps the image and creates an AMI. It can then distribute that AMI to other regions and other accounts.
So in a multi-account setup, the image builder runs in the shared services account?
Yes, it builds the golden AMI. It then modifies the launch permissions of that AMI to share it with the dev and prod accounts. Or, using the new features, it copies the AMI to those accounts so they own a local copy.
Then, your infrastructure pipeline picks up the new AMI ID and updates the CloudFormation stack sets to roll out the new instances.
Precisely. That is the full loop. Compliance is baked into the image. Deployment is handled by the stack set. The rollout strategy is handled by the auto-scaling group instance refresh.
Instance refresh. That's a feature of ASGs.
It allows you to roll out a new launch template to an ASG without needing code deploy. You tell the ASG, start an instance refresh. It will terminate instances and replace them with a new version, respecting your min-healthy percentage.
Let's look at a nuanced scenario. You have a code pipeline that uses a manual approval action. Who can approve it?
The manual approval action sends a notification, usually via SNS. But the permission to click Approve in the console is controlled by IAM. You can wrap that permission in a policy condition.
So you can say, only the security audit team IAM role can approve the deployment to production.
Exactly. And you should. Segregation of duties. The developers write the code, the pipeline builds it, but the security team holds the keys to the production gate.
What about managing secrets in this pipeline?
Never hard-code secrets in CloudFormation templates. The exam will penalize you instantly for that. You use Systems Manager Parameter Store or Secrets Manager.
In the template, you reference them as dynamic references.
Syntax is resolve, SSM, parameter name, or resolve, Secrets Manager, secret ID. CloudFormation resolves this at deployment time. It fetches the value and injects it. The value is never visible in the template code itself.
But what if I need to rotate that secret?
If it's Secrets Manager, rotation is native. You attach a Lambda function to the secret. It rotates the password in the database and updates the secret value.
But does the application pick up the new password?
That depends on the application code. A well-written application should cache the secret for a short time and reload it on authentication failure. If you are passing the secret as an environment variable in an ECS task definition, you might need to redeploy the task to pick up the new value.
Which brings us back to the pipeline. A secret rotation could trigger a pipeline execution.
It could. You can listen for the rotation event. But ideally, your application retrieves secrets at runtime, not build time.
Let's do a rapid-fire round on specific error scenarios. You get a delete_failed status on a CloudFormation stack. Why?
Usually a resource inside the stack is not empty. An S3 bucket with objects in it, or a security group that is referenced by a resource outside the stack.
How do you fix the bucket issue?
You can't delete a non-empty bucket via CloudFormation unless you use a custom resource lambda to empty it first, or you manually empty it and retry the delete.
Update_rollback_failed. The dreaded loop.
This happens when the rollback itself fails. For example, you tried to upgrade a database instance type, it failed, and CloudFormation tries to roll back to the old type, but you don't have enough capacity in the AZ for the old type anymore.
How do you get out of it?
You use the Continue Update Rollback feature. It allows you to skip the resources that are failing to roll back. You leave them in a broken state to fix manually later, but it frees the stack status so you can operate again.
Let's talk about organization trails.
CloudTrail for the whole organization. You set it up in the management account. You apply it to all regions and all accounts. The logs usually go to a dedicated log archive account.
Why a separate account?
Immutable logging. Even the administrators of the production account should not have write access to the log archive bucket. This ensures forensic integrity. If a hacker compromises production, they cannot wipe the logs because the logs aren't there. They are shipped offsite immediately.
And you protect that log archive bucket with?
MFA delete, versioning, and object lock in governance or compliance mode.
Let's summarize the golden path for the listener. If they're designing a governance strategy for a massive enterprise, what are the 3 pillars?
1. Use AWS organizations with service control policies, SCPs, to set the hard guardrails. Block what should never happen. 2. Use CloudFormation stack sets with service-managed permissions to deploy the baseline, security agents, config rules, IAM roles, to every account automatically. 3. Use Service Catalog to vend approved infrastructure to end users. using launch constraints to decouple permissions.
And the pipeline that orchestrates all this?
Code pipeline, cross-account, using KMS customer-managed keys for artifact encryption, and Event Bridge to glue the event-driven security checks together.
One final trick question. A developer wants to use a third-party tool like Terraform instead of CloudFormation. How does this change the SAP-C02 perspective?
The exam is AWS-centric, but it acknowledges Terraform. The principles remain. You would use a CI/CD runner, like code build, to execute the Terraform apply. The state file needs to be stored in S3 with DynamoDB for locking. The cross-account roles are still required. The governance is identical, only the syntax changes.
But for the exam, if the requirement is native AWS integration or minimize operational overhead, CloudFormation or CDK is usually the preferred answer over third-party tools.
Correct. Always bet on the home team for the exam unless the scenario explicitly demands multi-cloud support.
We have covered a lot of ground, from stack sets to encryption contexts.
The key is to visualize the flow of permissions. Identity A needs to assume role B to touch resource C. Trace that line. If it crosses an account boundary, look for the trust policy. If it involves encryption, look for the key policy. If it involves an organization, look for the SCP.
Excellent breakdown. This has been a High Yield Audio Labs production. We hope this session helps you construct a mental model that is as resilient as the architectures you build.
Sleep on this. Let your brain compile the data. We will see you in the next module. Good luck.
Good night.
The sheer volume of shadow IT we uncover during the discovery phase is frankly terrifying. You walk into a boardroom, the CIO tells you they have 500 servers, and by the time you finish the initial scan with Application Discovery Service, you're looking at 1,500. It's not just a capacity problem, it's a governance nightmare.
It's the classic iceberg scenario. They see the production web servers, but they miss the 3 generations of dev environments and the forgotten reporting databases running under someone's desk. Welcome to another deep dive session with High Yield Audio Labs. I'm Maya, and today we are dissecting Module 20, Migration Discovery and Assessment for the AWS SAP-C02. Alex, we're looking at the critical phase before a single byte of data actually moves.
Precisely. If you fail here, you are just moving your technical debt from a data center you own to a data center you rent. That is not migration. That's just expensive hosting. The SAP-C02 exam focuses heavily on this because a solution architect must be able to quantify the environment before designing the landing zone. We need to talk about the tools AWS provides to map this chaos, specifically the AWS Application Discovery Service, or ADS, and the AWS Migration Hub.
Let's start with the data collection strategy. The exam often presents a scenario where a customer has a mixed environment, some VMware vCenter, some Hyper-V, some bare metal. You need to choose the right discovery tool. We have the agentless collector and the discovery agent. What is the hard line between them?
The hard line is depth and platform. The agentless collector is designed specifically for VMware vCenter. It is an OVA file, open virtual appliance, that you deploy into the vCenter environment. It speaks directly to the vCenter API. It's non-intrusive. It gives you VM inventory, configuration specs like CPU and RAM, and disk utilization details. It is perfect for that initial "what do we have?" sweep. But, and this is the exam key, it does not see inside the operating system.
So it won't show you which processes are talking to which IPs.
Correct. It sees the VM as a black box. If you need network dependency mapping, if you need to know that process A on server 1 is talking to database B on server 2 on port 1433, you must use the AWS Application Discovery Agent.
And the agent supports a wider range of platforms, right?
Yes, Linux and Windows. It doesn't matter if it's on VMware, Hyper-V, bare metal, or even running in another cloud like Azure or EC2 instances you want to migrate to a different region. The agent installs at the OS level. It captures running processes, inbound and outbound network connections, and detailed performance metrics.
This is a crucial distinction for the exam. If the requirement mentions dependency mapping or visualizing server communication, you are forced to select the agent-based approach. The agentless collector cannot do process-level dependency mapping.
Exactly. Now, there is a nuance regarding data security. Candidates often worry about what data is leaving the premise. Both the agent and the agentless collector encrypt data in transit using TLS to the AWS Application Discovery Service. But the agentless collector can be configured to mask or suppress certain information if privacy is a concern, though usually you want that fidelity.
Let's talk about where this data goes. It feeds into the AWS Migration Hub.
Migration Hub is your single pane of glass. It's an aggregator. It doesn't just store data from ADS. It integrates with AWS Migration Evaluator and even third-party tools like Turbonomic or Cloudomize. The key architectural concept here is the home region.
Right. You must select a home region for Migration Hub, and the exam trick is usually about changing it.
Which you cannot do lightly. Once you set a home region for your tracking, that's where your data lives. You can technically delete the data and start over in a new region, but you can't just flip a switch and move the historical tracking data to another region. The home region is for tracking. It does not dictate where you migrate your actual resources. You can track in Oregon and migrate resources to Sydney.
That's a vital distinction. Tracking control plane versus target data plane. Now, Alex, let's pivot to the output of this discovery. The exam loves the 6 rupees, or 7 rupees, of migration. We take the discovery data, and we have to assign a strategy to every single application.
The R-type strategies. This is the heart of the portfolio assessment. AWS, and Gartner originally, defines these as rehost, replatform, refactor, repurchase, retain, retire, and the newcomer, relocate.
Let's dismantle them one by one, specifically regarding how they appear on the exam. Start with rehost.
Rehost is lift and shift. You are moving the bits. You aren't changing the OS. You aren't changing the code. You are taking a VM running Ubuntu 18.04 on-prem and turning it into an EC2 instance running Ubuntu 18.04. The primary tool here is AWS Application Migration Service, or MGN.
And previously Cloud Endure, but for the exam, look for MGN.
Correct. MGN is the standard now. Rehost is the fastest migration path. It offers the quickest ROI in terms of shutting down a data center, but the lowest ROI in terms of cloud modernization. You aren't using cloud-native features. You're just running virtual machines.
So if a scenario describes a tight deadline, the data center lease expires in 3 months, the answer is almost always rehost.
100%. Speed over optimization. Optimization happens later.
Moving to replatform. Lift, tinker, and shift.
This is my favorite middle ground. You aren't rewriting the application code, but you are swapping out the underlying infrastructure for a managed service. The classic example, you have a self-managed MySQL database on a Linux server. You migrate the data to Amazon RDS for MySQL. The application connection string changes, but the SQL schema and queries remain the same.
Or moving a Tomcat application to AWS Elastic Beanstalk.
Exactly. You get the benefits of automated backups, patching, and scaling, tangible cloud value, without the massive cost of rewriting the application logic.
Then we have the big one, refactor, also called re-architecting.
The Holy Grail. This is driven by a strong business need to add features, scale, or performance that otherwise wouldn't be possible in the application's existing environment. You are breaking a monolith into microservices. You are moving from a persistent server to AWS Lambda. You are switching from a relational database to DynamoDB.
And the cost profile?
Highest initial cost, highest effort, longest time to migrate, but lowest long-term operational cost and highest agility. If the exam asks for cloud-native, serverless, or decoupling, you are looking at Refactor.
Let's touch on repurchase.
Drop and shop. You stop using your legacy CRM on-prem and you buy a Salesforce subscription. You replace the software with a SaaS solution. The migration effort is purely data migration. You don't maintain the infrastructure or the application code anymore.
Retain and retire are straightforward, but important for filtering.
Retire is easy. Turn it off. The discovery phase showed nobody uses it. Retain is do nothing for now. Maybe it's a mainframe that is too risky to move, or a legacy app that is being deprecated in 6 months anyway. You mark it as retain in the migration hub and revisit it later.
And the seventh R? Relocate.
Relocate is very specific to VMware Cloud on AWS. This is hypervisor-level migration. You are using VMware HCX to move a VM from on-prem vSphere to vSphere running on AWS bare metal. You don't convert the VM format. It's not an EC2 instance. It's still a vSphere VM. It's faster than rehost because there is no conversion, but it requires that specific VMware Cloud on AWS target.
Let's dig deeper into the Migration Evaluator, formerly TSO Logic. How does this differ from the Application Discovery Service?
Good question. ADS is for the technical team. It gives you the IP addresses, the RAM usage, the dependencies. It helps you plan the how. Migration Evaluator is for the CFO. It builds the business case. It analyzes your on-prem provisioning, what you bought, versus your utilization, what you actually use.
It's looking for the zombie servers.
Exactly. On-prem, you might have bought a server with 64 cores because that was the standard purchasing unit, but it's running at 5% utilization. Migration Evaluator will ingest that data and output a directional business case that says, if you move this to AWS, you don't need an X1 E.32's large. You need an M5. Large. It projects the TCO, total cost of ownership. It is a pre-migration sales and planning tool, often used before you even install the ADS agents.
A common exam scenario involves importing existing inventory data. Let's say a client already has a robust CMDB configuration management database. Do they need to run the discovery agents?
Not necessarily. Migration Hub allows you to import data via CSV. If you trust your CMDB, you can upload that inventory directly to Migration Hub to group applications and track status. However, a CMDB rarely has real-time network dependency data. So, you might import the list of servers from the CMDB to populate the hub, but then deploy agents to critical application servers to map out the actual traffic flows for the complex refactoring candidates.
Let's talk about grouping. In Migration Hub, applications aren't auto-discovered as logical entities, right?
Correct. The tools discover servers. You, the architect, must define an application in Migration Hub by grouping those servers together. You select Server A, Web, Server B, App, and Server C, DB, and label them HR System. This logical grouping allows you to track the migration status of the application as a whole unit.
Alex, what about the dependency mapping visualization? I recall a limitation regarding data retention.
Yes, the raw data collected by the application discovery service agents is stored in an S3 bucket in your account if you configure data exploration, but the visualization in the console, The nice graph showing the spiderweb of connections. That data is retained for a limited period in the AWS service itself. It's usually sufficient for the project window, but you should be exporting that data to Athena or QuickSight if you want long-term analysis.
Speaking of Athena, that's a power move for the exam. If the question asks for custom analytics on the discovery data, like finding all servers with Windows 2008 R2 running a specific process, how do we architect that?
You enable the data exploration feature in ADS. This pushes the raw data collected by the agents into an Amazon Kinesis data firehose, which lands it in an S3 bucket in your account. Once it's in S3, you crawl it with AWS Glue and query it with Amazon Athena. That gives you standard SQL access to your entire on-prem inventory data.
That is a very high probability architecture pattern. ADS-Kinesis-S3-Athena.
It's the standard pattern for any analyze at scale requirement in AWS.
Let's go back to the R selection. How do we handle dependencies that cannot move? For example, a low-latency connection to a mainframe that must stay on-prem.
This drives a hybrid architecture. You would likely rehost the front-end and middleware to AWS, but you retain the mainframe on-prem. The critical piece here is the network. You need direct connect. A VPN might not meet the latency or stability requirements for a tightly coupled application dependency. The discovery phase identifies this requirement. If ADS shows a high volume of traffic between the app server and the mainframe, you know you need to provision a direct connect circuit before you migrate the app server.
And this brings up the concept of wave planning.
Migration is never a big bang, unless you enjoy unemployment. You migrate in waves. Discovery helps you define these waves. Wave 1 might be non-critical dev/test. Wave 2 might be the internal intranet. The dependency mapping ensures you don't accidentally split a wave, moving the app server in Wave 2, but leaving its database for Wave 3, breaking the application for a month.
That's the nightmare scenario. Splitting the stack across the hybrid link unintentionally.
Exactly. If you have a chatty protocol between app and DB, and you split them across a 20 milliseconds latency link, the app performance tanks. Discovery prevents this. You ensure the app and DB are in the same move group.
Alex, let's look at a relocate nuance. VMware Cloud on AWS. Who manages the ESG hosts in that scenario?
AWS manages the hardware and the ESG installation. VMware manages the vCenter software stack. The customer manages the VMs and the NSX networking configuration. It's a shared responsibility model distinct from native EC2. But for migration, the beauty is live migration. You can vMotion a running VM from your data center to VMC on AWS with zero downtime if you have the Layer 2 extension set up, HCX.
That's the only migration type that truly offers zero downtime during the move itself, right? Rehosting with MGN requires a cutover window where you stop the source and launch the target.
Correct. MGN, Application Migration Service, uses continuous block-level replication. It copies the data while the server is running. But to finalize the migration, you have to launch the cutover instance, which takes a few minutes to boot and change IP/DNS. vMotion is live memory state transfer. The user doesn't even notice the blip.
Let's verify the agent prerequisites. What if the customer has strict firewall rules on their on-prem network?
The application discovery agent is outbound only. It needs to talk to the AWS Ads API endpoints on port 443 HTTPS. It does not listen on a port. It doesn't need inbound rules. If the servers don't have internet access, you can route the traffic through a proxy, but it must reach the AWS public endpoints. It does not go through a PrivateLink or VPC endpoint in the traditional sense during the collection phase from on-prem. although AWS is improving private connectivity options constantly. Generally, expect to whitelist the AWS IP ranges for the region on port 443.
And for the agentless connector?
Same. It needs outbound HTTPS to AWS. It also needs inbound access from the vCenter server, usually on port 443, to query the API.
A quick scenario. You are a solution architect for a healthcare company. They have 200 physical servers. They want to move to AWS, but need to identify which servers handle PHI, protected health information, by analyzing the file contents. Does ADS do this?
No. Hard stop. ADS looks at infrastructure, CPU, RAM, network, process names. It does not inspect data inside files or databases. It is not Macy. It is not a DLP, data loss prevention, tool. If you need to classify data sensitivity, you need a different tool set or manual assessment before migration. ADS will tell you, this is a MySQL database using 80% CPU, not this database contains patient records.
Vital distinction. Don't select ADS for data classification questions.
Another common confusion, AWS Schema Conversion Tool, SCT. Where does that fit in discovery?
SCT is specific to database engines.
Right. If you are doing a heterogeneous database migration, say Oracle to Aurora PostgreSQL, that is a refactor/replatform. You use the schema conversion tool to assess the database specifically. It scans your PL/SQL schemas and tells you 90% of this will convert automatically, but these stored procedures need manual rewrite. ADS finds the database server. SCT analyzes the database internals.
So the workflow is ADS finds the server. Migration evaluator builds the cost case. You decide to refactor. Then you use SCT to plan the schema change. Then you use DMS, Database Migration Service, to move the data.
Perfection. That is the integrated tool chain.
Let's talk about the Migration Hub strategy recommendations. The Hub actually provides recommendations now?
It does. Based on the discovery data, it can recommend EC2 instance types. It looks at the peak utilization of CPU and RAM from the agent data and suggests a right-sized instance. This is critical because lift and shift often leads to lift and shift and pay too much if you map 1:1 based on provisioned hardware. Always right-size during the migration mapping if possible, or immediately after.
Can we export the Migration Hub data to tracking tools like Jira?
Not natively with a one-click button, but Migration Hub has an API. You can query the migration status and update your project management tools programmatically. However, the Hub is designed to be the central repository. You should be updating the Hub from your tools or letting the integrated tools like MGN update the Hub automatically.
Okay, let's wrap up the 7 rupees with a complex scenario. A client has a legacy monolithic application. It's mission critical. They want to move to microservices, refactor, but the code is so old nobody understands it fully. They're afraid to touch it. What is the strategy?
This is a strangler fig pattern application. You don't refactor on day one. That's too risky. You likely rehost, lift and shift the monolith to EC2 first. Get it out of the data center. Stabilize it. Then, you slowly peel off pieces of functionality into microservices, lambdas, containers, strangling the monolith until it's gone. So the migration strategy is rehost-refactor. It's a phased R-type approach.
So for the exam, if the risk is high and knowledge is low, avoid refactor as the immediate step. Rehost first.
Correct. Refactor requires deep knowledge of the application logic. If you don't have that, you are walking into a minefield.
One final technical detail on the ADS agent. What happens if the connection to AWS is lost?
The agent buffers data locally on the server. When the connection is restored, it flushes the buffer to AWS. However, the buffer size is finite. If the outage is prolonged, you will have gaps in your metric data, but the dependency mapping should remain relatively accurate as long as the traffic patterns repeat.
High Yield Audio Labs listeners, keep in mind, discovery is an iterative process. You don't just run it once. You run it continuously as you plan your waves.
Absolutely. The environment changes while you are planning. New servers spin up. Old ones die. Keep the agents running until the cutover is complete.
To recap the exam essentials for Module 20, 1. Agentless Collector is for vCenter, gives you inventory and utilization, but no internal processes. 2. Discovery Agent is for deep dive, dependency mapping, and physical/Hyper-V servers. 3. Migration Hub is the central tracker. Home region cannot be changed easily. 4. Migration Evaluator is for TCO and business cases, the $. 5. The 6 or 7 RS dictate the strategy. Rehost, MGN, replatform, RDS, refactor, cloud native, relocate, VMC, repurchase, SaaS, retain, retire. 6. Data exploration pushes discovery data to S3 via Kinesis for Athena analysis.
And remember the golden rule of migration architecture. Discovery prevents disaster. You cannot architect what you cannot see. The most successful migrations are 80% planning and 20% execution. The failed ones are usually the inverse.
We'll see you in Module 21, where we tackle the actual heavy lifting with DMS and MGN. Rest up and let this process map settle in your mind.
This has been High Yield Audio Labs. Good luck with your study. The latency was killing the project. We had a client trying to push 3 petabytes of genomic sequencing data over a standard 1 gig direct connect. They calculated it would take months. The CIO was sweating bullets because the data center lease was expiring in 3 weeks. They assumed because they had a dedicated line, the physics of TCP throughput wouldn't apply to them. They were wrong.
That is a classic miscalculation. Welcome back to High Yield Audio Labs. Tonight, we are dissecting the heavy lifters of AWS data migration. We are not talking about simple S3 uploads. We are talking about the industrial-grade mechanisms required for the SAP-C02 exam, data sync, the Snow family, and the transfer family. I'm Maya, here with Alex. So, Alex, in that 3 petabyte scenario, the exam answer isn't get a bigger pipe, is it?
Rarely. For that volume, unless you have multiple 100 gig links, the wire is the bottleneck. The exam expects you to know exactly when to abandon the network and switch to offline transfer. But before we get to the physical devices, we need to master the primary online engine, AWS Data Sync.
Let's start there. Data sync is frequent on the exam because it is the bridge. It automates moving data between on-premises storage and AWS storage services. What is the core architecture that candidates trip up on?
The agent. Data sync isn't magic. It requires a compute resource in the source environment. You deploy the data sync agent as a virtual machine, VMware, KVM, or Hyper-V on your local network. This agent mounts your source file system via NFS, SMB, or HDFS.
And the connection outbound?
That is the critical piece. The agent communicates with the data sync service endpoint in AWS. It uses port 443. All traffic is TLS encrypted. The exam might present a scenario where a firewall is blocking custom ports. Remember, data sync acts like a standard HTTPS client initiating the connection. It does not require inbound rules from the internet, which security teams love.
Let's talk about the protocol support. The exam often asks about specific metadata preservation. If I am migrating a Windows file server to FSX for Windows file server, why is data sync the preferred tool over a simple script?
Because of ACLs and metadata. Data sync preserves file permissions, ownership, timestamps, And crucially, Windows access control lists when moving to FSX. If you write a Python script or use the AWS CLI, you often lose that metadata or have to reconstruct it manually. Data Sync handles the translation. It also verifies every byte transferred.
Verification is a keyword.
Yes, Data Sync performs an integrity check, checksum verification, both during the transfer and at the end. It ensures the source and destination are bit-perfect copies. On the SAP-C02, if you see a requirement for audit-ready data migration or guaranteed integrity, Data Sync is your signal.
What about bandwidth? If I drop this agent on a corporate network during business hours, am I going to crash the CEO's video call?
Not if you configure it correctly. Data Sync has built-in bandwidth throttling. You can define a soft limit. For example, you can cap it at 500 megabits per second between 8 a.m. and 6 p.m. and then uncap it at night. This is a configurable setting in the task definition.
Okay, let's pivot to the destination. Where can Data Sync push data?
It is broad. S3, EFS, FSX for Windows, FSX for Lustre, and FSX for OpenZFS. Note that it can also move data between AWS storage services, not just from on-prem to AWS. You can use Data Sync to replicate EFS to EFS in a different region for disaster recovery.
Right. Now, let's address the scenario you opened with. 3 petabytes, 3 weeks. Data Sync over a 1 gigabit per second line isn't going to cut it. This brings us to the Snow family.
The offline transfer mechanism. The exam tests your ability to do snowball math. The general rule of thumb used to be, if it takes more than a week to transfer over the network, use Snowball.
Break down the devices. We have Snow Cone, Snowball Edge, and the Snowmobile.
Start small. Snow Cone. It is the ruggedized, portable device. Think of it as a tactical edge device. It holds about 8 terabytes of usable storage for the HDD version or 14 terabytes for the SSD version. It is small enough to fit in a backpack. You use it when you have extremely limited space or power or need to ship data from a remote location like a research vessel or a drone base.
And it supports Data Sync, correct?
Correct. That is a unique feature of Snowcone. It has the Data Sync agent pre-installed. You can wire it up, collect data, and then try to sync it online if the connection permits, or just ship the device back.
Moving up to the workhorse, Snowball Edge.
This is the most common answer for bulk migration. There are 2 flavors you must distinguish: storage optimized and compute optimized. For pure migration, moving those petabytes, you want storage optimized.
What are the specs?
The storage optimized device gives you 80 terabytes of usable capacity. If you have 300 terabytes to move, you order a cluster of them. The exam might ask how to handle 500 terabytes. You don't order one and ship it back and forth 5 times. You order a cluster of devices to run in parallel.
And the compute optimized version?
That is less about migration and more about edge processing. It has more vCPUs and a GPU option. Use that if you need to run machine learning inference or video processing on the data before it gets into AWS. For the migration module of the exam, focus on the storage optimized version.
Security is paramount here. These drives are leaving the client's secure facility and traveling via a shipping courier. How does AWS ensure the data isn't compromised in transit?
Encryption is mandatory and hardware enforced. When you order a Snowball, you use the AWS Key Management Service, KMS, to generate a manifest file. The data on the device is encrypted with 256-bit ASGCM. The keys are never stored on the device in plain text. Even if someone intercepts the truck and rips the device open, they have nothing but noise.
Also, the Trusted Platform Module, or TPM.
Exactly. The hardware detects tampering. If the chassis is breached, the device effectively bricks itself. When it arrives at AWS, they inspect the TPM signatures before they even attempt to unlock it.
And the wipe procedure?
NIST 800 to 88 standards. Once the data is imported into S3, the device is wiped clean before being reassigned. You get an audit report confirming the wipe. That is critical for compliance questions.
Let's talk about the interface. How do you actually get files onto a Snowball Edge?
You don't just plug in a USB drive. The device exposes an S3 compatible endpoint or an NFS/SMB interface. You connect it to your local network. Your servers see it as a local storage target. You use the Ops Hub GUI or the AWS CLI to copy data. For the exam, remember Ops Hub as the user-friendly tool for managing Snow devices locally.
Okay, let's look at the upper limit. Snowmobile.
The shipping container on a semi-truck, 100 petabytes. This is for exabyte scale migrations. If you see a scenario involving 50 petabytes or more, or a complete data center evacuation where the timeline is months, Snowmobile is the answer. It requires site surveys, power hookups. It's a massive logistical operation.
Is there a hard cutoff?
Usually around 10 petabytes implies you should start talking about Snowmobile, but you can technically chain snowballs. However, the exam scenarios are usually distinct. 80 terabytes, Snowball Edge. 50 petabytes, Snowmobile.
Let's shift gears to the third pillar, AWS Transfer Family. This one confuses people because it's not strictly migration in the sense of a one-time move. It's often about modernizing existing workflows.
Precisely. The Transfer Family is a fully managed support service for SFTP, FTPS, and FTP. The use case is almost always lift and shift. You have a legacy process, say, a bank receiving transaction files from partners via SFTP. You want to move that back into the cloud, but you cannot ask 500 partners to change their client configurations or scripts.
So you swap out the on-prem SFTP server for AWS Transfer Family.
Yes, you map the endpoint to your custom host name using Route 53. The partners continue connecting to sftp.bank.com. They don't know anything changed. But on the back end, the files are landing directly in Amazon S3 or Amazon EFS.
That distinction is important. S3 versus EFS backend. When do you choose which?
S3 is the default for object storage, archiving, and data lakes. If the data is going to be processed by a Lambda function or an EMR cluster, land it in S3. Use EFS if the data needs to be immediately accessible by POSIX-compliant applications running on EC2 or containers that need a standard file system interface.
Authentication is another exam favorite. How do we authenticate these SFTP users?
You have three main modes. First, service managed. You store user credentials within the service itself. Simple, great for small setups. Second, AWS Directory Service. You connect it to your Active Directory. This is for enterprise integration.
And the third?
Custom Identity Provider. This uses API Gateway and Lambda. This is the most flexible. You can authenticate against an on-prem LDAP, a custom database, or even integrate third-party IDPs like Okta. If the exam mentions authenticating external partners using an existing proprietary database, the answer is Transfer Family with a custom identity provider.
What about the security of the endpoint itself?
You can deploy the endpoint publicly or inside your VPC. For strict security, you use a VPC-hosted endpoint. This allows you to use security groups to whitelist IP addresses. You can also expose it via AWS PrivateLink, so clients can connect over a private circuit without traversing the public internet.
Let's do a rapid-fire comparison to cement this for High-Yield Audio Labs listeners.
Go.
Scenario: a media company needs to move 200 terabytes of video archives to S3. They have a 10 gigabits per second direct connect, but it is 90% utilized by production traffic. They need the data moved in 2 weeks.
Snowball Edge storage optimized. Even with a 10 gig line, if it's utilized, you can't saturate it. 200 terabytes fits on 3 Snowball Edges. Ship them, fill them, ship them back. It is predictable and isolates the traffic from the production network.
Scenario: a financial firm needs to sync changes from an on-prem file server to S3 every night for backup. The dataset is large, but the daily churn is only 50 gigabytes.
AWS Data Sync. It is perfect for recurring schedules. You install the agent, set a schedule to run at 2 a.m. It scans for changes, transfers only the deltas, and verifies integrity.
Scenario: you're retiring an old FTP server. You need to keep the same static IP address for your clients because they have hard-coded firewall rules.
AWS Transfer Family with a VPC endpoint and an elastic IP. You attach the EIP to the endpoint's network interface.
Tricky one here. A client has 5 petabytes of data. They have a 10 gigabits per second connection that is completely idle. They want the data in S3 as fast as possible.
5 petabytes. Let's do the math. 10 gigabits per second is roughly 1 gigabyte per second, accounting for overhead. That's about 3.6 terabytes per hour, roughly 86 terabytes per day. To move 5,000 terabytes, you are looking at roughly 60 days, 2 months.
Is that acceptable?
It depends on the business requirement. If they need it in 2 weeks, no. You order 20 Snowball Edges or look at a snowmobile. But if they are fine with a background sync over 2 months to save on shipping logistics, you could technically use data sync or simply the CLI. However, for 5 petabytes, the risk of network interruption over 60 days is high. I would still lean towards Snowball Edge for the initial bulk load, then data sync for the cutover.
That hybrid approach is key. Seed with snow, sync with data sync.
Absolutely. That is the pro move. You take a snapshot, ship it on Snowball. While the Snowball is in transit, data is still changing on-prem. Once the Snowball data is loaded into S3, you turn on the data sync agent. It compares the on-prem source with the S3 bucket, which now has 99% of the data, and transfers only the changes that happened while the device was on the truck. That minimizes the downtime for the final cutover.
Let's touch on a niche Snowball feature: tape gateway integration.
Ah, yes. You can actually run the storage gateway software on a Snowball Edge. This is for migrating physical tape libraries. You treat the Snowball as a virtual tape library, VTL, dump your tapes to it, and ship it. It helps you get off Iron Mountain and into S3 Glacier Deep Archive without clogging the pipe.
Speaking of Glacier, can you transfer directly to Glacier using these tools?
With data sync, yes, you can target S3 Glacier instant retrieval. But generally, you target standard S3 buckets and use lifecycle policies to move data to colder storage classes like Glacier Deep Archive. For Snowball, you import to S3 standard and then lifecycle it down. Writing directly to Deep Archive requires specific handling of metadata and object sizes.
Let's revisit the transfer family protocols. SFTP is SSH File Transfer Protocol. FTPS is File Transfer Protocol over SSL. FTP is unencrypted. Does transfer family support plain FTP?
It does, but with a massive caveat. It is supported only for VPC endpoints. You cannot expose plain FTP to the public internet via transfer family. This is a security guardrail. And frankly, if you are using plain FTP in 2026, we need to have a different conversation.
Agreed. What about the workflow feature in transfer family?
This is powerful automation. Managed workflows allow you to trigger steps after a file upload is complete. For example, a file lands in the SFTP folder. The workflow can automatically scan it for malware using a third-party tool, decrypt it if it was PGP encrypted, or move it to a different folder based on the file name. It eliminates the need to write complex Lambda triggers manually for common post-processing tasks.
One final war story before we wrap up. What's the worst migration disaster you've seen related to these tools?
A client ordered 10 snowball edges. They loaded them up with sensitive HR data. They didn't use the Ops Hub. They wrote a custom script to copy the data. The script didn't verify the right operations. They shipped the devices back. AWS imported them. The client deleted the source data immediately to free up space.
Oh no.
Turns out, their script had failed silently on 30% of the files because of long file path issues. Windows 255 character limits. They lost the data. The Snowball import report showed the failures, but they didn't read the report before hitting delete on-prem.
The lesson?
Never delete the source until you have verified the destination, and use the built-in validation tools. DataSync and the Snowball client perform checksums for a reason. Trust the tool, but verify the report.
Vital advice. To recap for the exam: 1. DataSync for online, agent-based transfer with bandwidth controls and protocol translation. 2. Snow Family for offline, bulk data movement when the network is the bottleneck. Remember the snowball math. 3. Transfer Family for modernizing SFTP/FTPS interfaces without managing servers. 4. Use Snowcone for rugged edge, Snowball Edge storage optimized for bulk migration, and compute optimized for edge processing.
And remember the hybrid pattern. Seed with Snow, sync with DataSync. That is the architecture of a successful, low-downtime migration.
You have been listening to High Yield Audio Labs. This has been our deep dive into Module 21, Data Migration Mechanisms.
Next up, we are breaking down security governance and policy. Get some rest. We will see you there.
I was looking at a post-mortem report from a major fintech firm yesterday. They attempted a lift and shift of their core transaction ledger, Oracle to Aurora PostgreSQL, and failed mid-cutover. For hours of downtime, complete rollback, and the root cause wasn't the network. It was the schema conversion. They trusted the automated tools blindly without understanding the playbook we're discussing tonight. Welcome back to High Yield Audio Labs. I'm Maya.
That is a classic tragedy, Maya. I'm Alex. And tonight, we are dissecting the AWS Database Migration Service, DMS, and its twin engine, the Schema Conversion Tool, SCT. This is Module 22 of the SAP-C02 series. We are talking about database replatforming, specifically the heterogeneous kind, moving from one engine to another. If you are listening to this, you know that moving data is easy. Moving logic, stored procedures, and proprietary Oracle PL/SQL to PostgreSQL PL/PGSQL, that is where careers end.
Exactly. The exam loves this scenario. They will give you a legacy database, Oracle SQL Server, and ask you to move it to a cloud-native target like Amazon Aurora or DynamoDB with near-zero downtime. Alex, let's start with the order of operations. You don't just spin up a DMS task and hope for the best. What is the very first tool you touch?
The Schema Conversion Tool, SCT. This is a local application, not an AWS service running in the console. You download it. You install it on a jump box or your local machine. Its job is specific. It translates the schema and the code. DMS moves data. SCT moves structure.
Right. And for the exam, it's crucial to remember that distinction. DMS does not migrate your secondary indexes, your sequences, or your stored procedures by default. It moves tables and primary keys. If you need to transform the SQL code embedded in your application, SCT is mandatory.
Correct. Now, visualize the workflow. You point SCT at your source database. Let's say a massive Oracle instance. You point it at your target, an empty Aurora PostgreSQL cluster. You run the Database Migration Assessment Report. This is the most critical document in the entire process. It gives you a color-coded breakdown of how difficult the migration will be.
I've seen questions focusing on that report. It flags items as automatically convertible or requiring manual intervention.
Precisely. It creates a migration playbook. It tells you, hey, this specific Oracle function using dbms_crypto doesn't have a direct equivalent in PostgreSQL. You have to rewrite that manually. SCT will even try to convert it for you, but if it fails, it marks it. You cannot proceed to the data movement phase until the schema on the target is ready. Once you apply the converted schema to the target, only then do you look at DMS.
Let's shift to DMS, the Database Migration Service. This is a managed service. You provision a replication instance. Alex, talk to me about sizing this instance. I see people using T2 or T3 instances for production migrations and wondering why their latency spikes.
Never use T-family instances for a production migration. The replication instance is doing heavy lifting. It is buffering data in memory, sorting it, and pushing it to the target. It is CPU and memory intensive. For the exam and for reality, you want compute optimized, C5, or memory optimized, or 5 instances. If you are doing a heterogeneous migration like Oracle to Postgres, the replication instance has to actually convert data types on the fly. That burns CPU cycles.
And where does this instance live? In the VPC, right?
Yes, it needs network line of sight to the source and the target. This brings up security groups. The replication instance needs outbound access to the source on the database port, say 1521 for Oracle, and outbound access to the target on 5432 for Postgres. It acts as the bridge.
A common exam trick is the public internet scenario. The source is on premises. The target is in AWS. The exam asks how to secure the traffic.
You never send database traffic over the open internet if you value your job. You use a VPN or direct connect. The replication instance sits in a private subnet. The traffic flows over the PrivateLink. However, if you absolutely must use the internet, the replication instance must be in a public subnet with a public IP, and you restrict the source firewall to only accept connections from that specific elastic IP. But for SAP-C02, assume direct connect.
Okay, let's get into the mechanics of the migration itself. We have 3 major task types in DMS: full load plus CDC, and CDC only. Break these down.
Full load is a snapshot. It grabs the data as it exists right now and moves it. It does not care if new transactions are happening during the move. If you insert a record while the full load is running, that record might be missed if the scanner has already passed that table.
Which is why full load usually requires downtime. You stop writes to the source, move the data, then point the app to the new DB. But the exam standard is minimal downtime.
That's where full load plus CDC comes in. CDC stands for Change Data Capture. This is the magic. DMS does the full load, but while that is happening, it caches all the incoming changes, updates, deletes, inserts that occur on the source. Once the full load finishes, it applies those cache changes to the target until they are synchronized.
This relies on the source database's transaction logs, doesn't it?
It does. And this is a huge configuration gotcha. DMS doesn't just work by magic. You must configure the source database to retain logs long enough for DMS to read them. For Oracle, you need archive log mode enabled. For MySQL, you need binary logs enabled and set to row format. If you don't enable these, CDC will fail immediately. The exam will give you a scenario where a CDC task fails with a generic error 90% of the time. Logging is disabled on the source.
So, the strategy for minimal downtime is 1. Use SCT to create the schema on the target. 2. Start a full load plus CDC task. 3. Let it reach a state called load complete, replication ongoing. At this point, the databases are in sync. 4. Briefly stop the application, verify the queues are empty, and switch the connection string to the new database.
Exactly. That cutover window can be seconds. But there is a hidden danger here: triggers.
Oh, this is a painful one.
If you migrate a table that has a trigger, say, on insert, email the admin, and you migrate that trigger using SCT before the data load, every single row DMS inserts will fire that trigger. You will send 10 million emails and crash the database.
So the rule is, disable triggers and foreign key constraints on the target during the full load phase. Enable them only during the cutover or apply them after the full load is done.
Ideally, you migrate the schema, tables and primary keys only, first. Run the data load. Then, apply the secondary indexes, foreign keys, and triggers. This improves performance massively. Indexes slow down inserts. If you try to load a terabyte of data into a table with 10 indexes, it will crawl. Build the indexes after the bulk data is there.
Let's talk about blobs. Large objects. JSON blobs, images stored in the DB. DMS hates these.
It effectively despises them. DMS has two modes for lobs: limited LOB mode and full LOB mode. In limited mode, you tell DMS, I promise no LOB is bigger than 32 kilobytes. DMS allocates a fixed buffer. It is fast, but if you have a 33 kilobyte file, DMS truncates it. Data corruption. Silent data corruption.
And full LB mode?
Full LOB mode is safe, but slow. DMS checks the size of every LOB, allocates memory dynamically, and moves it chunk by chunk. It kills migration speed. The exam compromise? Use limited LOB mode, but set the limit high, like 100 megabytes, if your memory on the replication instance can handle it, or identifying the largest LOB you have beforehand.
What about validation? How do we know the data is actually identical?
You enable validation on the DMS task. It is a checkbox, but be warned, it reads the data from the source and the target again to compare them. It doubles your read throughput costs and extends the timeline. But for a financial ledger, it is non-negotiable.
Let's scale this up. What if we are migrating 500 databases? Managing 500 tasks is a nightmare.
AWS DMS Fleet Advisor is the tool for the discovery phase, helping you inventory what you have. But for the actual movement, you just scale your replication instances. You can also use the DMS API to automate the task creation.
I want to touch on a specific heterogeneous mapping scenario, the transformation rules.
Powerful feature. You can rewrite schema names, table names, or column names on the fly. Suppose you are consolidating 10 different databases into one multi-tenant Aurora cluster. You can use transformation rules to prefix the table names with the tenant ID as they flow through the pipe. It happens in memory on the replication instance.
That connects to the SCT extraction agents. When do we need those?
Great question. Sometimes the data is just too complex, or the source database is a data warehouse like Teradata or Greenplum. A simple JDBC connection isn't enough. You install SCT extraction agents on servers close to the source. They work in parallel to pull data, compress it, and upload it to S3. Then DMS or a native loader pulls it from S3 into the target, like Redshift. But for standard OLTP migrations, Oracle to Aurora, standard DMS endpoints are usually sufficient.
Let's do a quick comparison for the listeners. When do you not use DMS?
If you are staying on the same engine, Postgres to Postgres, MySQL to MySQL, use the native tools first. Use a read replica if possible. If you are on RDS MySQL and want to move to Aurora MySQL, just create an Aurora read replica of the RDS instance and then promote it. That is infinitely more stable than DMS. DMS is a translation layer. Translation introduces risk. Native replication is binary. Always prefer native.
But the exam will force the heterogeneous scenario. Oracle to Aurora PostgreSQL. That's the keyword combo.
In that case, your golden path is 1. Schema Conversion Tool, SCT, for assessment and schema migration. 2. Provision DMS replication instance, multi-AZ for production. 3. Configure source/target endpoints. Don't forget the SSL certs. 4. Create task, full load plus CDC. 5. Monitor CDC latency source and CDC latency target metrics in CloudWatch. 6. Cutover.
You mentioned metrics. CDC latency source versus CDC latency target. What's the difference?
Critical debugging. If CDC latency source is high, it means DMS is struggling to read from the Oracle redo logs fast enough. You might need to increase throughput on the source. If CDC latency target is high, it means the replication instance can't write to Aurora fast enough. You might need to scale up the Aurora writer node or the DMS instance itself.
One final scenario I see popping up. You have a 50 terabytes database. The internet pipe is too small.
DMS can use Snowball. You send a Snowball edge device to the data center. You use the SCT extraction agents to dump the data to the Snowball. You ship the Snowball to AWS. It gets loaded into S3. Then, DMS takes over. It loads the bulk data from S3, and then, this is the cool part, it connects back to the on-prem database to catch up on the CDC logs that generated while the Snowball was in the mail. It stitches the timeline together.
That is the ultimate hybrid migration. High-yield Audio Labs listeners, remember that flow: Snowball for bulk, DMS CDC for the tail.
Exactly. It's elegant.
We've covered the tools, the sizing, the task types, and the traps. Replatforming is as much about planning as it is about execution.
The code is easy, the state is hard. Respect the state.
Perfectly said. This has been a deep dive into SAP-C02 database replatforming with DMS and SCT. Review the Database Migration Assessment Report concept before you sleep tonight. I'm Maya.
And I'm Alex. Good luck with the migration. Honestly, the bandwidth throttling was the least of their problems. The real issue was that they tried to force an agentless migration on a fleet of legacy bare metal servers that barely had reliable IPMI access, let alone a hypervisor API we could hook into. It was a disaster waiting to happen.
Which brings us directly to the gold standard for avoiding that exact scenario. Welcome back to High Yield Audio Labs. Tonight, we are dissecting the AWS Application Migration Service, or MGN. If you are sitting for the SAP-C02, you need to know this service cold. It is the primary answer for lift and shift migrations now that Server Migration Service and Cloud Endure are effectively legacy history in the exam's eyes.
Exactly. If you see a question about rehosting or lift and shift on the exam, your brain should immediately auto-complete to MGN. It's block-level replication, it's agent-based by default, and it is highly resilient.
Let's start with the architecture, Alex. A lot of candidates get confused about where the data actually sits before the cutover. It's not sitting in a target EC2 instance that's burned 24/7, right?
Correct, and that is a massive cost optimization point the exam loves. When you install the AWS replication agent on your source server, whether that's on-prem, in Azure, or GCP, it begins streaming block-level data. but it doesn't stream it to your final production instance. It streams it to a staging area in your target AWS subnet.
Define staging area for the record.
It's a lightweight, low-cost infrastructure. AWS spins up small replication servers, usually T3.small or similar, that receive the data stream. These servers write the data to Amazon EBS volumes. So, for 99% of your migration timeline, you are only paying for cheap storage and tiny compute instances. You aren't paying for that massive or 5.4's large database server until you actually click Launch.
That is a critical distinction. The source server is the source, the staging infrastructure is the staging area, and the final EC2 instance is the target. Now, let's talk about the agent. Installing software on a production server always makes change advisory boards nervous. What are the hard requirements?
The AWS replication agent is surprisingly lightweight, but it needs root or administrator privileges to install because it installs a kernel-level driver to capture block writes. It supports Linux and Windows. It communicates back to AWS over HTTPS, port 443, for control plane signaling. But, and here is the exam trap, the actual data replication traffic goes over TCP port 1500.
Wait, pause there. TCP 1500. If I have a strict corporate firewall or I'm sending traffic over a direct connect with a restrictive NACL and I forget port 1500?
The replication will never start. The console will show disconnected or stalled. You need outbound 443 to the MGN API endpoints and outbound 1500 to the MGN data endpoints. And if you are using a private subnet for your staging area, which you should be for security, you need to ensure those replication servers have a route back to the source.
Can we route that over the internet?
You can, and it's encrypted in transit using TLS 1.2 or higher. But for the SAP-C02, if the scenario mentions regulated industry or sensitive financial data, you strictly route that over a VPN or direct connect. You do not want block-level database writes traversing the public internet if you can avoid it.
Okay, let's move to the lifecycle states. This is where the operational questions live. You install the agent, it authenticates, and then what?
It enters initial sync. This is the heavy lifting. It reads every block on the source disk and ships it to the staging EBS volumes. Once that reaches 100%, the state shifts to healthy and continuous data replication. Now, it's just shipping the deltas. Every time a block changes on source, it's replicated. The lag is usually sub-second.
So it's effectively a continuous backup at this point.
Precisely. But here is the mechanism that trips people up: launch settings. You cannot launch an instance until you define how it launches. This is the EC2 launch template. You map the source, say a 4-core, 16 GB server, to an AWS equivalent, maybe an M5 large. You define the subnet, the security group, the IAM role.
And does MGN guess the right size?
It tries. It has a right-sizing recommendation engine based on the data it sees from the agent. But a good architect verifies this. You don't want to migrate a legacy server that was 90% idle and provision an identical AWS instance size. You want to downsize. That's a classic cost optimization scenario on the exam.
Okay, we are synced. We are healthy. The boss says migrate it. Do we just click cutover?
Absolutely not. If you click cutover without testing, you are failing the exam and probably getting fired. The required workflow is test, then cutover. You must launch a test instance first.
Walk me through the mechanics of a test instance. Does it stop replication?
No, and that is the beauty of it. When you launch a test instance, MGN takes a snapshot of the EBS volumes in the staging area at that exact second. It then uses that snapshot to hydrate EBS volumes for a new EC2 instance. The replication from the source continues uninterrupted to the staging area. The source doesn't know anything happened. You can spin up this test instance, log in, verify the application starts, check your database consistency, and then terminate it.
So I can run a non-disruptive disaster recovery drill or migration test in the middle of the workday.
Exactly. And the console tracks this. The lifecycle state moves to test in progress. Once you verify it and terminate the test instance, you mark the server as ready for cutover. The exam engine looks for this specific flag. You physically cannot initiate a cutover until the lifecycle indicates ready for cutover, which implies a test was performed or at least marked as done.
Let's talk about the cutover itself. We are in the maintenance window. We are ready to flip the switch. What happens to the source?
In a standard cutover, you shut down the source application to stop new writes. You wait for the replication lag to hit 0, meaning the staging area has every last bit of data. Then you click Launch Cutover Instance. Just like the test, it snaps the staging volumes, spins up the production EC2 instance, and converts the boot process to run on AWS.
Converts the boot process?
Yes, this is what MGN does under the hood. It injects the necessary Zen or Nitro hypervisor drivers, installs the ENA network drivers, and modifies the bootloader so the OS, which thought it was running on a Dell server or a VMware cluster, can actually boot on EC2 hardware. This machine conversion step takes a few minutes.
And what happens if the conversion fails?
Then you have a conversion failed status. Usually, this is due to an unsupported kernel version or a weird partition layout. But notice, your source server is still there. You haven't destroyed anything. You just fix the issue and try again. It is a very safe, non-destructive process until you explicitly decide to decommission the source.
One of the newest features integrated into MGN is the post-launch actions. This feels like a huge area for exam modernization questions. Instead of just booting a server and then having a human SSH in to fix things, we can automate it.
Correct. This leverages AWS Systems Manager, or SSM. You can configure MGN to automatically install the SSM agent on the migrated instance as soon as it boots. Once that agent is online, MGN can trigger a predefined runbook.
Give me some examples of what we'd automate here.
The classic one is uninstall the replication agent. Once you are on AWS, you don't need the migration agent anymore, so the script cleans it up. Another massive one is install CloudWatch agent. You want observability immediately, or join domain. If it's a Windows server, you can have a document that joins it to your AWS managed AD.
So for the exam, if the requirement is ensure all migrated servers automatically have the latest security patches and logging agents installed upon first boot, the answer involves MGN post-launch actions with SSM documents.
Spot on. It removes the human error gap between the server turning green and the server being compliant.
Let's pivot to a specific exam scenario, the cutover window constraint. A question might say, you have 50 servers to migrate. You have a 4-hour window. How do you orchestrate this? You can't click 50 buttons manually.
No, you use the wave concept. You group applications into waves. In the console, or more likely via the CLI or API, you trigger the launch for an entire wave simultaneously. MGN orchestrates the parallel launching. But here is the bottleneck to watch for: AWS API limits. If you try to launch 500 instances at the exact same second, you might hit EC2 request limits or MGN throttling.
So the answer is to batch them?
Batch them, or ensure you have requested a quota increase for your account well in advance. And remember, the cutover job includes waiting for the instance to boot and pass status checks. That takes time.
What about revert? Let's say we cut over, the app runs for an hour, and then we find a critical data corruption issue that we missed in testing. We need to go back to on-prem.
This is where resync versus revert gets tricky. If you just shut down the AWS instance and power the on-prem server back up, you are back online, but you have lost that hour of data. If you need that data, you actually have to reverse the replication direction.
Can MGN do that?
MGN is primarily one way. For failback, you often have to treat the on-prem environment as a new, target and replicate back, or manually export the data. However, for the SAP-C02 context, usually the fallback plan is simply turn the on-prem server back on and accept the data delta or manually replay transactions. The exam rarely asks about automated failback with MGN because MGN is a migration tool, not a bidirectional DR tool like Elastic Disaster Recovery, DRS.
Important distinction. MGN is for move and forget. DRS is for protect and recover.
Exactly. They share the same underlying technology. The block replication engine is identical, but the use case is different. MGN shuts down the replication after a successful cutover is finalized. DRS keeps replicating forever.
Let's talk about the agentless option. For a long time, Cloud Endure was agent-only. MGN introduced an agentless option for vCenter. When do we use that?
Only when you physically cannot install an agent. Maybe the OS is so old that the agent doesn't support it, or maybe strict compliance rules forbid third-party software agents. You deploy an MGN vCenter client, OVA, into your VMware environment. It snapshots the VMs and sends the data. But, and this is a big but, it is generally slower and has more limitations than the agent-based approach. The agent is always the preferred answer for minimized downtime and continuous replication.
Why is the agent faster?
Because the agent sits in the OS kernel. It sees the write happen in memory and ships it. The agentless approach relies on VMware snapshots, which creates a stun on the VM and is less granular. For a high-transaction database, agentless can actually crash the application due to snapshot stun. Agent-based is almost invisible to the OS.
That connects back to the bandwidth question. If we have limited bandwidth, say 100 megabits per second, and we are migrating 10 terabytes, how do we handle that?
You can throttle the bandwidth in the replication settings. You don't want the migration to choke out your production user traffic. You can set a cap, say max 50 megabits per second. It will take longer to sync, but it protects the link.
What if the link is just too small to ever catch up? The data churn rate, the rate at which new data is written, is higher than the bandwidth can support.
That is a death spiral. The replication will never reach 100% synced. In that scenario, the exam answer is usually use AWS Snowball Edge to seed the data.
Explain the seeding workflow with MGN.
You order a Snowball device. You copy the static data to it. You ship it to AWS. It gets loaded into an S3 bucket. Then, you tell MGN to use that S3 data as the preloaded state for the staging EBS volumes. The agent then only has to sync the changes that happened since you shipped the Snowball. It drastically reduces the network load.
Critical workflow. Snowball for the bulk, MGN agent for the delta.
Yes, it's the only way to migrate massive datasets over thin pipes without days of downtime.
I want to drill into the security aspect again. We mentioned the private replication subnet. What about IAM? What permission does the agent need?
When you install the agent, you generate temporary IAM credentials from the MGN console or use an IAM user with specific permissions. The policy needs MGN, send client metrics, MGN, send client logs, and access to the staging area resources. The best practice is to rotate these keys. But on the target side, the replication servers need an IAM role attached to them so they can write to EBS and talk to the MGN control plane.
And does the data get encrypted at rest in the staging area?
Yes, you can and should specify a KMS key in the replication settings. By default, it might use the default EBS key, but for enterprise requirements, you should use a customer managed key, CMK, so you can audit the usage.
Let's do a quick lightning round of troubleshooting. Scenario 1. You install the agent, but it fails to connect to AWS.
Check DNS resolution first. Can the server resolve the MGN endpoint? Then check outbound port 443. Then check if your IAM credentials are valid or expired.
Scenario 2. The replication is stuck at 95% and never reaches 100%.
High churn rate or network instability. Check if the disk I/O on the source is overwhelming the agent, or if there is packet loss on the route to AWS. You might need to increase the instance size of the replication server in the staging area to handle the throughput.
Wait, we can resize the replication server?
Yes, by default, it's a T3.small. If you are blasting 500 megabytes per second of data, a T3.small will run out of CPU credits and network burst balance. You go into the replication settings and change the replication server instance type to something like a C5.large or M5.large.
That is a pro tip. If the bottleneck isn't the network, it might be the staging compute.
Absolutely. The staging server has to process that incoming stream, decrypt it, and write it to disk. That takes CPU.
Scenario 3. The cutover instance launches, but you can't SSH into it.
Security groups. The launch template probably has a default security group that doesn't allow port 22 from your IP. Or the source server had a local firewall, like Iptables or Windows Firewall, that is blocking the connection, and that setting migrated with the server.
Classic. The lift and shift includes the lift and shift of misconfigurations.
Every time. If you had a broken config on-prem, you now have a broken config in the cloud. MGN copies the blocked device bit for bit. It doesn't magically fix your broken SSHD_config file.
Before we wrap up, Alex, give me the golden rule for MGN on the SAP-C02.
The golden rule is minimize downtime. MGN is designed for continuous replication so that the cutover window is measured in minutes, not hours. If an exam question asks for lowest RTO, recovery time objective, for a migration, MGN is almost always the answer over manual export/import methods like VM import/export. VM import/export is offline. MGN is online.
And remember the workflow. Agent dash, staging area dash, test instance dash, ready for cutover dash, post-launch actions.
And don't forget to decommission the source eventually. You don't want to pay for both environments forever.
That creates a split-brain scenario if users start writing to the old database while the new one is live.
Which is why the final step of the cutover checklist is always shut down source. Not delete, but shut down. Keep it offline for a week just in case.
Excellent. This has been a deep dive into AWS Application Migration Service. If you master these lifecycle states and the architecture of the staging area, you're going to crush every migration question on the exam.
And for those listening, if you want to verify your knowledge, go build this. Spin up a free tier EC2, pretend it's an on-prem server, and use MGN to migrate it to another region. Seeing the replication lag drop to 0 is a feeling of pure victory.
Thank you for listening to High Yield Audio Labs. We build experts here. Good luck with your study, and we will see you in the next module.
Stay secure, everyone. So the mainframe team swore the latency was network jitter, but when we actually traced the packet flow, The bottleneck was a 20-year-old SOAP interface trying to parse a 10 MB XML payload synchronously. The entire checkout process hung for 30 seconds because one legacy inventory service was garbage collecting. That is the definition of tight coupling, and that is exactly why the monolithic architecture had to die that night.
Which brings us perfectly to the final frontier of the SAP-C02 blueprint. Tonight on High Yield Audio Labs, we are dissecting application modernization. We are taking those brittle, monolithic giants and surgically carving them into resilient, scalable microservices. I'm Maya, looking at this from the audit and compliance angle, specifically how you verify these new distributed systems actually work.
And I'm Alex. I'm here to make sure you understand the architectural why. The exam doesn't just ask what a service does. It asks you to choose the best path for refactoring under specific constraints, cost, operational overhead, or speed of migration. Modernization isn't just about using Lambda. It's about decoupling.
Let's start with the strategy. The exam loves the strangler fig pattern. Alex, paint the picture for the candidate who sees a scenario about a massive e-commerce monolith running on on-premise servers. They need to migrate to microservices without downtime. What is the very first move?
The first move is not to rewrite the code. If you rewrite from scratch, you fail. The strangler fig pattern is about creating a facade. You place an API gateway or an application load balancer in front of your legacy monolith. Initially, this facade routes 100% of the traffic to the old system. The client applications, the mobile app, the website, they don't know anything has changed. They just see a new endpoint.
Right. And then you identify one distinct slice of functionality. Say, the user profile service. You build that as a modern microservice, maybe on ECS Fargate or Lambda. Then you tweak that API gateway facade to route requests for /users to the new service, while everything else still goes to the monolith. You slowly strangle the old system until it's gone.
Exactly. For the exam, watch out for the implementation details of that facade. If the legacy app uses REST, API gateway is your weapon. It can handle traffic shaping, throttling, and authentication offloading. But if you're dealing with a legacy application that requires sticky sessions or long-lived connections that API gateway might struggle with specifically in a high-throughput private context, an application load balancer using path-based routing is often the correct answer for the initial split.
Let's talk about the compute layer. You mentioned Fargate. A lot of questions will force you to choose between EC2, ECS, EKS, and Lambda. If the scenario mentions a legacy Java or .NET application and demands minimal code changes but containerized portability, what is the trigger word?
The trigger is app2 container. This is a CLI tool that analyzes your running application, on-prem or on EC2, and automatically generates the Docker container image, the ECR repository, and the ECS task definitions or Kubernetes pod specs. It even creates the CI/CD pipeline in code pipeline. If the question asks for the fastest way to containerize a legacy Java app, app2 container is the answer.
And once it's in a container, you have to run it. Here is the decision matrix I use. If the organization has existing Kubernetes expertise or needs open source tool compatibility, you choose EKS. If they want to minimize operational overhead and have no preference for Kubernetes, you choose ECS. But Alex, when do we force Fargate?
You force Fargate when the scenario specifies remove infrastructure management or serverless containers. With Fargate, you don't patch the OS. You don't manage the underlying EC2 instances. You define CPU and memory at the task level. However, be careful. If the scenario mentions specific kernel-level tuning requirements or using a specific GPU instance type that Fargate doesn't support yet, you must fall back to ECS on EC2 managed instances. Moving
deeper into refactoring, we often see the requirement to break apart the database. The shared database anti-pattern is the silent killer of microservices. You can't have 10 microservices all reading and writing to the same RDS instance. If you change the schema for one, you break the others.
Correct. This is where the exam tests your knowledge of database per service. Each microservice owns its data, but this introduces a massive problem: distributed transactions. In a monolith, you just wrap everything in a SQL transaction block. Commit or rollback. Easy. In microservices, if service A charges the credit card and service B updates inventory, and service B fails, you can't just roll back service A's committed database transaction.
You need the saga pattern.
The saga pattern. You must know the difference between choreography and orchestration for the SAP-C02. In choreography, services emit events. Service A finishes and emits order created. Service B listens, does its work, and emits inventory updated. It's decentralized. It scales well, but gets hard to debug. We call it the confused deputy problem sometimes, where you lose track of who triggered what.
Which leads us to orchestration. This is almost always the preferred answer for complex workflows on AWS. You use AWS step functions. The state machine defines the flow. If a step fails, step functions executes a compensating transaction logic you write specifically to undo the previous work. For example, issuing a refund if the inventory update fails.
Step functions is critical. Remember standard workflows versus express workflows. Standard is for long-running processes, up to 1 year. Think human approval chains or order fulfillment. Express workflows are for high-frequency, short-duration tasks, under 5 minutes. If you're building a high-volume event ingestion engine, Express is the cost-effective choice.
Let's pivot to the ultimate modernization, serverless Lambda. The exam loves Lambda for event-driven architectures. But there are constraints. The 15-minute timeout is the hard limit. If you have a legacy batch job that runs for 4 hours, you cannot just lift and shift it to Lambda.
You have to refactor. You'd break that batch job into smaller chunks using S3 event notifications or DynamoDB streams to trigger Lambdas for individual records. Or you move that logic to AWS Batch or Fargate. But let's stay on Lambda, the cold start issue. If you are migrating a latency-sensitive banking application written in Java, a cold start of 3 seconds is unacceptable.
The fix is Lambda SnapStart or provision concurrency. SnapStart is specifically for Java. It takes a snapshot of the initialized memory state and caches it. When the function is invoked, it resumes from that snapshot in milliseconds. Provision concurrency keeps a specific number of environments warm and ready. It costs money even when idle, but it guarantees 0 cold starts for that capacity.
Let's talk about messaging. Decoupling is the heart of modernization. You need to stop services from calling each other synchronously via HTTP whenever possible. If the receiving service is down, the sender fails. That's bad architecture.
Enter SQS and SNS. The classic fan-out pattern. A user uploads a photo. You need to generate a thumbnail, update the database, and send an email. You don't do this serially. You publish one message to an SNS topic. That topic pushes the message to 3 distinct SQS queues. 3 different Lambda functions process those queues in parallel. If the email service fails, the email SQS queue retains the message. The thumbnail generation isn't affected.
And specifically regarding those failures, dead letter queues, or DLQs. Every asynchronous architecture must have them. If a message fails processing 5 times, move it to a DLQ so you can analyze why it failed later without blocking the main queue. For the exam, know that Lambda, SQS, and SNS all support DLQs, but the implementation is slightly different. With SQS, you configure the redrive policy.
I want to touch on a specific migration tool that appears in the context of Windows workloads, the porting assistant for .NET.
Good call. If you have a legacy .NET Framework application tied to Windows IIS, and you want to move it to .NET Core or .NET 6 to run on Linux containers, which are cheaper, you use the porting assistant. It scans your source code and tells you exactly which libraries are incompatible and suggests replacements. It's a code-level refactoring tool.
Contrast that with End-of-Support Migration Program, EMP, for Windows Server.
EMP is for when you cannot refactor. You have an old application running on Windows Server 2003 or 2008. You lost the source code. The developer retired 10 years ago. EMP packages that application into a container along with the necessary OS dependencies and registry keys, so it can run on a modern version of Windows Server on AWS. It's a lifeboat, not a modernization, but sometimes it's the only answer.
Let's look at a war story scenario. I audited a client who moved their monolithic API directly to API Gateway and Lambda. They were thrilled. Serverless. But their bill at the end of the month was triple their old EC2 bill. What happened?
They ignored the high-frequency polling trap. They had thousands of IoT devices polling the API every second to check for updates. API Gateway charges per million requests. Lambda charges per invocation. If you have high volume, predictable, constant traffic, Serverless can be more expensive than reserved instances or Fargate Spot.
Exactly. The fix was implementing AppSync with GraphQL subscriptions. Instead of polling, the devices opened a WebSocket connection. The server pushes updates only when data changes. It slashed the request volume by 99%.
That's a key exam concept, protocol modernization. Moving from REST polling to WebSockets or GraphQL for real-time data. Also, keep an eye on AWS AppSync as the answer for unifying data from multiple sources, DynamoDB, Elasticsearch, Lambda, into a single API.
Let's dig into EventBridge. It's slowly replacing CloudWatch events in the exam lexicon. Why choose EventBridge over SNS for internal event routing?
Structure and filtering. EventBridge is an event bus. It allows for content-based filtering. You can say, only trigger this target if the JSON payload has status, error, and source, payment service. With SNS, filtering is possible but less granular. Plus, EventBridge has the schema registry. It can automatically discover the structure of events flowing through your bus and generate code bindings for your IDE. That is huge for developer velocity.
And it integrates with third-party SaaS partners. If you want to trigger a Lambda function every time a ticket is updated in Salesforce or Zendesk, EventBridge has native partner integrations. You don't need to write a webhook poller.
Let's address the legacy message brokers. The exam often features a scenario with a mainframe or on-premise system using ActiveMQ or RabbitMQ. They want to migrate to the cloud with zero code changes. They don't want to rewrite their producers and consumers to use SQS APIs.
Amazon MQ. That is the answer. It is a managed service for Apache ActiveMQ and RabbitMQ. It supports standard protocols like AMQP, MQTT, OpenWire, and Stomp. You literally just change the endpoint URL in your application configuration. It is a lift and shift for message brokers. SQS is a refactor because it requires using the AWS SDK.
Correct. Now, let's talk about the database layer again. Specifically, SQL Server to Aurora PostgreSQL. This is a common modernization path to escape licensing fees. But rewriting T-SQL queries to PL/PG-SQL is a nightmare.
Babelfish.
Babelfish for Aurora PostgreSQL. It teaches the Postgres engine to understand the SQL Server wire protocol and T-SQL commands. Your application thinks it's talking to SQL Server, but it's actually talking to Aurora. It allows you to run legacy apps on open-source databases with minimal code changes.
I want to circle back to service discovery. When we had a monolith, function a called function B in memory. In microservices, service A needs to find the IP address of service B, which might be a container explicitly shifting around on different nodes.
If you are an EKS, you use the native Kubernetes core DNS. But if you are an ECS or using a mix of EC2 and on-prem, you use AWS Cloud Map. Cloud Map allows you to register any application resource, such as URLs, queues, or IPs, with custom names. It integrates tightly with ECS service discovery, so your code just calls http://order-service, and Cloud Map resolves it to the current healthy IP addresses.
Speaking of healthy, let's talk about canary deployments in the context of modernization. You've refactored your service. You have a new version. How do you roll it out safely?
For Lambda, you use code deploy with traffic shifting aliases. You can configure a linear or canary deployment. For example, canary 10% 5 minutes. It sends 10% of traffic to the new version. If any CloudWatch alarms fire, like increased error rates or latency, code deploy automatically rolls back to the old version immediately. This effectively eliminates downtime caused by bad deployments.
And for ECS?
Same concept. ECS integrates with code deploy for blue/green deployments. It spins up a replacement set of tasks, the green set. It puts them behind the load balancer, but on a test listener port. You can run validation tests against them. If they pass, the load balancer swaps the production traffic to the green set and drains the blue set.
Let's discuss domain-driven design (DDD) briefly, as it informs how you slice the monolith. The exam might describe a complex application with mixed concerns.
You look for bounded contexts. Identify the seams in the business logic. Billing is a context. Shipping is a context. Inventory is a context. These boundaries define your microservices. Don't build nanoservices, like a service just for adding 2 numbers, that introduces latency without value. The service should own a full business capability and its data.
High-Yield Audio Labs listeners should also be aware of the data lake integration in modernization strategies. Often, when you break apart the database, the analytics team panics because they can no longer run massive join queries across all tables.
That is a classic friction point. The solution is to have each microservice publish its data changes or domain events to a data lake, usually S3, via Kinesis data firehose. Then, the analytics team uses Athena or Redshift to query the aggregated data. Do not let the analytics team connect directly to the microservice operational databases. That couples the systems again and impacts performance.
What about secrets management? In the monolith, connection strings were often in a config file on the server. In a distributed containerized world, that is a security disaster.
AWS Systems Manager Parameter Store or AWS Secrets Manager. For the exam, know the difference. Parameter Store is free for standard throughput and great for configuration strings. Secrets Manager is costlier but offers automatic rotation of secrets, like database credentials. If the requirement is rotate RDS passwords every 30 days automatically, the answer is Secrets Manager.
Let's do a rapid-fire round on anti-patterns. I'll name a scenario. You tell me why it fails the well-architected review. Scenario 1. Using Lambda to process a file upload that takes 20 minutes to process.
Fails. Lambda timeout is 15 minutes. Use AWS batch or ECS tasks triggered by the S3 upload event.
Scenario 2. Hard-coding the SQSQ URL in the Lambda function code.
Fails. Configuration should be in environment variables. If you redeploy the stack, the URL changes and you don't want to recompile code.
Scenario 3. Storing user session data in the local file system of the web server container.
Fails. Containers are ephemeral. If the container crashes or scales in, that session data is lost. Use an external state store like Elasticache, Redis, or a DynamoDB table for session management.
Scenario 4. A synchronous call chain. Service A calls B, B calls C, C calls D.
Fails. The distributed monolith. Latency stacks up. If D fails, the error cascades all the way back to A. Use asynchronous messaging, SQS/SNS, between services to decouple them.
I want to reinforce the 12-factor app methodology. It's the philosophy behind all this. Config in the environment. Backing services attached resources. Logs as event streams.
And specifically disposability, fast startup and graceful shutdown. This is why we care about Lambda cold starts and why we use SIGTERM handling in our Docker containers. When ECS tells a task to stop, the application should finish its current request and close connections cleanly, not just crash.
Let's talk about the API gateway caching feature.
Crucial for performance. If you have a microservice returning product catalog data that changes once a day, enable caching at the API gateway stage. This prevents 99% of calls from even hitting your backend Lambda or ECS, saving massive amounts of money and latency. You can configure the time to live, TTL.
And throttling.
Yes, to protect your downstream legacy systems. If your modernization is partial and the mainframe can only handle 50 requests per second, you configure a throttling plan on API Gateway to reject excess traffic with a for 29 too many requests error, ensuring you don't crash the backend.
We're nearing the end of the session. Let's synthesize this into a final exam strategy for application modernization questions.
When you see a question about modernizing, look for the constraint. If the constraint is speed/least effort, rehost, lift, and shift, using tools like AWS MGN, Application Migration Service, or VM Import/Export. If the constraint is portability, containerize using app2 container. If the constraint is cost, scalability, greenfield, refactor to serverless, Lambda, DynamoDB, API Gateway. If the constraint is legacy/proprietary, Replatform, Amazon MQ, Babelfish, EMP for Windows.
And always verify the operational excellence pillar. Are you logging to CloudWatch? Are you tracing with X-Ray? A distributed system without observability is a black box you cannot debug. X-Ray is the specific tool for visualizing the flow of requests across microservices.
One final note on multi-region modernization. If you are going global, use DynamoDB global tables for multi-region active data and Route 53 geolocation routing to send users to the nearest API gateway. That is the gold standard for high availability and low latency.
Perfect. You have the tools. You understand the patterns. You know that Strangler Fig is your strategy, decoupling is your goal, and serverless is your destination where appropriate.
Don't let the complexity of microservices scare you. It's just separation of concerns at a network level. Manage the state, manage the failure, and you will pass.
This has been the SAP-C02 Application Modernization Deep Dive. I'm Maya.
And I'm Alex.
You are listening to High Yield Audio Labs. Good luck and good night.